All right, well, welcome to the fourth RCN workshop at NYU Brooklyn, and it's, of course, on millimeter wave research and technology, and I am representing, and this is in some ways, I can only represent one or the other at any one point in time, but I'm representing NSF first and foremost, since I've been a program director there since November, and I'm also, from the University of Wisconsin. So, welcome everyone. We have an exciting program going on, and of course, it's great to be here at NYU as one of the big players and movers and shakers of millimeter wave wireless. Okay, so this is a slide that I've been using since the beginning, and it's still there were exciting times when it started, 2016. That's when I ran into Ted there at the announcement of the FCC Spectrum Frontiers announcement. And this RCN is part of that related announcement by NSF on a $400 million advanced wireless initiative, which is a brainchild of Thiaga and Nandagopal. He couldn't be here today, but this is one of parts of that initiative. And of course, the PAR platforms, which two of them were announced recently, NYU and Rutgers and Columbia are part of one, and then that's a Cosmos, and then Powder at Utah, Salt Lake City. So that's great. And, there's a lot of, it's a big part of 5G, as we all know, gigabit speeds, millimeter wave, millisecond latency, although that's still a challenging task, and hopefully there'll be some exciting discussion on that. And several use cases, but the big one initially is going to be the fixed wireless. That's going to be happening, and then some people think it's the killer app for autonomous vehicles, and then eventually we'll get to small cell mobile devices too, and backhaul is already being used. A lot of frequencies, FCC has played a big role, and a lot of exciting developments that we'll get to hear more today as well. Just to give you a quick background of where it's coming from, especially for those who are coming here for the first time, there are three big areas that we think: hardware, networking, communication and signal processing algorithms that play a role in wireless in general and millimeter wave in particular. And we've been talking about cross-layer for a long time, but this is really an area where cross-layer can't be, interaction can't be ignored. You're just going to sub-optimize things. And prototypes and testbeds make a big impact here as power platform, and that's going to be a big discussion here as well. And then industry, academia, government agencies, all are playing a role, national labs as well. And so the goal here is to really cross-fertilize the ideas across the three players or classes of players to fuel the development of millimeter wave wireless technology. Now, it's easier said than done, but we've been trying our best. And so we've had 3 workshops, starting in DC, and then Madison, and then last one in Tucson. And I think Marwan Kroon's, our host there, is around here too. He's part of a member of the steering committee. And so here's a steering committee, a whole bunch of people here. Sandeep Rangan, the local host here. He should be around here somewhere. There he is. And then Jim is not here. Ismail is here from NC State. Marwan is here. Hanglu is here. Ali injured his, not broke, luckily. Injured his knee, so he can't be here. Soccer fan. And Amitava was out in Santa Clara, maybe still there. I think Ozga is here from Qualcomm. And Carlos couldn't be here. Ashwin was at 5G. He's back. And Ian has a rep here, Charlie. And Kate Remley is here from NIST. And Tommy Swenson from Chalmers is there too. So we have a good attendance. These people guide us to some extent. And here is a new NSF building. If you haven't been there, come and visit us. Send us your great ideas. Serve on panels. It's very convenient, 10-minute metro ride from Reagan. And our offices are on the 14th floor on the east wing. Okay, so some big themes that have emerged, which are going to be emphasized here too, is hardware signal processing interface, signal processing networking interface. And last time we had a very exciting discussion on the interplay with the 5G NR standards, which are coming from 3GPP, and then the Wi-Fi standards. And they're kind of evolving, decoupled, but there's some possibility for synergy, and appropriate channel models for both. And of course, this is a place where a lot of channel modeling has happened. And then really the need for test beds for research and experimentation at academia. Everyone has said they're very expensive, and the technology, the way it's going to evolve is changing. So that's an important theme that we're going to emphasize here too. And I'll say a little bit more about that. There's a breakout dedicated to that, and hopefully we'll also discuss it in the panel discussions. And the venues for new conferences, journals, I think there's activity happening here. And we've been looking at some of the problems related to these interface areas and some big challenges that industry and academia can address together. And I don't know how many, I think a lot of people feel the same way, that collectively, I don't think we are really unleashing our innovation potential in terms of industry and academia collaborating. It's not an easy problem, but we're not doing our best. So, testbed development, as I already mentioned, I'll just put in a plug for NSF programs, which are very relevant to this. So if you are interested in building it, there's MRI, Major Research Instrumentation Program. That's a little bit smaller, although it's fairly big too, which is January 1st to 22nd in 2019 is the deadline. And then the SIZE Research Infrastructure Program, the preliminary proposal on November 7th, and full proposal in January again. So don't forget the website. I'm just going to quickly go through some of the posts that I put in there we put in there over the time. So this was happening in January. They're like, a lot of progress made on fixed wireless access. And then, of course, big announcement that the next iPhones will be built in Wisconsin, Foxconn. So that was happening there, which is exciting. So fixed wireless is a big deal. There was another. This is a lot of interplay on that. And then Huawei and NTT had a major milestone in Japan. And then KT, showed some additional data distribution during the Olympics. And then FC proposed auction of the 28 gigahertz spectrum. This was the power announcement. One of them, Salt Lake City and NYC. New York City get the Cosmos and Powder, as I mentioned earlier. Then the fixed home, this is going from the outside to the inside. And then this is getting towards the consumer devices. And then the 5G NR standalone standard or specification has been approved. And so that was one of the things in June. And this is one of the slides from last time that I had put in Tucson, which was one of the articles that, what Alan Gatherer runs. And they're great. The titles are, makes you pissed off or mad or what's going on. And so this was one of the articles by John Cioffi and his team about DSL, the next generation of DSL. And I wanted to get John to come and talk in Tucson. That didn't happen, but we are very fortunate to have him here. Talk about these waveguide modes in DSL as a complement to the last mile. It's a great pleasure to have our first keynote speaker, Professor John Cioffi from Stanford, and also the CEO of ASEA Incorporated. And he doesn't need any introduction. He's got his undergrad from Illinois, great school, and then he went to Stanford, almost as good. And he did his PhD, got his PhD there, and then he went to, I think, IBM for a little bit, and then he started his career at Stanford as an assistant professor in '86, I think, or somewhere around there. And then he left in '91 to form Amati Corporation, where the DSL started. And it was acquired by, I think, TI in '98. And then that was not the end of it. In 2003, he formed ASEA Incorporated, I think, if I remember correctly, to kind of really move it DSL to the next level. And he's been involved in that ever since. And And he's got many, many awards, of course, and Marconi Award, Alexander Graham Bell Medal, and he's a member of the National Academy of Engineering. So without further ado, John, please take it away. Thank you for coming. Okay, sorry.
I'd like to make some projections about an area that we've thought about for a few years, but now trying to promote to get some measurements and other techniques about using the waveguide modes of a bundle of copper twisted pairs, as opposed to, of course, we all know that fiber is a waveguide, but there's nothing to prevent copper from being considered a waveguide as well. So this is actually a portion of that diagram that Akbar had up a few minutes ago. But what I attempt to do here is just graph the horizontal axis. You can see is distance. It gets shorter. And then speed on a logarithmic scale on the vertical axis. And there is this dashed line there that shows the speeds of DSLs increasing over the last 25, 30 years or so. And you can see that they get up to the range of, say, as fast as 10 gigabits per second. But the distance on the copper is shorter each time that this is attempted. So maybe not too big of a surprise using the methods. Now, this is a match to fiber penetrating into the network. Unfortunately, I changed the talk, but you can see that the copper color and the fiber color got reversed here. But the copper color is supposed to be the fiber, and the green is supposed to be the copper there. But the idea is it's getting shorter, but fiber doesn't necessarily go all the way to the premises. In fact, there's about 750 million fixed access connections around the world today. And over 500 million of them will have some level of the DSL connection at the end of the fiber. About another 150, 200 million are also copper, but they're cable connections, again with some fiber. And then the last 100 million or so are pure fiber all the way. It kind of gives you an idea, after 35, 40 years of trying to deploy fiber, it hasn't made it as fast as anyone has projected to everyone's home. Now what I'm going to talk about is a potential path to take that black curve and make a pretty big jump to the green curve here, improving the speeds by using higher order modes in a twisted pair. And if you're able to bond, say, 4 twisted pairs together collectively for a single data rate, as is, for instance, done with Ethernet, RJ45 connectors we're all familiar with. There are 4 twisted pairs in the cable that's used to connect. Of course, you get about 4 times the data rate for that. So it gives us an idea of what we're attempting to do, and it's about 100 to 1,000 times faster at the same length. And important here is this length concept of kind of pushing back a little bit. So why is that important? Well, let me oversimplify the business case that you'll see service providers, internet service providers around the world work on. The average cost across, let's say, an entire network or an entire country is about $3,000 a home. It is not less than that, no matter what anyone tells you. If you want to put fiber all the way to the home, that's the average cost. The recent numbers coming in from some of the countries that have tried to do this with massive government funding, it's larger than that number. And even at $3,000 a home, that's about 3 or 4 times off what a proper business case would make for a return on the investment. So if you're getting a customer paying $40, $50 a month for the service, you can't recover that kind of investment. So that's one of the reasons it's been slow, is it doesn't make money. There's nothing wrong with the fiber or the technology, and it's really more the infrastructure investment costs for digging up streets and so forth to deploy it. Now, fiber part of the way does make sense. And you can get down to about 10 times less, about $300 per home. And that does make sense at that level. It does make sense for the service provider to invest. And just as a side point, I'm going to continue on here. We see a lot about the holdup on 5G wireless being that the need for fiber to a much larger number, maybe 10 to 100 times more small cells than we have today. Could it be possible to use the existing infrastructure, namely copper-based, to address some of that more cost effectively and thereby accelerate the deployment of 5G systems? So let's talk about the 5G structure. Obviously, many and more cells, higher frequencies being used up into the millimeter wave band, 1 gigabits to 10 gigabits per second speeds being discussed, projected even in the new radio standard from the 3GPP group. It goes up to these types of speeds, especially in the millimeter wave bands that are now specified there. And we get into this area of front and back haul of 5G massive MIMO systems where you have to get a connection out to that cell tower. You could do it with fiber, but is it possible to do that in some cases with copper as well? And just to give you an example on this from Germany, the Deutsche Telekom CTO and CEO just about a year ago, this famous quote. Now some people argue with it, and I even saw someone in the audience who'll tell me that they were lying about this, but because they wanted to get a monopoly on infrastructure build costs, but they estimated 400 billion euros for just Europe to run fiber to all the small cell sites. Now even if that's off by a factor of 10, it's still too much. You could resolve the Greek debt and the Italian debt and the Spanish debt for those kinds of numbers if you were willing to spend that. So what can we do with the existing infrastructure is an important part of the business case. Another thing that's perhaps not as much realized today is we see a lot about virtualization of data centers and increasing the software-defined component of all of our telecommunications networks, whether that means putting a central office re-architected as a data center or just any old data center. One of the greatest needs, my understanding, for bandwidth inside the data center itself is all the software-defined programs themselves being moved from one place to another. So they increase the bandwidth requirements. And so inside your data centers as well, there is still a substantial portion of copper. This changes every 4 years or so. There are companies like Cisco who have entire teams that spend their time trying to decide how much copper, how much fiber as they move a data center over. If they move it all over to fiber, that creates some problems. They want to leverage the existing infrastructure. So being able to go faster in those situations can also have some flexibility advantages in terms of their budget and how they migrate the data center to higher speeds. So with that as kind of the higher level rationale, what I'm going to propose here is to combine a couple of techniques that are somewhat well known, maybe not completely known, but well enough known, together to try to use the waveguide modes of a binder of twisted pair copper wires. And the first area is the waveguide area itself. Particularly their effects that are sometimes called the plasmon polariton. Many of you here may know more about that than I do, but if you read about it, it's one of the modes of propagation that's of interest, that could be very much of interest inside a twisted pair binder. And then there's the so-called vectoring. This is the same as massive MIMO. In fact, there's a nice diagram, if you've seen the book from Marcus Walden, the CTO of Nokia, on these two techniques. Vectoring is actually already deployed on DSLs around the world, probably 50 to 100 million of them already, with hundreds of antennas. And the processing is very similar to what's used in MU-MIMO or massive MIMO systems. In fact, the diagram makes the point, and I agree with it, that they're identical. So we know a lot about that, but the idea is putting those two things together. And I'll describe a little bit more about that. But the orders of magnitude speed increase that we'll project here would be applicable in all the three applications that I just mentioned. And so this is going to allow some rethinking from infrastructure standpoint of where the money, the resources could go to actually build faster networks sooner. So let me first talk about the waveguide propagation modes. Let's oversimplify it here, but let's pretend we had this big cable of wires and I cut it with a knife, and I'm looking in from the side. And I've just shown 3 of the wires here. There, of course, there are many more than that, and the copper section is shown there. This time I got the color right in copper. And then there's some kind of plastic or insulator around the copper. And then there's also some air spaces that are in between the wires in the binder. And it's those air spaces and the blue part that are really more of interest from a waveguide standpoint. And what we might be able to do is by injecting energy, think of it as tiny transmitters, sub-millimeter wave here, so let's say 100 gigahertz and above, in terms of carrier frequencies or bands that are used, and see the propagation of these tiny wavelength modes through the binder. So we try to take advantage of the green areas and the blue, if you will, and the waves are guided here. So the current is not in the copper. That would be a disaster. It would just get slowed down, and there's no passage of energy as they're down at the lower frequencies, say below a few hundred megahertz in DSL use today. And so the copper is really used as a waveguide. And the wavelength is clearly going to have, if you look at the dimensions here shown on the board, shown on the slide, less than 0.5 millimeter, basically, for this to have a hope of the waves being able to fit into those spaces. Now, the twisting is going to, I like to call this a Swiss cheese. Some people don't like that term. But think of this, all these wires are twisting. The different pairs inside a binder actually twist at different rates. They do that intentionally in manufacturing the cables. That's what's there. So those green areas are going to intersect with one another. They're going to create a mess inside the cable as the waves propagate down the cable. There are going to be reflections off the wires back in different directions. There are many modes of possible propagation. In other words, many possible potential solutions to the Maxwell equations that define this. And it's a MIMO wireless channel here. But we have already seen that one before. And there are quite messy systems today that are very accurately resolved by vector signal processing, if you will, which has already been proven in use. So maybe the simplest example, and we're not actually suggesting using the surface wave itself, but this is just a simple example for a single wire, and it's something that's been measured to date in these frequency bands. So-called surface wave dates to 1909, Sommerfeld. Some of you may be familiar with that work. It was initially hailed and then insulted and then hailed again. It went through its gyrations in history. But the idea was that the wire kind of helps hold the wave close to it. So it's a little better than wireless by itself. And they thought of this as actually the surface of the Earth being the wire. That's why it's called surface mode, the energy flying across the surface. So these have been used in certain so-called G-lines for television antennas you may have seen in the past. Also, the AT&T AirGig effort tries to use a power line using surface wave modes. But these are definitely wireless transmission, but the wire helps. So you can have wireless. If you have wires, they don't hurt. Typically, they help. Now, there are some questions when you have the insulator. What does that do to the propagation around the wire? And in particular, you'll see a lot of work, especially for surface wave. If the wire is bent, the energy tends to wander off in the direction it was going, and so you have an attenuation effect that occurs. You have two twisted wires or split pair, it tends to hold it a little bit better, but there's still some drift when they're bent. So we're going to look at those modes and then apply some of the vectoring models that have been used successfully in the past to all of this. There are also TEM modes that are so-called plasma and polariton, which basically have to do with the charges in the copper itself supporting the wave. And some of these things have actually been measured. I give a couple of sets of measurements. The first here is from Wiltsey. He had a 2 millimeter diameter wire, it's a little bit fat for phone lines, but measured the 100 gigahertz and above band and came up with a certain amount of attenuation in dB per meter, attenuation coefficient. Okay, so it's not 0.5 millimeter, which is more typical of twisted pairs, but he got about 0.8 dB per meter in the 100 to 300 terahertz band, 100 to 300 gigahertz band. Another set of measurements that we used a little more heavily was set by Grishkowski, which comes up with about 0.5 dB per meter for a 0.52 millimeter diameter. It's a single wire. Second wire close to it presumably would improve that. But we basically, and this is a plot down here on the right-hand side. Basically, up is less on this, or worse, if you will. But you can see there are very significant regions above 100 gigahertz there, where transmission is feasible. Now, that would mean 100 meters should see about 50 to 80 dB attenuation. Sounds like a lot of attenuation. But for if you're in the DSL space, I have been for decades, that's not a lot. Okay, we know how to handle that. So that tries to at least give you some optimism that something might be feasible here. Bending of a wire is going to be less of a problem. We have multiple wires, mainly because there's going to be reflections between those wires. Now, normally you say, geez, that's a mess. Everything's interfering with everything else. But with modern MIMO techniques, that's not necessarily bad. In fact, that's a good thing. As long as the energy is not going away from the cable itself, it's being reflected back, typically it can be recovered and aligned if the transmitter and receiver signal processing are doing the right thing. So there could be up to 3 or 4 modes per twisted pair that could sustain data transmission in the cable. Now, how are you going to get in and off? I'm not an expert on this, but a simpler way conceptually is to use a femtosecond laser, have a photodetector at the other side, not necessarily touching the wire, which I've tried to illustrate here. It turns out that there are efforts. One of my colleagues at Stanford, Amin Arbabian, has been studying the area of CMOS circuits for 100 to 300 gigahertz, and this actually comes from one of his papers. This is for backplane interconnect systems, but nonetheless, with 3D printing, they're able to construct systems with lenses and so forth that can actually create data signals in this frequency range. Now let's extend that a little bit and say there's a vector processor. And there are many of these lenses exciting different modes, if you will, or you can think of it as just exciting the wires. I've kind of shown it in dotted lines here to remind you it's more of a wireless effect. And then there's going to be an array of sensors, if you will, on the other side. And so what we have is this matrix H, which describes this channel. There'll be multiple modes for each wire, TM, TEM, TIR, and so forth. It's a Swiss cheese waveguide, as I like to call it. And if you've heard the term, if many of you in the wireless area have background, rich scattering, this is ultra rich scattering, and that's usually a good thing for MIMO systems. Okay, let's talk a little bit about the signal processing. If you have a channel, sorry, a little bit of mathematics here. If you have a channel H like that, you can do what's called singular value decomposition of it. It's important for defining the transmitter and receiver. If you have a single user on the system, these turned out to be the optimum signal processing that would be used. It's a fairly well-known result. If you have single-sided systems where, like massive MIMO, you have all the antennas in one place, you may have all the transmitters in one place in a binder of twisted pairs downstream, but the receivers may be in different places, and there's a dual of that in the upstream direction where all the receivers are in the same place, but the transmitters are in a different place. And so you can do what are called QR factorizations, that same matrix H. And these help define what the optimum transmit receiver systems are. And you can easily then compute what the data rates achievable would be. So we took the Rishkowski model for the channel, and we fit that to the data that they reported. And then we fit the same model basically to the crosstalking path, because why should that be any different? But as is common in wireless, and it's also used in DSL systems, there's a log normal model used for the crosstalk between the wires. And in a log normal model, you need a mean and variance. So we set that at 0 dB on the mean, a variance be 6 dB. And then we extrapolated from that log normal model using well-known methods to do this, 20 dBm of transmit power. We actually use 4,096 carriers between 100 gigahertz and 300 gigahertz. Carrier spacing is just a little under 50 megahertz. Some of the other parameters here have to do with the codes and signal processing that were used. And we had a couple of modes per twisted pair. So it gives you an idea of the signal processing. And we did it for 50 pairs, which is not that unusual. Typical cables will have 50 pairs in them. It depends on the country you're in and the exact type of cable, but that's not unusual. And then we use the signal processing methods that derive for a matrix channel model to make projections. For these systems, we used a background noise, which we found to be reasonable. Thermal noise is minus 173 to give you a reference, so at room temperature. So here, 13 dB or so above that in terms of noise level we used. And we've got a couple of curves here, but the horizontal axis is length, and then there's data rate. That's in terabits, so it's not a typo there. on the vertical axis, and you can see at about 100 meters, 1 terabit per second on the so-called NLP. That means nonlinear precoder. And then we also did a linear precoder. Now, all the DSL systems, all the 5G, all the Wi-Fi today use linear precoders. It is not optimum for a MIMO system. And now, it turns out it's pretty close to optimum for a lot of the channels they're looking at, so nobody bothers with the nonlinear part. Here, we finally got a channel where there's a difference. So we saw that coming up, and you can see the difference in those curves suggests that the crosstalking is so bad, and it's such a mess, that you really do have to go to the nonlinear model. It's not that much more complicated, but it is a little more complex than the linear model. And would simply ask tongue-in-cheek here, can any PON today get to a terabit per second, really at any length for transmission? Now, the pushback from the service providers, and I've talked to many of them about this, is could you slow it down and go longer at lower speeds? This is actually harder to do with these waveguide modes, in my opinion, but to push the length up and lower the speed. And so here we did 100 gigabits and projected about 300 meters for that. And that wasn't slow enough, so then we went down to 10 gigabits. Now the lengths are getting longer, projected about 500 meters for that. I didn't bother to show the linear technique any further on that. And those are distances that can make a big difference on saving the money. I talked about fiber getting to about 500 meters is cost effective. Getting beyond that gets very difficult in terms of the business case. Now what we did was we actually increased the bandwidth, went up to 500 gigahertz. We noticed in Grishkowski's results, he wasn't completely sure of them, but we took it on faith, but what he did show on that, and added the extra modes in. And in fact, the speeds go up, more modes to be exploited, more MIMO processing, of course. 2 terabits per second was possible at 100 meters. This is sum of uplink and downlink, if you will, so figure 1 terabit symmetric. So that's where the name of the title, or the name of the talk came from, was Terabit DSL. Now, I got pushed actually by AT&T here in the United States. Said, look, you have to go longer. Despite what they say about fiber, most of their fiber connections today do have a DSL. Even the giga power systems have DSL at the end of them. And they have a massive amount of their network that goes out to 2,000 feet that they don't think they're ever going to be able to put on fiber. So they asked the question, what kind of data rate can you get at 2,000 feet? So we ran it. I'm most skeptical about this because the waveguides have a cutoff effect at a frequency below which you cannot transmit. We pushed that down to 50 gigahertz, which is about as far as we thought might be possible. And you definitely need to use those lower frequencies to get these longer lengths. But this was the projection that we did for them. Many of you may have heard of X-Haul or front haul on fiber today. Well, these kinds of methods could also be used for that. Just simply carry basically the raw bit stream from a D to A or A to D back and forth across an RF carrier to a central place where processing can be shared. So conceivably, these modes could be used for that as well. MIMO processing then being largely at the data center for that, or the edge processing center. Signal processing, let's look at this from the standpoint of the analog portions of it. In addition to having sensors, however they're constructed, 3D CMOS, photodetectors, lasers, or equivalents to that. Today, if you look at fiber optics, there is an 8-bit 65 gigahertz A to D converter that's used. It's about 750 milliwatts per conversion device for that today. And so you could actually see the processing power consumed for several of these that might be needed to cover the bandwidths that we're talking about in the few watts to 10 watt type range. So that is not that far away from being feasible on a massive scale. Vector processing capabilities. The vector engine we used with a 50 megahertz wide tone spacing, if you will, was about 5 gigaops per tone. Which would be 20 teraops today with 4,000 tones. But before we get too concerned with that, the processors that you can see today, the Tensor Silicon processor, the NVIDIA processors, are already well above these numbers. Okay, these are used in data centers for processing. And if we were to take it down to 100 gigabits, lower the bandwidth, would the cost and power come down by a factor 1/10? Probably. These signal processing tends to scale with the data rate and bandwidths used. And these numbers, from going back to the early stages of ADSL and VDSL, you would get, analog people stand up in a room and say it's physically impossible to have an A to D converter. Believe it or not, one of the wealthiest men in the world, I went to one of the standards meetings today, I won't give his name, he's embarrassing him, and said a 14-bit A to D converter at 2.2 megahertz, which was what's needed for ADSL, was against the laws of physics. Those are dime store commodities today, so I'm sure he wishes he had not said that at the time. So we should not necessarily be daunted by the fact that we're not quite there on the analog conversion devices, but we're not that far away. So what is needed to progress? Well, today, everything has been single excitation. What we'd really like to do is get a matrix characterization, and to start with shorter cables, perhaps. There's a stepper positioning of transmitter and receiver, excitation with some kind of periodic sequence, and then measuring from all the input points to all the possible output points. Thousands of measurements for a single cable would be necessary, store them on a disk, and then process that and evaluate the data rates, and then progress to longer cables. And then from that standpoint, we begin to investigate cost-effective or mass-producible couplers and signal processing for the whole area. So I know there's some interest at NSF, and there have been some proposals in, and my company certainly sponsors and supports one of those that I know is in right now, and we'd love to see the area take off and help us assess. So the conclusion is, I say it appears possible because we really haven't proven this yet, but based on the best that we know or know how to do today, and nobody's been able to tell me of anything better we could do other than measure it right now. This is kind of a pre-competitive area, and we need measurements and then the consequent calculations and projections to advance. Earlier focus, if you listen to the service providers, they want lower speeds at longer lengths. This is the exact opposite of what's easy to do in the lab first, which is actually higher speeds at shorter lengths. But nonetheless, that's where the initial application could be. And this may help as well the 5G and the data center problems I mentioned earlier. So needs funding and needs people, and if you're interested, feel free to talk to me. Happy to try to help you or route you to others who are interested as well. So thank you, and I'll just let me put up, I've got a slide here crediting some of the people who've been helpful on these results here.
John, is anybody still manufacturing this cable, or are you relying on just the old-fashioned things from 50 years ago that are still in place to millions of homes?
Well, both. I think it's more the latter has been the argument that I have made here, that it's there, it's existing infrastructure, and so the cost makes sense. If you had to replace a copper cable with something, you're probably going to choose fiber because the costs of digging up the street or whatever you have to do are going to be about the same for that. If you were to look, however, are there groups manufacturing, is there a copper industry today? Yes, and it's quite large, and there still is a large amount of copper cabling being constructed for a variety of different, you can go to the store and buy an RJ45 connector, and somebody had to make the copper for that. And some of those groups have actually talked to me about what they could actually do to make the cable better in the future, by not necessarily, maybe not twisting the pairs or doing other things inside the cable to make a better copper cable. I don't know if that makes sense to be pursuing here because of what we just said on the first point, but there are groups that actually manufacture the cables still today, and it's a pretty large industry still. Go ahead, Ted.
From your past experience in DSL, with cable interconnects, aging cable, the real world problems, transformers, what do you see as the biggest challenge that will limit the overall distance with, corrosion of metals and the connectors and all that kind of?
Of course, every service provider you talk to, there's a meeting. What about bridge taps and what about all these things? And I've tried to say, well, those have all been transcended in the past. And what is needed first is just straight run of copper. Maybe all the wires are going from the same place to the same place initially to be able to make projections. But the issues with bridge taps and spectrum management, crosstalk between the different systems and so forth have all been addressed previously. The nonlinear precoder that I saw is going to bring in a new stage. I think this is going to come in 5G wireless because of IoT anyway. You see it called NOMA. That's a new name for an old effect that many have seen before, but you share the dimensions rather than orthogonalizing all the users of the system. And then there's an order of the customers or users or the applications that you have to solve that problem. There are some solutions to that, but how's that done will be an interesting kind of communications problem that needs to get solved as well. Did that completely answer your question?
I was really wondering, when you go up to 50 gigahertz and above, the actual physics of metal interconnect and corrosion and water leaking into a cable, I think.
Oh, yeah, absolutely. All of those OB issues, but they've been transcended in other frequency ranges before.
Do it up there.
Yeah, I mean, I talked to, I don't have him here, I mentioned earlier, but I talked to Amin, he is up there at Stanford on this. And some of these issues do come up in the backplane interconnect areas and problems maybe not as profoundly as here, but if you could get 100 gigabits or terabits at these lengths, the Broadcoms and Qualcomms and major semiconductor groups who would be manufacturing or working on these things, there's enough money there that they'll solve these problems. I'm not so afraid of that as just getting the measurements to see what the actual cases would be. Go ahead, Stefano.
I would add that the propagation you're talking about are not differential modes in the copper where you would have the physics problems that is around.
Yeah, that may be true too.
It's alleviated. It's not the differential mode between copper and ground, but it's in the surface. A plasmon is light interacting with metal.
So I should mention one of the things that's come up, in fact, I saw Dan Middleman here earlier this morning. He raised this earlier when I first talked to him about his name's up here too, is the insulators and the effect that they may have in this range. But Stefano raised his hand, and I haven't seen the paper yet, but he says he's looked at this area and up to 500 gigahertz, at least on theoretical models. It appears like unless you've changed your results since I last talked to you, it looks like something, that we shouldn't let that prevent us from going ahead with the measurements.
The major effect of adding the insulator is that you have a cutoff, you have multiple modes. If you don't have the insulator, you have a fundamental mode propagating with no modes. So, and then cutoff frequencies, but in the order of some gigahertz, you have multiple modes, but then you process them.
So I'm waiting for him to get this cleared so I can read more about this, but it sounds very interesting. So,
I have a related, there's a question there.
Thanks for a really nice talk. So the key performance gain you're getting is with the nonlinear precoding, right? Do you think this is viable without that at all, or would you?
Well, it was a lot less. I mean, the numbers increase are so large that even if you're only at 1/10 of the numbers, it still makes sense to attempt to try to do this. The whole area of nonlinear precoders is controversial, both in wireline and wireless. It's a little harder. It reminds me of the days, believe it or not, the same kind of issue came up in the what are called VDOT 34 and the 56K modems, where they did eventually use nonlinear precoders. There are issues in coordination of transmitter and receiver that require exact down to the bit level precisional alignment between the two systems, where they wander off in different directions and cause an issue. Some of those things are being looked at, some of the ITU standards groups for these MIMO type systems. The gain has not been that great to merit the investigation and effort for that. I think we're beginning to cross the threshold in other applications as well, where these nonlinear precoders and the equivalent, I like to call it a generalized decision feedback equalizer in the receiver for uplink, will need to get addressed. And they've been addressed in the past, and I believe they can be addressed. But it adds another layer of coordination and standards between transmitter and receiver that has to be maintained in order to do that, and then it becomes very controversial because of different groups will have different patents on different techniques, which happened in the old modem days as well. There was a huge fight that went on for decades in that after just on the precoders themselves and how they were used. So you might see some of that. So I think it's been more politics, and so there isn't that large of a gain. People have not gone to the nonlinear precoders yet, but I think they will as the whole area advances.
The second question I had was about, so all of this is still simulation based on theoretical channel models, right?
Well, except for the single line measurements, the
So
parameters
what
for the
kind?
theoretical models came from those measurements, but otherwise
so what
correct.
kind of assumptions did you make on the rank of the channel and what kind of capacity?
We used a logarithmic model, so basically it's a random rank that occurs as you sample from that model, and then you average over all of. I have more data, but I didn't show it on the 99th percentile and the 1%, type thing, and the 50%. We're looking mainly at the averages here with these results.
The U.S. NASA is extremely protective of certain millimeter wave frequencies, for example, at 231 gigahertz resonance of ozone, and basically tries to veto any such use. There were huge controversies in the U.S. in the 70s on cable TV leakage into aeronautical bands, and in the year 2000 on broadband over power line leakage into HF bands. So one thing you might want to do as part of your early analysis is to understand not only what the leakage of a single wire might be, but if you were looking from on high down in a city that was filled with these things, to come up with some estimate of what the overall leakage it would be visible. Because when you go up, the propagation loss is relatively small, only about 200 dB.
Well,
sideways, propagation loss is huge.
These issues have come up in all of the wireline areas about the emissions requirement. Now, presumably, one of the problems we were trying to address was the drifting of energy away from the wires, and that tends to spread, and the levels that I've seen are fairly small, so I would hope the various groups.
You have no idea how protected it is.
So yeah, we don't want a space shuttle homing in on a phone line with this, so that we'd have a problem with it. But yeah.
The issue is passive sensors
Yes.
of environmental resonances, and NASA, shall we say, verges on the irrational in its protection of these things.
So no, I have had no contact from NASA, and it's a good point, and I'm happy to speak to anyone who might know more about that.
So it seems like you're sort of a parallel with some of the fiber communications. You mentioned waveguide modes and things like that. Is there any issue with the modulation type that you have to use? Like in the fiber, they use wavelength division multiplexing and primarily focus on the simple amplitude type modulation schemes, or do you think that
We
you'd be able
used
to cover
coherent. We
both?
presumed coherent here and on all the carriers, but there were standard types of constellations, 4 QAM, 16 QAM, and so forth. It turns out that the bit densities that I didn't have a plot on it here, but I have looked at it. They're not as high, especially if you're talking about 100 gigabits per second or some of the push for the lower speeds. We're talking only a few bits per hertz or less for these systems. So the 8-bit converters I was talking about would be well within range for use and would support that. I think the signal processing is there. The main issues would be just getting that converted at these speeds and into a processor to take advantage of that.
Okay, I think we got to cut off time now about the frequency. So some of the rest of the questions will have to be offline. Thank you very much.
I'll be around today, so happy to take them up. Thank you.
All right, so maybe I'll just go in the order of here. So Ted Rappaport is the founding director, or the messiah of millimeter wave. So maybe I'll just ask him quickly, to each of the panelists, to talk a little bit about what their organization is doing, and particularly their involvement in industry. So Ted?
Okay, I'm at NYU Wireless with my colleague Sandeep. As you know, in 2011 and 2012, we did the pioneering measurements that proved to the world that millimeter wave would not only work, but actually, as you'll see in my keynote tomorrow, works better than any other generation of cellular we've ever had, which kind of busts a bunch of myths about going up higher in frequencies. We've done channel modeling, we've done network access, we've looked at all kinds of things with 12 faculty and about 100 grad students here. And Sandeep, thank you, and Akbar, thank you for bringing the millimeter wave community here to NYU. We're really glad to have you and hope you have a great couple of days here.
I just also want to say Ted has worked extensively with industry, so we'll have a unique perspective. We've worked with many of the companies that have been founding in the millimeter wave space, and we'll have an interesting perspective for this panel. So Özge is actually, I think, maybe senior director, is that right? Yes, at Qualcomm. He's been heading the entire millimeter wave effort when it was in its infancy in Qualcomm, so you're getting it firsthand from him.
Hi, my name is Özge Koyman. I work out of the New Jersey office in Qualcomm. I'm part of Qualcomm Research, so I'm not on the product side, but we interface closely with the product team. So we've been looking at millimeter wave for a number of years now, started in wireless backhaul, then started looking at the access part of it. Worked with Ted and others on the channel measurements, channel modeling, proving it out, and then really went full into it. And you know, our focus really is to make this work in a UE handset. So it's not really a fixed wireless type of application, although we do look at that as well, but it's really in a UE handset, and that's what we've been trying to prove for the last couple of years, show that it is feasible, and we'll be heading to commercialization pretty soon, so that everyone here can also see that it works in a handset.
All right, next up is Harish Krishnaswamy. Anyone who's familiar with the millimeter wave as a circuit design knows a lot of his work out from Columbia. But I also wanted him to come onto the panel because he's involved in a very exciting startup and give his perspective from a small company in the field.
Thanks, Sandeep, and thanks to Sandeep and Akbar for organizing this. So my name is Harish Krishnaswamy. I'm an associate professor at Columbia University in the Electrical Engineering Department. I've been at Columbia for close to 10 years now. My group there works on RF and millimeter wave IC design. We try to innovate at the IC design level in the circuits for new forms of wireless communication in general. So we've looked at things like full duplex, massive MIMO, and of course millimeter wave. In fact, my history with millimeter wave goes back actually to the days of my PhD, starting in 2003. In the mid-2000s, actually, a lot of the fundamental circuits work in millimeter wave was done back then. We were looking at, can you push to higher frequencies? Can you build a multiple antenna system, phased arrays on a single chip? And at that time, the big excitement was around the 60 gigahertz unlicensed band that later came to be known as WiGig. But around 2009, 2010, that didn't really take off. And then in the early 2010s, as Ted pointed out, because of a lot of pioneering work that happened, of course, from NYU Wireless and other places, there's a lot of excitement now around cellular communications at millimeter wave and the so-called 5G. And so we've been looking at circuit innovations for that as well. As Sandeep pointed out, we recently spun out a startup company that is looking to commercialize some of this RFIC work, as well as incorporating some system concepts. So, happy to speak about that.
All right, and finally, Tommy Svensson, come from Chalmers University all the way from Sweden. He actually has a one-slide visual, if that helps.
Thank you for inviting me. So, I have a background I'm leading wired systems research at Chalmers, and a background also a little bit at Ericsson. I worked employed 11.5 years. I worked 2.5 there. I did my PhD on code modulation back in the end of the I finished 2003. And then we worked on micro radio links up to 37 gigahertz. We had a project 2009 to 11 with Ericsson and a couple of companies where I worked on advanced micro radio links. And we started an online site millimeter wave backhaul links project in 2011. We worked half a year on it, and actually we lost the funding, 600,000 euro, because the German funding is a bailout. Anyhow, we tried to start it there, but then I worked on millimeter wave communications in the big EU projects from 2015 to 17. So this picture is from there, a project we called Millimeter Magic, where we worked on waveforms, frame structures, cooperative hybrid beamforming, and a couple of things. So with this slide, I want to illustrate what we are continuing doing at Chalmers. We have a research center called JSON, and 5 projects related to high-frequency communication, or high-frequency techniques for sensing communication. And I'm leading a project called Mantua. This picture illustrates a little bit that the scope we have. Actually, it's a PowerPoint, so can you step forward a little bit? I have some text coming up.
Oh, yeah.
So we have 4 web packages. We try to work a little bit academical here from fundamental, understanding what key performance metrics should we actually have to analyze from a communication theory point of view, taking all the way down to hardware and up to use cases, because I think we maybe should rethink a little bit. And then we work on different kind of architecture, how we should use the bits, where we should do the processing, and how many bits we should have in front-haul, backhaul situations. And we work on different cooperation techniques for access, and also with joint wireless access backhaul. Because in Europe, 56% of the links are wireless backhaul. And I see a convergence here. I think we should jointly design it. And then we also have some demo activities. We have testbed at 30 gigahertz called MATE, Massive MIMO Millimeter Wave.
Okay, great. And one of the other things I wanted to get Tommy to talk about here is they have a sort of slightly different model for the industry university partnerships in Europe, where there's a very close partnership on very large projects, and we can hopefully that can come up into discussion. So Akbar started this session today with a kind of a quick history of what's happened in millimeter wave in the last few years, and it's been really dramatic. If you look back just in the last 5 years, you've seen a huge amount of progress. The FCC has opened up a large number of bands. You've seen a number of trials, and I wanted to start off with the panelist. You know, what have we learned from these trials? Ted wrote a very famous paper, millimeter wave, it will work. So is it working? What are the challenges? What are the research? And if any one of you want to start with, take a stab at that. Ted, maybe you're the one who wrote the paper, it will work. Were you proven wrong, proven right?
Yeah, well, what you're seeing in the popular press...
Is that coming on? Is that sound coming on?
Yeah,
okay,
it's on.
Okay.
The carriers are all reporting better than expected results. If you've noticed, and if you have personal talks with the people leading them, they're kind of shocked. In fact, we saw that at the Brooklyn 5G Summit. It's video recorded on IEEE, where we had Qualcomm and Intel both presenting their first generation chips at 28 gigahertz and marveling at how much better it works than they ever expected. So yeah, it not only works, it works better. There's more bandwidth. And as long as the distances are kept relatively short, that is less than a few kilometers, the weather impairments really don't affect the channel severely, such that the data rates are beyond anything anyone's ever seen in wireless. So it not only works, it works better than what industry thought, which is good news because it kind of opens up the minds of the general engineering community to realize that if you look at fundamental physics and try to apply things, you saw Dr. Cioffi's talk, the Sommerfeld equation, 1909. Millimeter wave was developed by Bose and others in Russia in 1890s. Finally, 100 years later plus, we're seeing that it can change the world. So, yeah, I think it's working better, but we should ask Ozge that question because he's making the chips, and hopefully we'll have them in handsets by Christmas. That's my prediction.
Yeah, so it does work better than we expected, actually, because it was 4 years ago when we started this project, we really had doubts, so that's why we started doing the channel measurements and working with NYU, and then quickly we realized after we built our prototype that it does work a lot better than we expected. So we weren't involved in any of these trials because these trials are really focused on fixed wireless, so our testing was really more internal. We do have UE handset form factor devices and prototypes that we've been testing, and I can say that many people that do visit the New Jersey office, and we show them the indoor enterprise use case, for instance, and how it can work and how you can hold the device and try to hand block it and see the effects of it. Everyone that comes in, the operators or anyone that has disbelief in the beginning, and they just don't think it's going to work. And then we show them that it penetrates walls, it penetrates 30,000 square foot office, no problem. And we give them a challenge to try to block it, hold the device, try to block kill the signal, and it's not that straightforward. And actually, many people are surprised. So now, but that disbelief still exists. So there are many operators in the world and many companies in the world that still believe that it doesn't work. That still believe that it's not going to be, it's going to be a failure, and due to the small propagation distances and density required, and all that is really will all those questions will be answered in the next 6 months or so, and as we start commercializing it, and we have massive trials starting at the end of the year with hundreds of handsets and wide area urban environments, and then the commercial handsets come first half of next year. that's when really we have to prove to the world that it does work. Until you have the massive deployments and the massive trials, people still have a doubt. They think that things are engineered and they're presented in a way that it makes it look good. But we do have hope that we'll convince the world soon.
Actually, I just want to follow up on one of the things that you said. Is there a disconnect between where the vendors like Qualcomm are and the operators like Verizon? They seem that the operators still doing trials focusing on fixed wireless. Is there a lack of a compelling business case to go to mobility, or are they worried about the technical challenges with mobility? I know AT&T has claimed that they're also going to do a mobile trial, which is one step beyond what Verizon is doing, although I'm not fully sure if that's the case. So what are the vendors really the ones that are pushing the mobile part of this, but the operators are still at the fixed wireless stage? If any one of you want to try to take a stab, or go ahead.
Okay, I can yes. Yeah, so it really depends on the region and the operator and which vendors are working with the operator, because some vendors don't believe in millimeter wave in a mobile use case as much as others. These are on the infra side. And on the handset side, we've been pushing it, and there are operators like AT&T and Verizon that see both. They see a fixed wireless and a mobile use case, and we're working with a bunch of handset vendors that majority of them do think it's feasible to put in a phone, and they are putting in a phone, but there are still some that have doubts, and maybe we'll wait for the next generation of it. But it really depends on the region. European operators in general don't see the mobile use case for millimeter wave, at least in the beginning.
Okay.
They're really more focused on the fixed wireless. And they've concluded that they're really, even for fixed wireless in many places, that there's no business case for it, that there's no need for it, there's no capacity need for it. So it's really the Asian and the North American operators that are the more aggressive, and they see the capacity crunch, and they see that this could really solve offload some of the data, that are really more interested in the handset mobile use case.
Yeah, in particular, I'd say KT, Freetel in Korea, and Samsung's a big driver for the mobile case immediately. And in China, that's where you see a big belief. Japan as well, NTT Docomo's coming along, but you really see Asia on the mobility. That's where mobility will happen first, I believe, and it'll happen within the next 12 months. You'll see mobile handsets and deployments of 5G mobile. But in the U.S., the landmass is so much greater, and the fiber build-out is tougher, as we saw, getting terabits to the last base station. So in America, it'll be a little slower because they want to prove the technology, and they need time to get the massive fiber backbone. I think that's what the T-Mobile Sprint merger is all about, getting spectrum and getting enough fiber to be able to ramp quickly when you want to go.
Just want to echo, what's been said here in terms of what we as a startup company are hearing. I think both in the Europe and the U.S. we hear that. So depending upon who you talk to, either we hear that there is a lack of a good business case for the mobile use case, or that if it comes, it will come later, and fixed wireless access will be what will come first. I think certainly Asia is the most bullish on mobile access. I think the other thing that we've been looking into is there a business case for a hardware vendor into fixed wireless access, basically? In other words, if you look at CPE equipment and access points for the fixed wireless access, are there enough volumes to justify a custom hardware build out? And I think even that is a little unclear at this point. I think the amount of market penetration, historically infrastructure has been a more challenging space for custom hardware development compared to cellular, and the amount of market penetration that's projected over the next couple of years in the fixed wireless access, depending upon who you talk to, may or may not be sufficiently robust. So I think there are certainly business case questions even around fixed wireless access.
Is part of the difference that's coming between Europe and Asia and Europe and the U.S. The fiber penetration? I know that was always a huge issue with the small cells, and of course millimeter wave is a small cell, or is it just that in Asia there's just a lot of, let's say, close relation between the vendors and the regulatory governments that actually, basically pushing it aggressively? Tommy or anyone else, if you wanted to say something on any of the questions.
Yes, I cannot talk from company point of view since I'm at the university. But in Sweden, I can start there. Fixed wireless access, I think maybe it's not so important case because we have a lot of dict fiber. Although I think non-line of sight wireless backhauling should be an important case, and this flexibility with in-band backhauling, so you can start building out the small hotspots. Then where these hotspots should be. Personally, I believe in maybe professional situations, automation situations, where you can have a business case with a vertical industry. Maybe I could imagine that could be where an operator can start earning money on millimeter wave. Then there seems to be a little bit split focus or a split view on the use at mobile cases. We have a big EU project now work on connected vehicles called 5D car. Inside there, I see different views on it. Personally, I believe in millimeter wave is very useful for vehicles, and we can create better receivers. And we quite often have street canyons with more or less line of sight. Personally, I believe in that there's a good case there, but I also hear others being skeptical. So for Asia, I just remember when everyone said, okay, in Asia they're building fiber, I don't need any wireless backhaul. That was some time ago. But and they're easy to tear down houses and can build more fiber. That's not the case anymore. I think maybe 10 years ago we were rolling out 4G, that was the case. There seems to be interest in wireless for backhaul also there. And there's more friction to dig fiber. So I don't have a hands-on knowledge, but I just remember those comments some years ago.
Okay, great. I think we have a question here from the audience. You want to introduce yourself?
Sure. Dave Burstein. I write about this stuff. In fact, I just did 6,000 words on why almost nobody except Verizon in the West believes millimeter wave is going to happen soon, and I hope you'll prove them wrong. One of the answers that I haven't been able to find, and get lots of different opinions, is whether it's going to be practical to backhaul a millimeter wave small cell, which needs 5, 10, maybe more gigabits backhaul using wireless. What are you finding out? Verizon says they must have fiber, but it sounds like you think that you may be able to do it wirelessly.
I think Tommy had mentioned that there were like 56% of cell sites in Europe are already wireless backhaul. But
I remember my last application, that was 6 years ago, I think it was 54, 56%, we had some reference. That might have changed a bit, but in that ballpark.
That's a bit or less.
Yeah, for millimeter wave cells, if the cell sites were to increase, orders of magnitude with the millimeter wave with backhaul.
Then I think it needs to increase. Personally, I also believe in, because we are working a little bit on hybrid fiber wireless, because I see maybe a migration path there. If you start to build out some millimeter wave access hotspots, maybe the business case is fully solid, so you maybe gradually want to add fiber.
Did you want to, Ted?
Yeah, fundamentally, there should not be a problem to provide high bandwidth, 10 gigabit per second plus wireless backhaul between small cells if the spectrum allocation is there. It's a very clean channel. There's high directional antennas that can be made in a small footprint. So physically, it is possible to be using small cell base stations for both mobile as well as providing backhaul from others, say several others. In fact, that's how I believe the networks will evolve. Small cells in an urban or suburban area will indeed have multiple antennas that can simultaneously steer to the mobiles while they, at the same time, have a dedicated steerable antenna linking the other base stations together. The key is having enough RF spectrum bandwidth. And the 28 and 39 gigahertz spectrum alone is not going to be enough to do that. So there's a lot of interest in terms of the carriers getting the FCC to release some of the spectrum up higher, 70 gigahertz and above. When you start getting these 5 gigahertz channel bandwidths, you'll be able to do amazing backhaul, fiber-like backhaul speeds at the same time you're supplying mobile.
By the way, I was really happy that Professor Cioffi opened this whole today's session with a great talk on the terabit copper. That was a fantastic talk, and maybe that'll also be a solution to small cells. That's always, if you've been in this space, you know that bandwidth to small cells have been always a key problem. Okay, did you want to say something?
Yeah, so the backhaul part of it, so the fiber does exist in many of the base stations in Asia, so in cities like Seoul and Tokyo. In the U.S., it is a problem. So backhaul, you can certainly reach the multi-gigabit per second. It's really just what technology do you use. I mean, there are existing proprietary solutions now, which you can use, but the way we're pushing it is to eventually have the integrated access backhaul, which is being standardized in 3GPP right now, and that's something that we as Qualcomm are pushing with AT&T, because we see the importance of it, and we see the importance of having backhaul and access share the same spectrum and dynamically allocate resources and have it be standardized so that we're not tied to a proprietary solution. So it's something that operators want, and it's really when that is standardized in Release 16 that maybe you'll see more deployments in a mass scale.
I think Kate, you had a question.
Yeah, Kate Remley from NIST. Getting back to the mobility and the handsets, I guess I had been under the impression that one of the big impediments to deployment of handsets was the power consumption issue up at millimeter wave frequencies. And so it sounds like maybe there's been a breakthrough there. Are the handsets that you're talking about that are imminent, will they include the beamforming and the tracking of the base station and those kind of things? Thanks.
Yes. So they'll have multiple 28 gigahertz or 39 gigahertz RFICs with, what's feasible right now is just four antenna elements in each location. So it's a beamforming with a phase array, four antenna elements. So power consumption, it has gone, it's much lower than we initially thought, but it's still, I'm not going to say it's very low. It's still an issue, and just like the first generation of 3G phones or 4G phones, the power consumption might be a little bit higher than we want. But then the next generation of phones will bring it down further and further.
I want to let Harish chime in on this whole power consumption issue, and then to Manisha. But on the power consumption issue, is there when I was looking at papers, and then maybe the status has changed, and looking at what industry was producing, there seemed to be a big discrepancy between what's reported in the top conferences in terms of power efficiency, and then what people were actually practically obtaining in terms of power numbers. And the power consumption, I'm glad, Kate, you brought that up, because it's been such a key issue as we're kind of moving past the functional phase of 3GPP. Do you want to?
Yeah, absolutely. So, I think when you look at what the numbers that industry has in mind versus what's in papers, as you said, there's definitely a discrepancy. And I think the discrepancy comes from both directions. So on one side, obviously academic papers are going to be extremely aggressive in what they report as power consumption in various building blocks. You can easily report a very aggressive power consumption if you ignore several of the practicalities of what it takes to build a circuit that actually goes into a chip. A classic example is an analog to digital converter. The buffer that drives that converter and scales the voltage to full scale can often be the most power hungry thing in the analog to digital converter. But if you just test it with a signal generator that forces that signal in there, you can just take that power consumption out, report extremely low numbers. Also, the clock of a very high speed analog to digital converter can often be the most power hungry thing. If you play tricks with how you provide the clock, you can also report really low power consumption numbers. So certainly academic papers, we need to apply an academic correction factor in basically the power consumption. But also, I would say definitely, because this is early days in millimeter wave, I think what you will find that's happening in industry is some of the more basic and robust circuits being employed, and I think there is certainly room for innovation in improving the performance of the circuits that would be used in actual deployment. So there is basically a way for both sides to kind of come closer together. on this topic of power consumption in the UE, I think there's certainly improvements to be had, as Ozge mentioned. I think also we will hit some fundamental limits, though, in terms of power consumption. Power amplifiers at peak, a vanilla power amplifier would have an efficiency of around 20%, and under average, under modulation, maybe the average efficiency is less than 10% now, or early 10s at best. I think there's probably maybe a factor of 2 to be had there with power amplifier innovation through better power amplifiers, through linearization techniques, but it isn't going to go up 5x, right? You can never exceed 100% in efficiency. So I don't think there's 10 dBs to be had in power consumption, and so I think it's an issue both in terms of battery draw as well as thermal considerations in the phone. I think the way that we should be looking to make this work is to make the link even more asymmetric than it is, reduce the number of elements in the UE as much as you can through base station designs that have that get closer to the EIRP limits that the FCC allows you. So I would say, is it possible to do something with, just a 2-element array, for instance? I don't know that the directionality of the array is as critical as the power combining, but if you get benefits on the small cell side, can you actually relax the requirement in the UE? I think that's the way to make believers out of.
So kind of a massive MIMO you're proposing, really, that sort of topology in a way.
Even more elements on the small cell side, get more beamforming gains. The flip side of that, what people will ask is, well, what about the uplink, right? That helps the downlink. That doesn't really help the uplink if basically the UE is hobbling on 2 elements. I think at least initially, traffic is unidirectional these days. There's definitely a lot of interest in things like millimeter wave for supplemental downlink versus uplink. So I think that is, a viable way forward.
Manisha, before, I just want to let Manisha get a question in before.
Before you go, Manisha, I just want to follow on. I think Harsh is exactly right. I think this is a really important point that the industry's not talking about. That the ability to put very high directionality in a very small form factor at the base station is going to be the key to success, because we're going to need that base station to do a whole lot, because with only 4 or 8 elements in the handset, there's not going to be tremendous uplink margin, so we're going to have to hear much better. And so this great directionality at the small cell base station is not only going to make the mobile link on the reverse link or the uplink, but it's also going to give the ability to steer and look at other base stations for this backhaul. I just wanted to amplify that point because it's a really important one. Now, Monisha.
Thanks. Monisha Ghosh from NSF. So actually, before I ask my question, I just wanted to follow up on the power consumption thing. It's also an issue at the base station. The numbers I've heard about how much, because of the nonlinearity of the OFDM waveform, and the backoff that you have to do, the amount of power these base stations are going to end up using is enormous. So aside from that, I wanted to pick up something that you mentioned, and I'll play a little bit of devil's advocate here. You mentioned that you started working on millimeter wave when WiGig was hot. That did not take off, and so you switched to cellular. So what exactly makes, if you look at all the projections of where the high data rate is being used, it's indoors, and WiGig should have addressed that market. So what is the rationale behind saying that we did not succeed in WiGig, it's going to succeed in cellular?
Good question. Anyone want to take that tough one?
So I can attempt to answer that. I think there might be other people on this panel who are also, Qualcomm, for instance, heavily invested in both technologies, can talk about how they view WiGig versus cellular. With regard to my point, I don't think WiGig didn't make it for a technical reason. I think WiGig didn't make it because it was a little early. There wasn't a good market need at the time. I think if you look at some of the first startup companies, so SciBeam was a startup company that started in 2003 when I was starting my PhD out of Berkeley. If you think about that, something like 15 years too early, right? And I think they were coming out with their first product in 2009 with essentially a 60 gigahertz. At that time, it was a different standard. It was called wireless HD, and they were coming out with those chips to be embedded in smart TVs. 2009 was not a good time to be coming out with a product that added $500 to your smart TV. So I think there was a little bit of a timing issue. I think also the applications hadn't matured at that time. if we look at what we think is going to require gigabits per second data rate now, I mean, really, if you want to have gigabits per second, it needs to be 4K video or above. So it needs to be really high definition video, and it needs to be an application where latency matters so that you cannot compress that video, right? So even streaming video, it can be compressed and basically sent over low frequency Wi-Fi today. So we really need applications which are ultra low latency, but also extremely high data rate, things like VR and AR. And I think, you know, the 2000s was not a time where essentially those types of applications had matured. So I don't think WiGig didn't make it on a from a technical standpoint so much as just being a little early. But I really should let Ozge comment on how his team versus the Velocity team within Qualcomm sees their individual roles.
Yeah, so timing is a really big part of it. You know, right now we actually are seeing more traction on in WiGig now because. Especially with VR headsets. You know, that is one application where latency matters and high data rates matter quite a bit. And so that seems to be probably the best use case for it. There really wasn't a use case for a handset or for a laptop too much. You know, there were some projectors, I think that's wireless projectors that came out. But the problem that the difference between the WiGig and the licensed 3GPP really becomes also what you can support. You know, WiGig is really just focused on a point-to-point link in room, high data rate, but you don't really get, given their power targets and the ERP targets, and you don't really get penetration out of the room. You know, and given that it's really intended to be a point-to-point, and each side is trained individually, it doesn't really scale in a mass environment. So there's, unlike in license where you actually broadcast your directional signals and all the UEs trained to it en masse, in WiGig it's really just a point-to-point type of thing. So it's very hard to scale it. So when you start deploying in bigger environments like convention centers, indoor stadium, then that's really not really well suited for WiGig. So it was really probably timing and also just a very narrow focus on what they really wanted to achieve that didn't allow it to take off.
I'm Jinfeng Du from Nokia Bell Labs. So the challenge you mentioned for the WiGig is not air interface. It's more mic issue, which could be addressed quicker since the hardware, if hardware is already there. So why not address the mic problem rather than develop a new set of air interface?
Well, I mean, at this point, both are ready, right? We have chipsets for both. So there's no need to go back and try to fix that. But the other problem with that is that they're just given their target of 2 gigahertz channels, and now they have channel bonding, and it's not really intended for long distance coverage and more. The use case is just not there. It's really just intended for in-room point-to-point type of links. So it's a lot bigger effort to take that and make it a more of an access type of system.
Yes, I just want to kind of amplify a point. 2 gigahertz channel bandwidths. I think some of the I don't want to say mistakes, but some of the challenges that one sees with WiGig is, 2 gigahertz is a fairly wide bandwidth. Often you don't have the signal-to-noise ratio to basically fill that bandwidth with, a high constellation. I think the standard would have done better to have a scalable bandwidth that allows you to back off to like 1 gigahertz, 500 megahertz, and those kinds of bandwidths based on the available signal-to-noise ratio that you have. So I think that would have been something that would have helped with the robustness of WiGig. My other perception with the use cases of WiGig that people were looking at in the mid-2000s is being completely indoor, you're really limited by the pipe that comes into your house, right? So if you're suddenly able to do multiple gigabits per second, if you don't have a multi-gigabits per second pipe coming into the house, then you're really limited to use cases where the source of the data and the sink of the data is inside that house. And those are starting to be, it's hard to come up with those, I think, VR and AR. That's why I think the traction that you alluded to WiGig getting right now is either AR, VR, or now suddenly outdoor applications such as the Facebook Telegraph project that Qualcomm is working on.
We had a couple of questions, one from Akbar, and then I'll get Damar one.
Okay, so before we left power efficiency, I wanted to ask, Ted mentioned, hey, we need to go to higher frequencies. And so one question is that how would these power efficiency issues that Harish and Ozge alluded to would scale as we go to higher frequencies? And the second one is someone mentioned, Harish or somebody, latency. App use cases. So millisecond latency was one of the things. How far are we? Can we even achieve it in any use case? And I want to hear something on latency.
I can comment because I had a couple comments I want to do on the energy efficiency or power efficiency. I think we need to split the word a little bit also. Are we hardware limited? Are we energy heat limited? Are we EIRP regulation limited? And there are different solutions on the network level for that. I really believe we should do as bursty communication as we can, so we can have sleep modes when we don't have a very heavy pipe like a stream virtual reality. And then why not have some crazy academic ideas for the uplink? Virtual antenna arrays. Try to cooperate as often as we can and use some out-on-band links or resources for share the data, so we can get access to more antennas and get better beamforming gains. Then I have a comment related to how it scales. I know because we are working on Terahat's, it's called a FET flagship initiative in Europe now. I'm part of that. And we also have a lot of the people at Charles working on Terahat's components. And the heat management is the key problem from our perspective. So it's not scaling well. If you cannot have hydrogen or helium cooling.
This isn't a handset device or a
this is general chips try to create.
Oh, just even the chip itself?
Yes, to make many, for example, many RF chains. Because it's hard to get enough power from one chip. So if we could get massive parallel chips, but then the heat is one of the key challenges.
Let me say,
go ahead, sure. But then we'll try. Go ahead.
I'll be very quick about this. I just want to say something about the power efficiency that Akbar was talking about. So, for a given technology, a flavor of CMOS or a flavor of any other semiconductor technology, the rough rule of thumb is that output power and efficiency scale as 1/f. So if you go 10 times higher in frequency, both of them go down by roughly a factor of 10. But simultaneous with that, technology is getting better, right? We're getting newer generations of the semiconductor process. People are making improvements for millimeter wave. So I think just as Ted and Ozge talked about at the system level in terms of propagation and robustness, people are surprised by what they're able to achieve at millimeter wave. I think also we're seeing some surprising results from the efficiency of circuits, specifically power amplifiers. It's possible to get peak efficiencies of around 40%, average efficiencies around 20%. That's not so far off from what you can get at RF, certainly not an order of magnitude. That's point number one. I think point number two, I want to allude to something that Monisha was talking about, which is the OFDM waveform and nonlinearities. I think actually the biggest gains in efficiency to be had at this point are to get system people to talk to RF people more. So as an RF designer, I can tell you that after working with system designers within the startup, I now understand how horrendously underspec we make all our RF circuits. So we really assume the most stringent requirements at every single block in the chain, and then we proceed forward. And at the end of the day, you have an end-to-end system that is far more rigidly constrained than what you would need. So, for instance, my perceptions of the amount of backoff that you need for an OFDM waveform were at least 3 dB more than what you actually need. I'd say the standards have also been more generous towards 28 gigahertz systems than for the sub 6 gigahertz cellular, which is nice, right? We all need a little help. So I think bringing the systems folks closer to the RF folks are probably actually where the biggest delta is to be had in efficiency these days.
Okay, I think Marwan, and you want to just quickly introduce yourself and then.
Yeah, Marwan Kronos, University of Arizona. So going back to the issue of beamforming and the number of antenna elements that we can afford at the mobile and so on. So my question is related to this hybrid analog/digital beamforming, and since it's just been, at least in academic circles, it's being discussed extensively. How practical is this for indoor, and more critically, what are the implications in terms of power consumptions, if any? This is more on the signal processing side. Is this of a concern? Do we expect to see some form of hybridization to take place in indoor environment?
Yes, I'll talk about that tomorrow morning when I give my talk. But it's both very practical and will happen, not just indoor, but outdoor. And what we've seen is that you don't need all these very, very complex joint coordination of multiple base stations. That is kind of the ultimate in comp to achieve near optimal capacity. That is, as long as you do a little coordination and smart hybrid beamforming at each individual base station with a minimal of passing of information, you can do tremendously well. People are working at it in the companies. You'll see chipsets probably in 18 months that are implementing this, I believe. So it's very feasible, and actually hybrid beamforming makes so much sense because to go full digital with 16 channels or 8 channels is very expensive on the power side, but you can do so much less power consumption in a hybrid approach and achieve within a few % of what you would get in a digital. So yeah, that's going to happen. I want to get back to the question Akbar asked about latency, and something that I think is a really nice rule of thumb to just remember in this era. I call it the massively broadband era that we're now in, and I think we're here now for the next, for the rest of time. In this massively broadband era, radio waves travel 1 foot per nanosecond, and so to go 1,000 feet is a microsecond, and you do 1,000 bits at 1,000 feet, you're now at a millisecond. So a good way to think of 1 millisecond latency is 1,000 bits over 1,000 feet. And so if you have minimal or processing time of epsilon, we're talking about 800 to 1,000 bits in a millisecond. So any packaging of data in whatever bandwidth you have, whether you have a bunch of narrowband parallel channels or a broadband channel, really can meet that 1 millisecond latency. And so that's why you see the 5G standard in 3GPP having roughly 1,000 bits per transmission. So we're getting there, and it's just a question of the physical channel and where you're sending the information to. The biggest problem is the back end, where you're going to cache the data. And that's where I think there's very exciting work going on, and where you're going to see very interesting business combinations between Facebook and Amazon and AT&T and Verizon and the people that know how to cache data that's accessed at the back end. I think that's a very exciting part of the future of telecom.
Tommy wanted to chime in, and then we'll get it over to Stefano after that.
Just a small comment on, because of one key use case people talk about low latency is connected vehicles for maybe dynamic maps and mobile edge computing. And it's easy to be naive coming from telecom and go to another industry because it's a very complex vehicle. They have a lot of security service. So it takes seconds actually to reach their destination inside the car for this information flow, even if you have a millisecond of the air interface. So simply the problem is quite often bigger than we think from telecom side to get on the latency. Definitely. As a generic comment given from the automotive application.
Definitely. Stefano, just quickly introduce yourself.
Stefano Galli with Huawei. Going back to the comment about RF engineers talking more systems, but also comms engineers. Above 60 gigahertz, 3GPP has not defined the waveform yet. Would a single carrier millimeter wave waveform make life easier to exploit the low power efficiency of the amplifier, not having to back off or phase noise and things like that? And your opinion on that?
So I think the gap between single carrier and OFDM is not as severe as what people would have to would believe, right? So WiGig has actually migrated towards single carrier. In AD, nobody implemented the OFDM standard. In AY, everyone is kind of moving towards single carrier. But I don't think actually the gap between single carrier and OFDM in terms of the peak to average power ratio, basically waveform complexity, how much however you want to define it, is that significant. And I think we're seeing innovations in the hardware side that would allow OFDM. So I'm personally a believer in OFDM waveforms. I think single carrier is leaving, is leaving bang for the buck on the table, and so that's my take on it. Yeah.
Also, remember in the uplink, you can get a lot of the peak to average gains by using a single carrier waveform per transmit block, much like it works in the LTE. So it's possible that there would be even less loss, at least on the UE side, where you're not multiplexing as much. I wanted to switch topics. I want to actually get back to some of these great technical issues, especially on the networking. But it was just last month that I think Akbar mentioned this, that the Release 15 3GPP standard came out, and congratulations to all of any of our industry folks who have worked on that and worked very hard and got an amazing spec out. I want to ask your opinion, a couple of points. Do you think of the new radio standard as really incremental or revolutionary? And so we're spending a lot of time in academia here working on this. Was any of it useful towards how you made the standard, and or are we just wasting our time?
That's for us.
Certainly our interaction with NYU Wireless had a big effect. 4 years ago, we really weren't a believer, and we, I guess our interaction made us a believer. And then after that point, just given the way Qualcomm is, we kind of stuck to ourselves, and we contributed standards, without much collaboration with academia. But I think the standard itself is, at least on the millimeter wave side of it, it's all new, right? There's significant novelty there, and given the amount of time that we had, the industry, it was really many all-nighters by everyone in the industry to really pull off, because there was so much new, and it's really on all aspects of it. It's not just the air interface part of it, but it's all the RF testing, the RAM4 aspect of it. It's completely new. And how do we test this thing? Does it always have to be OTA? How do we do this in a conductive manner? And it was really quite an effort. And in the result, the beam management aspect of it, and managing link failure, all that, it's really all new. It didn't really exist, and it's really just sub-6. You could potentially argue that it was more just evolution, but on the millimeter wave side, there were a lot of hooks placed that really didn't exist before.
Okay. Tommy?
A comment briefly, given the European perspective, we have these big projects, collaborative projects, industry, academia. So it's a little bit indirect in that way, because there we build a consensus, and then the project cannot contribute to a standard to 3GPP. So it is individual partners that do it. So we don't know the tracing, but we know that the METIS project also involved in, it had impact on the way of thinking and what millimeter wave could be used for and so on. And the millimeter magic project, I don't know how much actually contributed to standard in the end. But just a comment on the indirect way of we working in Europe. Then, of course, we have bilateral collaboration between academia and industry. For example, Chalmers and Ericsson, we have a lot. A comment on what I think is new and good in the standard, though, is the beam spaces and the flexible frame structure. I think those are two important novelties that are game changing.
Well, I think I have a related question, and I'll go back to latency. So, physical layer, we can calculate that. Ted, you put it very clearly. And, I was at a meeting at Mobicom last year or something in Salt Lake City or somewhere. And luckily, in the panel discussion, there was a panelist from Nokia in the panel, I'm not going to name, and one person from Nokia in the audience. And they were working on different parts of this standardization. One was on the networking side, and one was on the physical layer side. And I asked networking people, and he said, TCP/IP is a bottleneck. We cannot achieve it. It'll have to be some kind of a new, I don't even know what, a hybrid protocol. And I said, okay, is the standardization body talking about it? And he's like, well, are you guys talking? And, it turns out they were not talking to each other. So I'm going to ask Ozge, is there anyone who's actually taking the networking side seriously to kind of make it closer? I know in your question you mentioned that Google has recently proposed some new protocol. So I want a discussion on that, because I think that's kind of like an elephant in the room that's not being discussed.
I think just as on Akbar, I think we have a poster up. I know some of my students have been working on Google's BBR, and there's some test we've done here at NYU over interdigital stuff with BBR. We can talk about that, but I'll let Ozge, who was asked that question,
okay,
respond.
So I'll have to admit I'm not talking to anyone on that side. I mean, there are groups in Qualcomm that are focused on that. It's really that. My particular project is really an L1 and a RF focused project, and we don't necessarily talk to those. I mean, we're all optimizing our individual ones, but there are people that do talk. So maybe I'm at fault here as well for not talking up the chain.
I think Harish's comment was good, that people have to talk. So if industry people are not talking within their own silos,
we're in deep doo-doo.
Well, the IETF is where a lot of this networking layer standardization is going with the enterprise equipment makers, Cisco and others. The idea of TCP/IP, it is tough as you get to these very high data rates because of the overhead. And so there's information-defined networking protocols and a lot of funding that the NSF has done over the last 5 to 6 years, looking at new ways that specify not an internet protocol address, but rather content address. So if you have photos or there's a downloaded application, that can exist many places around the world in different caches, and you simply access it by a network identification. Shiv Panwar has been working on that, I think, in the back. Shiv, do you have something to say about that?
Yeah, I'll get to you. So Shiv is actually, I mentioned on BBR, and Shiv has been looking at TCP over this, and we have another TCP expert here, Michela Zorzi, in the audience too, so both of them can chime in.
Yeah, I just agree 100% with the gentleman who's raised this issue, is that the networking people are not talking enough with the Airlink people and vice versa. And a lot of the gains in the Airlink that we are discussing today, which we are rightly discussing, may not be fully actualized at the application layer without a full knowledge of how these protocols work and a rethink of these. So, BBR, we found, which is supposed to deliver low latency transport, is not aware of the vagaries of the wireless channel underneath, and there are a lot of issues with it. So certainly, I think there's not enough communication about how things at the physical layer ripple up to the applications and vice versa, which need to be addressed.
With a question over here, and then just quickly introduce yourself and.
Kumail Heather from Rice University, and a little bit more about that networking aspect. So mobile sensing is also a very attractive application of millimeter wave, especially bringing it to the mobile side. And I really think that the way to sell it would be communication plus sensing versus communication alone. But has there been any standardization efforts, or what is the industry perspective towards it? Any efforts in that domain?
Sorry, standardization efforts on which part?
Mobile sensing, like...
Oh, mobile sensing.
Yeah, like indoor localization or mobility tracking with millimeter wave.
So this is what's local...
on localization.
Localization.
Sensing with communication, like sensing applications.
I mean, right now the focus has been in TGP standardization. It has just been EMBB, the enhanced mobile broadband, and that's really been the only application for millimeter wave. And even going forward in release 16, so where does millimeter wave find a place? It's really integrated access backhaul. There's some kind of there's positioning, but it's really those applications. It hasn't really gone beyond that. Is there place for millimeter wave in sensing or industrial IoT, or those are yet to be discussed and standardized.
I think, let me just mention that the 3GPP standard actually does have a lot of hooks in it, beginning in the LTE or maybe even earlier for positioning. There is a whole specification just on the positioning part of that standard. So for example, as you know, if in the LTE standard you have to keep timing alignment. So as a result, you know the relative time of arrival from the uplink, and that can be used for triangulation. And all those parts are in the standard. And presumably they'll leverage that if they haven't already in the millimeter wave, because you'll get it to that much higher accuracy with the higher bandwidth. Tommy?
Just a small comment. Well, I think both that tracks, for example, joint communication and radar. There are research going on, for example, Charles also. But then I think there's another aspect, and that could be to harvest information from the communications. Ericsson have shown maps from the micro radio link networks where they do weather forecasts better, with much better accuracy than the radio stations that were deployed. Because the micro backhaul network is so dense. So just by following statistics on the rain fading statistics, you can do better weather forecast when it comes to the moisture at least, for the rain.
And I'm sure you've probably seen, I mean, Google has a project called Soli, which is using 60 gigahertz for gesture recognition. So they've been using just commercially available 60 gigahertz chips, converting the comm system into a radar system effectively. And then, they've shown how you can use it to, for instance, on a smartwatch, scroll through things, swipe things, and so on. So I think it's clear that millimeter wave will always be a very high resolution radar. And I think, to what he was saying, there's definitely been work on repurposing communication, both waveforms and hardware for radar. So there's work on OFDM radar, for instance, which goes away from the more traditionally used waveforms, which might be, linear frequency modulated chirp or something like that. So I think it's definitely an interesting area for research.
You remember, actually, already we've seen on the automotive space going up from 24 gigahertz to 77 gigahertz. That's a big area right now, and put a pitch in for Harish has also built some very, I believe, even higher frequency radar systems in his lab if you were to head over there.
Just a question. So I'm curious about the views of the panel on 6G. So I personally think it's early to talk about that, but I've seen it's already, the academia it's been pronounced. So I guess NYU has a project on 6G. I've seen an article on that, and last week I seen VT magazine called for papers on what will 6G be. Do you think it's early to talk about that, and what may be some fundamental technology? So from 4G to 5G, there was millimeter wave. Is there anything new for 6G if we start talking about that?
Yeah, great question. I mean, I know the industry is just trying to catch its breath from that sprint out to release 15 on 5G, and it's now people are talking about 6G. Too early, or?
No, not for academia. That's our job in academia. So actually, I'm very excited about 6G, even though we don't know what it is yet. But it'll be faster, better, maybe not cheaper. But the fact is, I think 6G, I'm going to talk about it. I think it's above 100 gigahertz RF bandwidth, RF carrier, and 10 gigahertz plus RF bandwidth. And think about what you can do when you start to look at channel bandwidths of 10 gigahertz. Remember, a foot per nanosecond. 10 gigahertz is a tenth of a foot. It's an inch. So now you can start to think about, in a mobile device, in a chipset, the ability to get resolution to an inch, and actually with some simple signal processing, get fractions of an inch. Right now, how many of you use the camera on your smartphone to take a picture of something that's hard for you to see, maybe in the back of a stereo cabinet, or if you're like me, your eyesight's going, so you take a picture of something? How many people have done it in the room? Use your camera. Okay, so it's about 10%, and most of you are older rather than younger, with the exception of Kate. But the fact is, I think this is a glimpse of the future. I think 6G is going to bring this idea of using these very, very wide bandwidths to allow us to use our mobile device to see in the dark, to see behind walls, to actually bring radar and imaging and sensing to our handset and to glasses. And this idea of getting super resolution of the environment around us is something we really haven't done, but we will. And I think you get free spectroscopy. If the air is bad, or there's a gas leak, or you have an allergy, You're going to actually be able to monitor food allergies and your whole sensory existence in the world. I think 6G is going to bring that, and those are some of the exciting things that I think we should, in academia, should be working on.
Yeah, I think for industry, it's too early. We haven't even deployed. I think if I ask for funding, I have zero chance. Yeah, I think we'll just maybe in 5 years or so.
But I mean, the good thing is that there is, federal funding for this. So there was a large center that was announced that is being led by the University of California at Santa Barbara and NY Wireless, and my group at Columbia is also participating on that center. The good thing about looking at frequencies above 100 gigahertz is when folks tell you that it's impossible, then obviously there are fundamental challenges to be solved, and so there's work for academics to go and do. So that's looking at new device technologies, so looking at 3-5 compound semiconductor technologies, whether it's indium phosphide or gallium nitride, trying to push them beyond 100 gigahertz, looking at how circuit and system design would change as you go to these extremely high frequencies. The bandwidths are now enormous. I think it will start to stress parts of the system that we, maybe took for granted before. Things like serial links and so forth will become extremely challenging. And then, of course, there's the applications, right? What can you do with enormous bandwidths, but you're now at very high frequencies, and so propagation is challenged. So I think there's definitely a lot of interesting work that this will force us to think about. And I think in Europe as well, I've certainly heard a lot of 6G type news coming from different parts. I think in Finland, I think the University of Oulu has a very large grant, that puts what we think of as large in the U.S. to shame, essentially, to work on 6G type technologies.
Yes. Well, from the start, I think these labels are sometimes a buzzword to be used for our own purpose. I remember when they started working on 4G in the winner projects, the operators refused to talk about 4G. No, we want to protect our investments, call it beyond 3G. So we did that in the beginning. And before the end of the fourth-year project, the operators were keen on talking about 4G more than the vendors at one point. So it's a flip coin when they see the need for a new labeling of the new technology and the new visions, new things you can do. So with that said, I think there are a lot of things we need to do on evolved 5G. Actually, we have a workshop at Globecom. That's the series that I call them Technology for 5G, and this year we call it 5G Plus. There are a lot of things that need to be done based on what we have. Dense networks, closer to vertical application needs, non-standalone millimeter wave networks. I see things that sure you have enablers in the standard, but that's like basic ingredients for making the dish. You have the potatoes and the onion and so on, but you don't really know how to do the dish. If you go to a Michelin 3-star restaurant, sure, there are actually some knowledge behind the basic ingredients up to the dish. Then I also believe there are new things we should do in 6G, and as I mentioned, I'm part also of a big terahertz initiative in Europe now, and I sincerely believe there are things we can do there. From communication perspective, definitely backhauling, wireless backhauling. It's an easy case. We should move up and get the fat pipes to the base station using terahertz, and we can, if we get the hardware. Please. But then I also believe in I really like what Ted said. I think there will be maybe more similar focus on sensing and communications in the 6G era, and maybe also computing in the same pool. Maybe we should do all three at once, because time matters, NA matters. Delay matters, NA matters in those contexts. So definitely there's a need for 6G. Oulu have, they're taking the labeling race a little bit. To be honest, I don't know if I think there are so many new things there. But I believe there will be 6G, and terahertz will be a component.
All right, and we have about 10 more minutes left in the panel. I want to kind of switch to two meta questions, really. The first is, now that we have an industry panel here, is about what's the role or ability for startups to get involved. One of the big problems in the cellular space in general has been the huge barrier to entry. I know you're involved in a startup. We have Professor Cioffi here, a serial entrepreneur, and Ted. All of you have worked in this space. Can you share experiences? And is it possible? I know a lot of the students here want to get into into startups, they all tell me this, but then they just really struggle. How do you get past that barrier? Is it possible?
Can I add to one thing to it?
Oh, yeah.
Sorry. That, going forward, 6G startups, that what is I also feel that as we go to higher frequencies, analog and digital interface is going to shift. If you look at optical systems, a lot of it is done analog. And there's a lot of techniques from there to be looked at too. So as you're looking at going forward, maybe comment on that too, where startups or technology could come in.
So, let me quickly comment on that as a sort of a little bit more of a technical question, then I can talk a little bit about my experience with a startup. So, I think when you go towards hundreds of gigahertz, we need to really start thinking about that analog to digital interface. It might even become similar to optical, where you sacrifice spectral efficiency for power efficiency. So instead of trying to do some 64 QAM or 256 QAM over 20 gigahertz of bandwidth, there have been people who have been looking at even just doing OOK type waveforms, non-coherent OOK. You still get 20 gigabits per second or more, but it's much more power efficient because you don't even need an analog to digital converter anymore. You don't even need a PLL anymore. It literally becomes almost like an optical transmitter and optical receiver. So there's certainly a case for that, although that needs to be looked at in the larger system context, whether that would make sense. From a startup perspective, first off, let me preface by saying, don't get me wrong, I still wish I knew how to write an app like LinkedIn or something like that and make $1 billion, right? So I still wish that was my domain of expertise, and this will never be that. And so let me preface by saying that. But that being said, as someone who knows how to design circuits and make hardware, this is at least a time where there's a lot more openness. So the things that Ozge said about the standard being completely new, about there being this whole aspect of beam management that didn't exist before, we're finding that firstly in terms of raising money, and then after that in speaking to customers, they're a lot more willing to listen now, in this 5G I think we're sort of approaching the peak of the hype cycle of 5G, and so people are willing to talk to, emerging players a lot more. People are willing to listen to new stories that need to be told. So it's definitely, I shudder to think about what it would be like to try and sell a 4G, some new hardware for 4G or some new system for 4G to people. So it's definitely a lot more open. There's still always going to be, the challenges of breaking into, even if it's the cellular or the Wi-Fi space, maybe the Wi-Fi space is a little better, to a space which is dominated by the Qualcomms of this world right here, where also the number of potential customers, if you're talking about infrastructure vendors or carriers, are still only around 5. So I think there's certainly challenges, but this is probably, if you wanted to do a millimeter wave startup, this is probably the right time. I think 3 or 4 years from now will be too late, and certainly 5-6 years ago was too early.
Do you want to go? Always. You can always do startups. Great opportunity. Every time, every place. I've done 3 startups, sold them for $5 million, $40 million, and $3 billion this year to Verizon, straight path. They wanted spectrum. The fact is, there's always a need for good ideas, and if you can solve a fundamental problem and you're ahead of the market, you heard Ozge say that industry is so focused pulling all-nighters just to meet the next standard 6 months or 12 months in advance. They can't look further than 12 months down the road. So if you can solve some of the fundamental problems and be there and prove it and be tenacious. The real thing is being tenacious. I remember when John Cioffi was selling DSL. We were both young professors. I remember how hard he worked, and I saw him going to every single carrier, convincing them that you could actually do these data rates over copper. And he was there ahead of the internet curve, right when bandwidth was starting to ramp. Similarly, straight path with spectrum at 28 gigahertz, ahead of the 5G curve that Verizon needed because they were behind AT&T in having the carrier licenses to deploy in the US. As long as you've got a really good idea and are savvy and really become a student of the game and talk to customers and listen to what's needed, you can always do a startup. Now, there are some startups that are better than others, more capital intensive than others, more likely to succeed than others. But, there's always an opportunity. And just look at what's happened in millimeter wave. Look, if we were all in this room in 2012, 2013, even 2014, none of you would have ever thought that in 2018 there'd be a millimeter wave standard in a handset. You said it yourself. No one ever believed it. So, someone with a good idea and with proof and tenacity, you can do it and you can change the world and you get paid for it.
Yeah, I think in millimeter wave, there definitely is an opportunity because I just know from just our internal development that there are a lot of open issues, open holes, and if you're competing on the modem side of it, that's a brutal battle. Like it's, I think there's no room for that because of the Qualcomm and Intels and HiSilicons of the world. But on either end of it, on the RF side, there's a lot of innovation that can happen. Maybe the challenge right now is that interface between the modem and RF is not really standardized right now. So if you want to get into a handset, it's all proprietary interfaces. So maybe that'll change at some point. And then on the other side, on the upper layers, all the management of the interference management and enterprise deployments, and how do you actually deploy these millimeter wave systems? That's another software aspect that's open, and I'm sure there'll be innovations there as well.
Let me just wrap up then with, sorry, go. Just quickly introduce yourself.
Ahmed Suleiman from Embry-Riddle Aeronautical University, Arizona. I remember like 10 years ago when we were talking about WiMAX and LTE. WiMAX was supposed to be unlicensed deployment, and it could have given startup opportunity to be able to launch something if they really don't have the means of acquiring spectrum. Now my question is that, is the following. In the context of 5G, people are bringing in unlicensed bands. How much of that are you pursuing, especially Qualcomm and others? And will you tell customers that these services are provided over unlicensed band? So, because if you don't, then it looks like we bring in WiMAX from the back door.
So actually, this time around in 3GPP, shared spectrum unlicensed is one of the key topics, at least starting release 16, and it's something that Qualcomm actually has been pushing very strongly. We were key in doing the deploying. We did multi-fire on unlicensed LTE in the 5 gigahertz band. So there's, we definitely feel there's a room for that in the 37 gigahertz or 60 gigahertz deployments as well. And it's because of, it's a tricky balance because the operators, of course, they want the license, they want to control it, but then there are other non-incumbents that want to deploy if it's it's just a private network or someone like a Comcast or someone that wants to come in. We want to enable those players as well. So unlicensed is key in standardization as well.
Yeah. In fact, I would say if you look at the unlicensed spectrum, it's probably one of the most amazing low-capitalized success story in the history of telecommunications. Your cell phone in New York City is likely to be captured if you have Wi-Fi by the Time Warner cable or a Wi-Fi network. This aggressive access to all your Wi-Fi when you're in big cities. In fact, you have to turn Wi-Fi off to get it work if you're not a Time Warner or Comcast subscriber. I mean, they have access points all over, and it's amazing. You talk to the cable companies, and they are really seeing this unlicensed Wi-Fi entree to the world of mobility. And frankly, it's very symbiotic for the carriers that want to offload as much data as they can to keep their network keeping up with the 50% per year consumption of each human in the industry. So Wi-Fi will continue to grow. You're going to see WiGig. It's already happening now in enterprise, so WiGig is really starting to ramp. Qualcomm's going to see that. You'll see the chipsets that's really grow, and the phones will soon have them, so that all these outdoor Wi-Fi that the cable companies are providing will start consuming this higher 60 gigahertz and above. So they will always continue to grow, and they'll always continue to develop, but there'll always be a disconnect. And as much as people want to try to merge the two, they're just very different. It's not just the Mac, it's the whole infrastructure and the business model, and using enterprise indoor versus mobility. And mobility is the key to why 3GPP doesn't pay much attention to the unlicensed.
Okay, I think we just have time for one last question. Just quickly introduce yourself.
Ali Cafer Gürbüz from Mississippi State University. As several people mentioned, actually, millimeter wave frequencies are also very attractive for radar applications. higher bandwidths, better resolutions. You also mentioned like millimeter wave communications will be better if you get more bandwidth from the same frequency. So in terms of spectrum sharing, how do you see the feature of this in the same frequencies, radar or communication applications working together? For the industry, do you want to share these frequencies with the radar applications? What's your take on that?
Sorry, and just before you answer that, maybe this is we're running out of time right now. So maybe just if you want to either answer that or just give your final parting thoughts about how to help universities and industry come together and realize great products. End it at that.
I think so. Radar. I know our automotive division looks at radar, and they certainly wouldn't want to share it with the communication because it's these are very safety critical applications. So I don't see that being shared. I mean, the sharing will happen more communication system to communication system. We might share with the satellite. We might share with other comm systems, but I don't see sharing with radar.
I think sharing's a tough sell when carriers are spending billions of dollars on infrastructure and spectrum. And you get maybe 3 dB. I think Michel Zorzi published a paper on sharing a couple years ago. The gains just aren't that great for the risks. Parting thoughts, this this broadband era, this massively broadband era is very new. It's really the sky's the limit. We saw a keynote today about a very exciting application of, plastic that's buried in the ground carrying terabits of data. I think it's a very exciting time to be doing research, and there are so many problems to solve. You've heard some of them this morning.
Yeah, the next year is going to be a very exciting time. We've really been working as an industry for the last, in academia for the last, 4 or 5 years to bring us to where we are today. Starting end of this year when we have these mass scale trials and we have the first handset coming out next year, it's really the fruition of all that hard work. And I think it's going to be an exciting time. And there are still a lot of open issues that industry and academia have to solve, and we'll only make this better and better, but at least now it's becoming a reality.
Yeah, I think back to, I started at Columbia in 2009, so I was just coming from a PhD that worked on millimeter wave phased arrays. I started at Columbia in 2009. Nobody wanted to talk to me about millimeter wave for about a couple of years. They just didn't want to hear it. WiGig was a failure. I started to work at RF, actually. I went back to like sub-6 gigahertz. It was also, way less expensive in the lab to do that. That's a different story. But and then suddenly, 2010, 2011, 12, 13 came along. Thanks to the work of, TED, NYU Wireless, folks in industry, the interest in millimeter wave exploded. Now there's more money in millimeter wave than academics know what to do with necessarily. So I think resources-wise, doing innovative work, there isn't there's a lot of excitement, there's a lot of willingness to invest, and so I think it's an exciting time from that perspective. I think the main wish list from the academic side of things, if I were to think about it, is I think there needs to be a stronger connection between industry and academia in terms of informing academia what the real problems are. On the RF side of things, as I mentioned, certainly a lot of work had been done in the mid-2000s. Of course, there's still open problems. I think power amplifiers are still an important problem. But I think really a lot of the open problems are the intersection between the hardware and the systems. And I think that's where each individual community is not necessarily sufficiently educated as to what the real problems are. And so I think meetings like this are certainly very valuable. I think the different communities need to speak to each other so that we're actually solving relevant problems for millimeter wave moving forward.
I can comment on both the unlicensed aspects, I think, and a little bit on the research ecosystem. I think it's so important to have the unlicensed spectrum domain for innovation. A small company can start ideas, and so we really need to maintain and protect it. When we go up on terahertz frequencies, there are not much spectrum allocation now, but we need to protect in the ITS domain. I think there are room on innovation. There are ITS bands. They're dedicated for ITS services, but within that, it's unlicensed, right? Or you can have open competition. So it's very good there, but then at one point, when they scale up and become massiveness, we need to rely on it. We need the reliability of a license. So I think we have a decent balance as it is now, to be honest. On the research side, I can comment a little bit from EU perspective. Going from FP7 to Horizon 2020, the risk program we have now, it went from academic point of view, I think, a little bit too close to industry needs. There were less room for academic initiatives in the EU projects, in the bigger ones in particular. Let's see if it will be rebalanced. We have a new program coming up soon, FP9, and there will be, part of it at least, will be based on missions. So it will not be, well, everything is not decided, but the indications are there. Meaning that it's not so disciplinary research, it's towards problems, societal problems. So let's see if we'll have clear dedicated communications programs. It might be connected to some missions. Let's see how it will go, but there's some new thinking there.
Okay, I want to thank the panelists. I also want to thank NSF, and in particular, Tiaga Nandagopalam and now Monisha who's here, because I think they were not just champions of 5G, they're the sponsors of this event, not just champions of 5G and millimeter wave, but also really, they both came from industry of trying to get industry and academics together, and so this kind of panel wouldn't have been possible without them. So one hands of applause for all our great panelists. Oh.
Okay, so let's get started. So my name is Manu Gosain. I'm from Northeastern University. The hat I want to wear here today is as part of the Power Project Office. Power was a program called Platforms for Advanced Wireless Research, recently announced by the NSF, well, in April 2017 as part of the Advanced Wireless $400 million investment. Our goal is to fund 4 city-scale advanced wireless research platforms, and sparing you some of the details of the program. We fast forward to April 2018 when we funded one of the platforms called Cosmos, which is actually based in New York, with the main team members responsible for developing and deploying that testbed being Rutgers University, New York University, Columbia University, and the city of New York. And lo and behold, their main wireless research focus is millimeter wave systems, hence our interest in this community. And as it is a deployment, a large city-scale deployment envisioned in millimeter waves, we really wanted to get input and feedback from experts here in the room, as well as on the panel, who I'll introduce in a second, about what are the different ways, and first of all, what are the needs of this community when it comes to systems and testbeds, where this community is in the technical roadmap of developing systems, as well as how best could we accelerate some of that research and produce systems that can be of use to the community. So that'll sort of be the theme, and we'd love to hear. It's again, an open forum. Discussion questions are best. We're not going to be presenting much slides, but we did put forth some questions. With that, I'll pass on the mic to the other panelists here. So Kira, do you want to introduce?
I'm Kira. I'm with National Instruments. I'm part of our business development and lead user team, and I work with lots of researchers and companies in setting up testbeds and helping to understand what products would make sense for us to be developing to support testbeds.
Hi, I'm Greg Lakai. I'm a PhD student at UC Berkeley, and I'm leading our effort to build a testbed that's a 128 element massive MIMO implementation at 75 gig. So we've been kind of working on that for the past couple of years, and all the hardware is coming together, and we're entering the final stages of integration now.
I'm Han Liu with Catholic University. I'm a faculty member there, and my research is mainly on the millimeter wave networking, on massive MIMO, and some other related issues.
Okay, so when we were sort of tasked with running this this panel or this discussion breakout, some of the questions that we put forth that we've put up here, the first thing is, again, how does a testbed benefit this this community? And again, we understand there are multiple stakeholders, both from academia as well as industry, who participate here, and essentially, you know, what stage of that development roadmap do we have? We know industry is much further ahead. We heard earlier today about trials that have been done by Verizon and AT&T with millimeter waves, and you know, we want to get a sense of what that gap between industry and academia might be, and how best can test beds that might be developed or this input that can be then relayed back to the National Science Foundation with respect to what is missing in this community and how do we best accelerate some gaps. So we have some academic folks here. Maybe I start with Greg with respect to where you are and where you see industries and some of the gaps, if you may address those.
Sure, yeah. So as far as what we're doing at Berkeley, we've kind of, taking two fronts where, at the end of the day, we do a lot of custom ASIC design, and we kind of want to move down that road so that we can demonstrate, energy efficiency and form factor and things like that. But, building an ASIC is kind of an enormous undertaking. So we're also kind of exploring off-the-shelf solutions that, might burn kilowatts of power and, be the size of a refrigerator, but they'll work, and we can kind of prove stuff out that way. So I think kind of both of those roads are important for, what we're doing.
Yeah, and maybe I can add a little bit. So, and right now my research is mainly focused on higher layer protocols like media access control, multipass access, and and mobile device associations of each base station associated to and whether or not to go multi-hub or etc. Right. So mainly our research right now is the tool we are using is simulation and analysis. So I think that the test bed is really, really important. So I still remember, several years ago, everybody was working on this wireless line, right? So we work on this ad hoc networks. So we work on, and the different wireless line techniques. Especially for the higher layer, there are different routing protocols, different media access control protocols, power control, or different tricks to form networks. So, but for the millimeter, so there were a lot of experiments because wireless line was available at that time. Then there were multiple test beds were built, like Rutgers, they had this Orbis, or then there's a Genie project, But right now it's lack of test bed for the millimeter wave, right? So even now, and people are trying to build. So, but still not there yet. So from component point of view, you may get here or there, right? So, but for the more systematic research of the large test bed, is still not there. So, but I think that's the key, critical. And also, a lot of equipment are very expensive. So like NI equipment, so we have to spend a lot of money on that. So, yeah.
Kieran, do you want to highlight where industry is based on your interactions with them on millimeter wave systems, etc.?
Sure. That is definitely feedback we get a lot. Is we want it better, cheaper, faster. But there are definitely constraints within industry of how do you actually make a product and make it something that can be usable and scalable. So that's really where we are is trying to make it scalable and make experiments that can be repeated.
Okay, perfect. So I guess just to let's start again at the base of what the fundamental problem is. I think I want to sort of jump off a comment that was made earlier in the morning. I think Akbar made that point where the radio designers and the network designers aren't really speaking to each other and aren't really aware of each other's constraints and issues. We obviously see testbeds as one place which sort of is very democratic, which allows different players to come in and actually integrate solutions end to end to really understand and implement application services or actually play at each layer. So what sort of one of the things I guess we want to understand here, and we want to reflect that back to the wider audience when we do reports out, is where do we actually see the benefits of testbeds for millimeter waves? I think clearly there's a pain point where people have put their head down and are really moving aggressively. And we also heard, I think it was quite openly stated, at least from the Qualcomm perspective, that if you don't try to get into the modem game, that's just the barriers of entry are too high. So where can we actually play? And that sort of gets into it. The further away you move from silica, I think that's when things start to get a little bit more open. Are we there yet in terms of addressing fundamental research questions in the millimeter space that would actually call for development of testbeds? Is there more? And that sort of, I'm jumping a little bit ahead, and I apologize if there are any international members in the audience. I'm just using some standard NSF terms up here. So this is switching gears with respect to, first of all, what is the need? And if there is a need, how could that be fulfilled with respect to the current instruments we have as part of our different agencies that we can rely on for funding such testbeds? So, again, pose that question, where are we at a stage where the technology or the research is mature enough for community size, large-scale testbeds, or do we still need fundamental challenges or fundamental questions answered that might be done at an institution or at a much smaller scale?
Yeah, I guess one thing that I would kind of chime in on is that I think, building these kind of large-scale testbeds and building them in kind of a flexible, reconfigurable way actually really helps us inform what we need to do, right? Like, I think once you get to the point where you're going to build something that's actually commercializable, there's going to have to be a lot of analog mixed signal design. You're going to be doing hybrid beamforming, things like that, and it's going to be a tightly packaged kind of system. But to get to the point that you are going to want to actually be confident in what that system looks like and know that you're building the right architecture, you want to have more than just kind of pairing, some building block characterization with some MATLAB sims. So, that if you talk about building, fully digital arrays with kind of FPGA implementations that are highly programmable, yes, they might, burn a kilowatt, but you can actually emulate the analog, say, in those designs and show that, like, okay, I threw away, these many bits of resolution and I left these things partially connected, and I can kind of almost match these systems. So I think people building these flexible test beds is really good, and just finding a way that we can make it cost effective for them so that they can build something and test out a lot of different scenarios on a flexible platform will help move things forward.
I guess along those lines, I would sort of change the question a little bit and say that I don't think that they're necessarily mutually exclusive, but they should build off of each other. And how do we make sure that we build both types of test beds so that they can, so that there's no barrier between them? It's not necessarily that you have one small CRI at your university and that means that you can't make use of a larger city scale test bed. So how do we kind of flip the question and make sure that we're utilizing our resources as best as possible, which I think is along the same lines as what you were saying.
I also think so, and on the other hand, right, and typically if you have these smaller test beds, so you can do some prototyping by yourself, more like in-house, right? So then, because most of a large community test bed is far away, even we have a good management platform there, like Utah has or Rutgers has, right? So, but it's still far away, and you have to schedule it, and if you can have some internal sandbox type of thing, at least you can do some experiments, and also I found, some students, they are more used to see something before they can do it, right? So if you have this remote test bed,
right. So there's an inherent trade-off there. At least, the good thing there is that this is the area where everybody wants to work. But because we are at such an early stage, things are obviously a little bit more cost prohibitive for sandboxes at each of your home institutions, which I'm sure as academics you're aware of. So that's sort of the, and that's where a shared test bed sort of lets you defray some of those, costs, because you sort of optimize the usage of those resources, et cetera. So that's where I guess the scale question that I was trying to pose. And if this is seeming a little bit more amorphous of, test beds, I'm happy to sort of just go over, we don't have the Cosmos folks in the room, but I'd be happy to go over what the thought process for the millimeter wave test bed that this team has envisioned, and it might help sort of stimulate thoughts around, and we have a lot of open questions that we are hoping to answer, if that helps.
So I'm Stefan. I'm from Freefall. We're a startup company out of the University of Arizona down in Tucson. So Tucson is a very kind of close-knit community. So you do have stuff like there's a hacker space where people can join and go and use tools and stuff there. So community level, something like a scalable test bed would be good. Our company, we develop a lot of stuff in-house. Mainly it's been simulations, and now as we move towards this 5G, we're finding, well, we have to go out and get this equipment that can go to these frequencies. And we know that the frequencies are going to go higher and higher. So with that, we also want to have equipment or a test bed that would be scalable for that, so we're not having to rebuild from scratch constantly. So that's just kind of my initial reaction on that.
Yeah, so eventually the idea is that within the Cosmos testbed in New York City, you'll have access to 2 millimeter wave technology within a city scale testbed. Is that something that you would then, I guess, what would barriers of entry to using something like that be for you and for your company?
I imagine at that point just accessibility to it, being able to access it at a reasonable cost. So, especially if it's a well-defined test bed, then we can build our stuff to interface with it and then just go utilize it.
For me, 100 gigahertz is the low frequency end. So, talking about community scale test beds above 100 gigahertz is sort of talking about, it's kind of like talking about opening an ice cream shop on the moon. It's a little bit ahead of its time. But I don't know, is Cosmos got anything at frequencies above 95? Well, okay, then give me a call when you're ready. Because we can make measurements as high as you want.
It's echoing Dan's comment is, when this was built as a millimeter wave session, it's really a solely 5G millimeter wave session.
No.
It's not solely 5G.
No.
It's solely below 90 gigahertz.
It's open. I think we are trying to think. We're trying to obviously understand what the requirements are,
okay,
and how they might change. So yes, please.
Well, let me comment. Give a preview to my presentation. Is a key issue above 95 gigahertz is coexistence with passive satellites, and a key issue of that is measuring antenna characteristics. And there's no convenient common source for measuring antenna characteristics. NIST may be about to open a better test bed, but maybe they are, maybe they're not. So an important test bed for those of us who are interested in above 9,500 gigahertz is verifying the performance of antennas, particularly at side lobe levels. Side lobes are very critical for sharing, and there's no open source to measure side lobe levels, and that would be a common resource for the technical community that, whether it's NIST or NSF supporting it, would be very useful.
Actually, so maybe I can kind of just ask a question to the audience then in terms of, I think when we talk about these test beds, it can be in kind of a couple domains as far as what it's actually being used for. So kind of the stuff that I've been interested in that kind of Hydra is pursuing at Berkeley is really kind of this co-design of circuits and systems and kind of end-to-end functionality, right? So we really want to explore all the way from network level to PHY, how do these things actually kind of play together? And so in that aspect, I don't think there's like a huge difference between 75 gig and 140 gig in that, it's mainly digital. You have a direct conversion front end, and it changes the propagation characteristics slightly. So that's, I think, one aspect of the test bed. And if changing the front ends and moving to over 100 gig is something that adds a lot of interest to the community, it's something we should be talking about. And then also, I guess what I'm kind of hearing is that there's also still a lot of purely PHY research that people are interested in. And so how can we maybe design these platforms to kind of satisfy both needs?
And it doesn't need to be one size fits all sort of an approach. So what sort, and that's the point here is, again, not to come to any consensus, but understand the landscape better. So what we have again today with, if you call that 5G, would be 28, 39, maybe 60, which is unlicensed. And then, you could compartmentalize that as short and medium term, because that's probably where the industry players might be more interested. And that might be a space that's probably ready for some of these system-level integration issues, which some of these testbeds might be amenable for. For the frequencies that you're talking about, going up above 100, et cetera, there are fundamental research questions that need to be answered, and that's where you need calibration instruments. You're looking at it from a different perspective. So I think. Much earlier, of course, and that's where we want to put that on. So when we do present this, at least to the when we report it out, we obviously want to break it into if the group here thinks that's a fair distinction to make between a short and medium term versus going forward.
Even at 5G, while the bands that you've mentioned are the ones officially designated for 5G as of today, there certainly is discussion in the cellular community of 70, 80 gigahertz. So if you're in the R&D business, while no decisions have been made on 70, 80 gigahertz, and there are some awkward issues about present users versus 5G, but am I the only one who reads publications that say there's discussion of 70, 80 gigahertz as possible? Right, so, if you're building test beds other than for what's about to go in production next week, and I would hope that NSF-supported things would be focused not only on what's about to go in production next week, because it's supposed to be fielded by 2020. The FCC is obsessed to win the race to, FCC and CTIA are obsessed with winning the race to 5G, whatever that means. There certainly is discussion of 70, 80 gigahertz, so there should be some capability, even in the 5G community, of not just focusing on today's official bands.
Yeah, so I think I'm going to interject a couple of things. So we have, it's a little bit of a sparse audience here. So this is also going to seed the questions in the discussion tomorrow in panel 2, because testbed development is an important topic, and I'm sure that people in the other breakouts are interested in that as well. So I'm going to reframe it. I would like, Manu, you to give a little more, add more to the power. My understanding of power is that, it's going to be more of an infrastructure so that we can explore 5G and beyond. Any kind of emerging technologies so that you can have a city-scale test beds to explore them. And in terms of the questions raised by Dan, there's a fine line between what's stable and ready for that city-scale test bed and very nascent and really, has to be nurtured in a lab. So as it gets forward, maybe there can be partnerships formed to move it up there. So it's going to be a combination. But going back to Greg's comment, end-to-end simulation is of interest. And so right now, there are very few platforms available. And in fact, NI is a monopoly. And so we want to break it. With all due respect, we want, so it shouldn't be just that. I think, so in my lab, before I was at NSF, we were building a test bed where we did the whole front end lens antenna arrays and the RF and the back end FPGAs. And it's a lot of work, but you can do it. And I think some of it is done at UC Berkeley as well. And so there are alternative versions too. You can make it more compatible with MATLAB in addition to LabVIEW. And so the question here is, what would be useful to people? Some may be interested in just the antennas, and before they can get to power platforms, they may be able to partner with some other researchers, say Berkeley or even in my lab, where they could be, those systems could be put as part of an end-to-end system, or some other players who may be using NI platforms. Right. And or if it can the community, if say Berkeley and other people are developing FPGA-based protocols, those take time. Can they be done in a modular fashion so that they can be shared with the wider community? That could, some of it may be developed in power. So we want to look at all of those aspects combined together. And so with that, maybe Greg, you can say a little bit more about what are you guys doing? Is it FPGA based? Are you interested in, do you think it's in a place where you can share it with other people, the designs, and what could be done there? Maybe Kara can say something about next level, maybe the USRPs. I know that maybe they're at a better price point where you are playing with more of the higher level functionality. And then Manu can say something about power as well.
Yep, that's great.
Sure. Yeah, I think kind of at Berkeley for like this Hydra project, we've kind of built it up to a point where we have a platform that's kind of tied to our architecture, but the hardware that we've built can be kind of adapted. So we're going to be taking a couple fronts where right now it's an uplink only, so it's just kind of the handset talking to the base station, and that's been kind of easy for us to make modular and kind of build up one step at a time. So there's kind of a front to kind of keep going on that and explore like what we can do in the uplink architecture, and there's a front to kind of add downlink functionality. So when it comes to like interfacing with other people and collaborating, I think actually, very soon we would be on the front where we're kind of able to interface on the uplink side, and we would love feedback from people on, what things they would like to explore on that side, what kind of Mac level and network problems they could kind of use our platform to explore. I realize when it comes to doing network level stuff, it's kind of hard if you only have one direction of the communication. So I think that getting the other direction is kind of a priority for us and something that's coming down the road. And hopefully once that's up, then we can definitely plug and play with people more. But we definitely want to have collaboration on both what should be in the stack above us and making our platform at the PHY level available so other people can also kind of explore their own PHY level algorithm of choice.
Just before you pass on, if you could just touch on some of the, and I'll do that for the Cosmos one. But what are sort of the biggest barriers that you see in your development? What sort of
packaging? Millimeter wave packaging is a pain. It took us a long time to get to a front end that we could kind of reliably assemble with high yield to build up a large number of antennas. I think we're there to that at this point. Fingers crossed. We do have kind of 64 antennas kind of up and running now, but it was a pain to get there because you're kind of in this weird space of not low volume, but certainly not high volume. There are not a lot of people that want to work with you in that space. So that was I think that's kind of our biggest barrier to entry. And then cost I think is a barrier to entry for everybody. I went back and kind of crunched the numbers, and obviously we had to respin boards in our design and stuff like that. But I think now knowing the full design, if you wanted to buy everything from scratch with like no donations or anything, building a full Hydra system would cost you around $300,000. Right, and that's 128 base station antennas and 16 handsets. So it's a lot of functionality for that, but it's still, for a university, a very significant cost.
Mm-hmm. Okay, so let me ask a follow-up on that. So one, the barrier to, the packaging, was it a little bit more, did you have to work with a third party to manufacture it? You had to design yourself? And two, out of 300K, how much of it is your digital backend and how much of it is the front end, phase array, and RF?
On the packaging front, I think, the embarrassing thing is that it gets to the point that the key to success is knowing the right technician at this company to call to make sure he's the one actually running the wire bonder for you, right? It's kind of silly that you have to get to that point because, you're paying them for a service and they should be kind of doing this to some specification. But at these very low volumes, if you're talking about I'm doing 100 elements and I need a yield of, better than 90%, that's kind of the space you're at. So I can share the email of, our contact at that wire bond house, but probably if everybody decides they want to do this, they're going to have to find their own guy that is the right person to be emailing. So I think for Berkeley, we've kind of solved that barrier, but I don't know that I have an open source solution for everybody in that space. For the cost, I think it breaks down actually pretty, for kind of the fully digital direct conversion architecture that we did, it broke down pretty cleanly. It's about 25% FPGAs, about 25% data converters, 25% 75 gig front ends, and 25% packaging cables and odds and ends and stuff like that.
I said USRPs. I mean, are you, where is NI in its ecospace of offerings? I know that you guys have the high-end PXI or whatever, and then you are also going to do some USRP level production. Because, some of the things may be interested to people who want to do PHY layer. Other things who are maybe on PHY fixed and they want to play with some of the networking layer USRP kind of architectures may be relevant too, so you can say something about that. And also you have partners in your system. So going to Greg, even UC Berkeley's partners, I know you don't want to give the number away, but I think we shouldn't leave it out because there may be, it's not just one person, one company, there are multiple companies, and perhaps we can do something here. So it's not out of the option. And then maybe NI has partners who may be willing to work with the community to develop some of the stuff. And maybe we can even help in some of the painstaking work that those people have to do before they do their specialized work. So I want to think us out of the box.
Sure. So I think there were a couple of questions in there. So I'll start with the topic of USRPs. So I typically, in a millimeter wave type of conversation, would leave those out, only because they're 0 to 6. And pretty squarely in the 0 to 6 range. They are definitely our lower end offering, but also FPGA enabled for that PHY layer prototyping. The nice thing about anything in 0 to 6, if you have a front end that would be down converting that low, then you could plug them in front of a USRP and automatically get that scalable architecture there that you're looking for, which I think is the direction we might end up going in one of the power programs. To answer your question about partners and expandability, I think the demo right out front is a great example of, similar to the USRP, but even on the PXI platform, being able to take the same physical layer, the same, for that example, it's channel sounding and putting, and stepping from the 60 gigahertz channel sounding and prototyping and measurements, and then putting, I believe it's 140 gigahertz front end on it that's out there right now that Ted's group is doing. And our goal with our architectures is to make that an option. So whatever front end you want to use, whether it's NI or not, if you can put it in front of our hardware, and then whatever software you've written can then be scaled to that frequency based on that hardware. So I think that's a good example of what you're talking about there. We are not sort of encouraging anyone in any direction as far as development of front ends, so I don't think we're the right people to talk to about partners there, but VDI out there is a great example of someone who is creating those front ends.
Just as kind of a follow-up, so I think in this millimeter wave space, there's kind of two things that millimeter wave buys us, right? There is this opportunity to go to like much wider bandwidths, but then there's also these this high directionality and beamforming gains and all of these algorithms. And I think from the algorithm people that I've talked to, the bandwidth isn't actually that important to them. So I think if I think of like the NI platforms that are available that I've seen, I think your 128 massive MIMO system is actually cheaper than your like single element millimeter wave system, or like roughly of the same order. And so if you could put out a cheap millimeter wave front end that could kind of plug into that massive MIMO system and says, give you 128 elements, but we only have 20 meg of LTE style channel bandwidth, that would be something I think a lot of customers would actually be really interested in. When we were first starting Hydra and talking to NI, that was actually the biggest problem, was they were kind of pushing this 2 gig of bandwidth platform. It's like, well, we want data at every antenna, so obviously we can't buy 128 of these $1 million systems. So I'm just curious if you guys are interested in that space as well, if you're going into that market.
I think it's a great idea, and it's definitely been tossed around. We've had conversations with other customers around the same thing, and knowing that there should be an option with lower bandwidth. Right now, the platform doesn't support it, and I think from a historic perspective, to not get too much into the history, our components in our front ends are more designed for a test type of customer and a test environment where they have to be a little bit more precise. And so cost there, it just is what it is from a component perspective. I think you guys figured that out too, that it's hard to lower the cost of components there. So yeah, I think it's definitely something that we would explore. When is the right time and how to do it, I think is still up in the air, but for sure.
Lower bandwidths, you can only go to a certain point before you can create a bigger headache for yourself. For 20 megs on a 30 gigahertz, you're inviting disaster, because things are going to go, because you won't be able to digital process fast enough, and the variations are probably going to kill you. So, temporal variations, everything is faster at that, so you don't want to go too low.
I think it depends. It depends on your algorithm. If you're talking about like an OFDM-based kind of algorithm on that, your subcarrier bandwidth is probably below 20 meg in like a millimeter wave architecture.
Well, that's right, but you're sampling faster.
Yeah, but in OFDM, you just have a smaller number of subcarriers at that point.
Yeah, actually, I also want to add a little bit from cross-layer design point of view. So, because I work on these networking protocols, and from higher layer point of view, right? So when we do the experiment, all we want to have this abstracted view. So basically, we want to change some parameters, physical layer, for example, and the beam pattern, or number of beams, and the power, very flexibly, so then we can do this cross-layer optimization, right? So it's really good to have a standard interface and provide the tool for the higher layer researchers, to control it. So.
Actually, that's a great point. So let me ask both, NI's platform, how much networking protocols can you play with? And then, Greg, where are you guys with your networking backend?
So I think, like the rest of NI's platform, it's up to the user and how much you want to put into it. We do have hooks in some of our products now to add in some network simulators like NS3, and use a more standard physical layer and then have a hook into a simulated network layer. But if you wanted to build your own network layer, that's something that you could do. Right now, those layers aren't available in any standard products from NI, but I think you should add it.
Yeah. So as far as where we're at on kind of the Berkeley platform, like I mentioned earlier, right now we're kind of unidirectional. So that kind of precludes a lot of, network stuff, right? So we have our architecture is a closed loop beamforming. So the handsets send pilots, and then that are scheduled with just kind of a reference clock, and then they send their payloads. And so we're just, kind of lower end max stuff. Once we get the downlink into place, I think we're actually very excited about, adding in hooks to do the network level stuff. That's actually something we're trying to prefetch a bit, in that we are, we have a couple students that are just kind of building on FPGAs more standard interfaces for 802.11 LTE and like a couple things like that, so that we'll have some example platforms about, how we should plug in at the different levels, and we can kind of substitute our own hardware at the lower levels once we get to there. But it'll be a little bit before we actually have the downlink direction, and you're not going to do networking without downlink.
Well, yeah, that's true, but you could, okay, so you're developing FPGA based. Is that something you want to do, do you have enough, or is that something where a collaborative, like say someone, maybe Hank's group, or I know that there are some other folks who are more focused on the networking side, and they may be using a really primitive PHY layer, like some velocity thing from Qualcomm, which they are ready to pull their head, hit them, whatever. So they may be willing to, reduce the time frame. Is there possibilities for teams working together in that regard?
That would actually be great. Yeah. Certainly at kind of the L2, L3 interface, where you're just kind of expecting like packets and scheduling, we don't have any secret sauce in that space. So somebody having a kind of structure and a standard interface definition that we can kind of put on an FPGA and just, fill up a buffer and take info from that, that would be a great resource for us to have to kind of pair with people. At the L1, L2 interface, we do have kind of these closed loop beamforming algorithms. So our particular hardware that we're building is a bit more specific about what we would want. But I think we could certainly at least talk about, people being interested in getting involved in that, and, how we could, if not standardize it, at least generalize it a bit more. Yeah.
Yeah, and I think that's what I think from a cross-layer interaction perspective, maybe if we could build modules which were on a common, we decide on whatever FPGAs we're going to use on a common platform, and then have some underlying common framework, and then some people could develop the networking protocols, and then they could be tested out on a particular hardware space, and then if we twist the right arms, we might be able to get, replicate it at other places at maybe a little lower cost. So some people, for example, I think we could provide front-end beamforming architectures at less, lens array-based ones, which are much less costly, and which could be an alternative to a price point and functionality to explore in a bigger context. Okay.
So just to, this is a great conversation piece. So just to distill it for what's the work, or what needs to be done to get to that point, is to sort of identify the players who are sort of developing the hardware, and then what I'm trying to understand is what's missing.
I think people getting on the same page about who the players are going to be, how you're going to team up, where to actually draw the interface lines, that's really important, obviously. Coming up with the right CAD flow as far as this FPGA stuff is really important. If you're going to actually put both layers on the same FPGA, you kind of have to be in sync about how you're going to implement it on there. Right now, I actually kind of want to change our flow, but I don't want to burn up the infrastructure I already have. So that's something we would kind of need to get on the same page about. And just kind of coming together and figuring out who's interested in doing it.
Yeah, I think in terms of the interface, right? So one thing is what parameter can be controlled. Another one is the measurement, right? So certainly the physical layer measure a lot of stuff, right? This CSI or each antenna, what's the received signal, and how much information or how much measurement can be exposed to the higher layer and can be used to design this cross-layer optimization. That's another aspect, Certainly there are a lot of trade-off, if you put a lot of measurement out, there's a burden for the hardware, but on the other hand, from testbed point of view, and you may give a higher layer designer some more controls.
So to use that as a sort of, I guess, jumping off point for what this particular Cosmos platform that was briefly mentioned, just to sort of give you an idea of what exactly the vision here is. Some of you have heard this, some of you might not have, but as part of that power program, this is one of the platforms that has been awarded, and the award was made in April of this year, so this team has just literally gotten off the ground with respect to their designs, etc. The teams are sort of listed up there. Majority of the players are actually present here at this meeting, NYU, Columbia, as well as Rutgers. So what's the millimeter wave side of the story? So before I get into that, essentially what the whole vision of this platform is to develop a multi-layered computing system with RF clients, flexible signal processing, network compute application. So it's sort of envisioned as an end-to-end system. Millimeter wave is obviously the key RF technology, but as you can see, this is pretty much envisioned end-to-end with a goal of actually being able to play at any layer of the stack that you'd want to play in. And you can sort of have a tunnel vision and focus on a particular piece without caring about what happens at higher layers, because that sort of comes as part of the baseline for these platforms. This is envisioned to be deployed outdoors around the Columbia University campus in West Manhattan. So this is around where the Columbia University campus is, and the two big parallel lines are Broadway and Amsterdam Avenue. It might be hard to point out here, but there are essentially large number of rooftop sites which will have multiple SDRs in temperature-controlled boxes or co-located indoors with wideband, multi-band antennas on the front end. So programmability and flexibility being a key design criteria for developing these platforms. The scale is about 1 square mile is the deployment area, with about 20 to 30 site locations on streetlight assets, 9 or 10 of those on rooftops, as well as a large number of small mobile, semi-mobile nodes that can be placed in cars, carried in backpacks, etc. And on top of that, all of these nodes sort of are connected via a fully configurable, reconfigurable optical DWM-based backbone. So ROADM switches will be deployed at each of the boxes you see. So wherever there's a radio site, it'll have direct connectivity via fiber to these ROADM reconfigurable optical switches that allow you to switch at the light level, which allows you to develop or create different topologies on the network side of things. So now you have a very thin RF client, large amounts of network, and then you have lots of different kinds of compute, again, co-located to the radio. So CPUs, GPUs, FPGAs, very close to the RF. So you could implement, or you could think about Cloud RAN, radio over fiber sort of applications that can be envisioned. And this is, again, I'm right now focusing on the sub-6 space, so that's also part of the mandate. So as you can clearly see, I don't want anybody to have any illusion that this is solely dedicated, focused on developing millimeter wave technologies. It is envisioned to be end-to-end. There are large, lots of expertise in different areas that comes together to actually build this beast. So that's sort of, that's the overall vision. That's what's being done. They have about 5 years worth of funding. And as Akbar correctly pointed out, it is an infrastructure project. That's how it should be viewed. A lot of the research that's been brought or has gotten us to this point is obviously accelerated what this infrastructure can do or can provide to the community. But again, no illusions. This is pretty much about building and deploying this infrastructure at a large enough scale that allows research and industry, as well as our SME startup folks, to actually get access to things at scale, which would be very hard to do on a per company, per institution basis. So that was sort of the philosophy rolled into what Cosmos is going to do. With respect to millimeter waves, so essentially, the way we drew the line here, I think they will be focused on what we would like to call, at least in this room, the 5G spectrum, so which would include 28 gigahertz to begin with, and then the ability to scale up to 60 gigahertz. And that's what the plan is. Again, as I said, April 9, 2018 was when the award was made. The millimeter wave development roadmap story is still evolving, and that's sort of one of the reasons, at least I'm here, to keep my ear to the ground, understand from this community what exactly is going to be beneficial to the community, because this is sort of an avenue that's been presented or provided by the NSF, and we want to understand that we're not building something that nobody's going to use in a year and a half when this will be available. So getting your inputs here is absolutely paramount for us as we think through these things. So for the 28 gigahertz, what essentially we have as part of the team is a IBM team which is going to provide the 28 gigahertz phased array. I can give a little bit more detail if people aren't already aware of this. This was sort of a well-cited, well-published paper by an IBM Ericsson team. So 64 antenna elements, essentially 4 ICs, multiple TX-RX pairs, and essentially it outputs out 3.5 gigahertz IF, at which point you need some or some large amounts of baseband processing if you're doing what the Cosmos team eventually wants to do, which is 8 simultaneous beams, 500 megahertz or 800 megahertz of bandwidth. But to begin with, the plan is obviously to start small, which is with a single stream. We are trying to work with NI to sort of understand what are the best ways to actually get that baseband processing done so that these systems can be deployed. And that's sort of, again, one of the avenues that we want to understand. And this is where it becomes semi-attractive to move along that thread of a modular sort of a setup where you can sort of plug and play different configurations. Hey, you bring this expertise, you do this, you define the interface, and you sort of plug it in. I think that's sort of the same design philosophy the Cosmos team has with the IBM team, folks from NI, as well as the NYU and Columbia team providing some. So with respect to where millimeter wave will be deployed, I think the goal is within the first year and a half to have about 25% of these sites be millimeter wave capable, having that phased array RF front end, which will be available to the experimenters. And at this point, sort of, I reflect back and we'd like to really understand what are the kinds of things. So if you put on your best fortune teller hat and think ahead to a year and a half out, what sort of research challenges would you envision this community struggling with or wanting to implement, validate, publish, etc.? Because that is obviously one of the key mandates of these platforms as well. So, any feedback to me, and I'll relay this back to the development team. If you see Sandeep, Harish walking in the hallways, make sure you tap them on the shoulder, let them know. But the timeline, at least for this community, is with respect to something that's going to be available for you to play with very early on in a sandbox environment by October, November this year, with a small set of outdoor deployed, remotely accessible community testbed a year and a half from now. So, pause here, take questions.
I have a question. So did you say an IBM 16 4 antenna?
Element, yeah.
4 antenna elements. So 64 element array, but each patch is 4 antenna.
That's right.
So a single beam would only be formed with 4, or would it be formed with 16 elements?
16.
So this is 16, I see. So 16 element, 4 antennas.
That's right.
Okay. All right. So 16, but 64. Okay. So this is going to be, so this is great, and I think we will give a pointer for, tomorrow or two to give feedback. But, this is a single beam, so this is, for millimeter wave, this will be small steps, I think, in some ways. And I think this would be a great where we can get in and plug in. That would be really useful. That would be nice interplay. But what we want is, so Hydra is multi-channels. We can do multi-channels and other places too. What can we do in parallel for community testbed development, which could eventually, we could try some new algorithms, and then they could be really tested on the Power platform. So I think that's what we'd like to get here as well. But this is really good input. Thanks.
Yeah, it's one piece of input I kind of have about just this array architecture is it's really nice if you can find a way to get per antenna channel state information recorded somehow for experimentation. Because I think, even if we look at platforms that we want to build and we say, we're not going to put a data converter at every antenna, as like a low-level circuit designer, maybe we can put some kind of interesting, innovative blocks there to kind of cooperate at like the per antenna level and the higher level. So knowing, having that capability so you can test these algorithms out either digitally or in software or something like that is like a nice capability to have.
That's great.
But that's actually a good question, and I don't know if they can necessarily.
Yeah.
I think this is probably a 16-element phase array with a code book or something, and they may not even be measuring it.
Right.
So it's going to be millimeter wave in a straitjacket.
Yeah.
So I guess contrary to that, I think now is the time to bring those up when we're still, and I don't know why I said we, while the teams are still interfacing with someone like IBM to actually push them for that information and to make that available. I think now's the time to hear that.
Yeah, and that's exactly right. So that's the kind of feedback we want to hear. While
no, I agree, but I'm just saying that. I think their hardware is not capable of providing that information.
No, understandable, but that's what we want to see. What if this is useful and at what level would it be? So I think thinking of at least these platforms down the road, I think the model that you suggested here, where you're leveraging other test beds, maybe your sandboxes, and actually getting yourself ready for these systems to come online, so that you can actually port over or bring your experiments or bring your research to actually conduct on these platforms would be really good. And that's sort of that pipeline that we want to start filling today, so that we are ready.
But I think, having said that, I think the point that I think Power should be, and I would think would be doing, is to actually record all the measurements as much as possible, especially in the millimeter wave space, and store it in a format that's easily accessible. And point out and put these questions so that they can say, sorry, we don't have this, but we can provide this. So anything and everything from physical layer and beyond that can be recorded and kept is useful.
Yeah, and I think that's exactly the point, is we need to be making it so that, in 3 years, the testbed's still going to be somewhat in its infancy when new arrays and new hardware is going to be very much available and very much mainstream, where if we put in the hooks for the information that we would want to have that we might not have available right now, then it's going to be a lot easier to go up onto the roof and just switch out the array. And make changes much easier, and then also have some parity with data. Even if it's not there, we still have the same format and everything like that. So so experiments are much easier.
Right. So the measurement philosophy, I think, has been imbibed by the team, and I think while we're talking about these platforms being deployed, the first sort of set of experiments, quote unquote, that the platforms plan on running is a measurement of the environment that they're in, and actually providing that. So a sample experimental workflow would essentially entail a user or an experimenter getting, either in simulation or models, and validating, quote unquote, your experiments on a simulation environment before actually going out and doing things in the wild, as any of you who's even tried anything to do outdoors, could attest to. So that's sort of the first thing that the measurement, what some of the formats are. I think I personally, again, am not aware of standards that sort of do exist. There is a SIG-MF for capturing the measurements. So are you talking about just developing? Yeah. So I'm talking about capturing base IQ samples essentially. And are there ways, easy ways, standard ways of capturing, storing metadata, artifacts?
What these guys were supposed to figure out.
Right.
And they have been funded now, so they better know the answers.
There we go. See, they conveniently ran out of the room.
They better, so this
okay, let's just add work onto them. That's what happens when you leave the room, right?
No, I'm not joking. I mean, I was in the back end of multiple teams, and this was part of, they should be part of the plan that, hey, what is the best way that we store this information? And I'm sure that there are formats, and I can't remember, but there are formats which can be used for storing this large amounts of data.
So that was discussed at one of our very early user workshops, not for Cosmos, but for the other platform, and I'm sure that's semi-applicable to this as well, but yeah.
So I actually had another kind of follow-up question about kind of the capabilities of the system. You'd mentioned, initially you guys are planning on looking at, 28 and 60 specifically, kind of like, say you want to do 28 versus 60, what does it look like to actually like change out those front ends? And, is it going to be modular such that, 3 years from now we say we want to do 140, what does that look like to change over to that?
Oh, absolutely. Extensibility, modularity, like the way the base RF design of the unit is intended to be, it is intended to be a swap in, swap out system.
But so I guess, where do you draw that interface line of the swap? Is that like essentially data converter samples? Like, is it IF?
IF.
Okay.
Yeah. Okay. IF. That's again today's thinking. And again, I don't want to speak for the team, but that's the latest information, at least I have from them.
I was going to actually bring us back to the question of if power would include over 100 gigahertz and what that would mean. From my standpoint, I think that the power testbeds actually give us a really great opportunity to be pushing the boundaries and pushing the limits of what the FCC will allow us to do with experimental licenses, and then having a somewhat secluded area that is still public that you can start deploying and start testing that you wouldn't have elsewhere. You wouldn't have a city that would, where you have a very close relationship with FCC to actually start deploying and start working out some of the issues of coexistence. That would be where I would think in 5 years, I would hope that this would go, is being able to swap that in. Go for it.
Nope.
So since you brought up the little issue of what FCC will permit, the real, especially if you talk, when you go above 100 gigahertz, I wanted to give a preview to my poster, the real reality is that NASA is a pain in the neck. NASA essentially has veto power over NTIA, and NTIA has veto power over FCC. And I would go tell NSF that NSF has a seat at the table along with NASA. And as far as I can tell, there's no sign that NSF is trying to moderate NASA's extreme protectionist goals in its seat at the table. And that, because in reality, if you want to do experiments, say above 100 gigahertz, you can't walk into Radio Shack and say, I want 170 gigahertz transmitter. You have to take what transmitters you can get. Otherwise, you spend $5 million commissioning a transmitter. That's the reality today that makes above 100 gigahertz very different than say 50 gigahertz. And there needs to be some pragmatic attention at NSF management to stop this harassment of R&D people by NASA, who are not interested in protecting their satellites. They're interested in forbidding uses of spectrum. Any use of spectrum their satellite uses rather than discussing whether the experiment threatens their satellite. I mean, I have a client in the university that was kicked out of 2 bands by NASA, and they were bands used by non-geostationary satellites, and it took a couple weeks of extreme effort to convince NASA satellites that are on the other side of the world do not get interference. NSF was on the committee that decided that. There's no sign that NSF was aware or took any action to moderate when NASA said 24/7 you can't use that band ever, when there was only one satellite to get it. This is a real problem above 100, 150 gigahertz, and NSF should try to get NASA and NTIA to focus on protecting systems, not forbidding any use of certain bands.
So, right. So again, none of us are from the NSF, and Akbar stepped out of the room. But what I can tell you is from interactions with the FCC, and just to build on Kira's point, the way this program experimental license has been conceived, this allows for experimentation. Okay. Well, we'll learn. We'll find out.
You listen to what you wanted to hear. But I can give you license application after license application.
That's been rejected.
Sure. And particularly program licenses exclude, the rules exclude band subjects in the US 246 provisions, which are these passive bands. So go read program license rules.
Sure. Well, we didn't encounter the 100 gigahertz and above because that's not in the purview. Right.
Above 100 gigahertz, the program license rules specifically exclude using those bands.
Okay.
And if you go get a regular license, you get the problem for a different reason.
Got it.
So, nobody wants to address it, but it
well, say that again when I guess Akbar comes here, because this constituency here can't really help you.
You could report,
Oh, he's back.
You should be, presumably you're reporting to him.
Right.
And the issue is, above 150 gigahertz, there are spectrum access problems anywhere in the USA, and NSF has to engage that.
Okay.
So my hope, and this is also, again, a naive hope, is that we can start using platforms like Power once they are off the ground to start addressing some of those and getting some backing and getting some voice behind it that we might not have had in the past. And that's, again, a very naive approach to it, but that is the hope, is that we'll be able to at least get some more eyes on it. It's been a highly publicized program, so hopefully we can get some more power behind it. Again, naive, I know, but.
I actually have kind of another question about kind of the FCC issues, and if you guys are going to look into this for Power. Is I know Facebook faced this with the Telegraph system. Is that even though it's really a point-to-point system, because they serve multiple users via time division multiplexing, the FCC called it a multi-point system, and that reduces your EIRP limit by 40 dB.
Right.
So there's this question of, what is a limit due to safety, and obviously we need to respect those, and what is a limit due to, they're just not actually interpreting the system correctly. So do you guys have a sense of what EIRP you guys are actually going to try and push out of Power?
This is trial by fire. So essentially, we get a step ahead of the program experimental licenses. So basically, what you see in the deployment area will be classified as an innovation zone, and essentially that relaxes some of the requirements that you have on the current ELS, experimental licensing systems, etc. So there's more leeway, and that's all I can say for now. Again, it's going to be trial by fire when we actually deploy these systems and we encounter these issues, but we obviously want to monitor them. You brought up Telegraph. I just want to at least bring out in front of this community, and you can just nod if you're already aware of this, but the 60 gigahertz Telegraph radios, Facebook wants to give those out to universities for channel sounding and for channel modeling efforts at a very low cost with limited support, et cetera, et cetera. Is that of interest to this community for 60 gigahertz channel modeling? Is that already, you already know how to do that? Do we have enough model information data? Because
potentially, but it remains to be seen what they can do if it's single beam and what's the characteristics, but that could be useful, and I think, and I want to so we have 15 minutes, and I want to get a little structure on. Suppose we were to say a community project where we wanted to have multiple teams carve out different parts of a project to develop a test bed, which could be complementary to power, feed into that, but maybe even if power didn't exist, how would we partition it? So one would be, it's like a natural partition would be, some people could be doing the antennas and RF hardware, some teams, or it could be partition one, potentially I'm thinking FPGAs and A to D could probably be one component, the hardware, and then maybe the networking folks could be another one. There are 3 teams. But then, in terms of other players, you mentioned, some technician at a company. What are the different components that we'll need to bring in, say, in a 3-year time frame? So one of the goals that I want to put forward which I'm going to put forward tomorrow, is that we have 2 more meetings of this RCN and the original thing, which is about a year from now. And so what can we develop? Can we develop a plan in terms of what we need, what we do, what will be the teams, what are the players we need to put in, and what resources we need to pull that off, which could go in parallel. Cosmos is the only one right now with millimeter wave, but that's not the focus. Maybe there'll be another platform focused on millimeter wave and terahertz, who knows? So what can we do going in parallel, and how would we break it up?
I guess one, I think, set of researchers that have been missing from this is packaging researchers. Like when we talk about hardware, I think the circuit design community is pretty well represented at these events. So I know Georgia Tech does a fair amount of research in millimeter wave packaging. There are a couple other schools, and I think getting representation from that community, people that actually know how to do high density interconnects with that operate at 100 gigahertz. Would be a community we really want present. And that would be a big piece to kind of doing a collaborative project.
And I think this is a part of Cosmos too, that right now what's happening is just like Telegraph, Facebook is giving these 60 gigahertz radios, but now companies are also beginning to provide even analog devices that has these evaluation kits or TI and so on. And so they are interested in it. And so are there any, I think Thiago was mentioning that, maybe ADI was going to provide some of the baseband architecture for Cosmos. Are there partnerships like that possible? And other than packaging, what about, who would build it? Even we have researchers, but at some point at the end you have to, ask someone to build the RF hardware, put it on a board. Right, so.
But that's
the easy part, I guess.
But that's actually, I would say, that's the hard part, because that's you're now, if you're trying to go to, and that's we faced this in previous projects. You're competing with the Apple, Samsungs of the world when you're trying to go.
No. You don't want to commercialize.
No, but even to build on, you're not talking. You're going beyond just dev boards, etc. Right?
No, it could be like a dev board. You take there are these 3 different wafer scale and then these surface mount components, and you could create an RF layout. We had a discussion a year ago, and then you could have some third-party company put those components onto a board. That's what he was referring to, wire bonding stuff. So do you want to have?
Well, so I think who the good companies are to collaborate with this is kind of up to what architectures you want to explore, and that so I think people have a pretty kind of, like you said, millimeter wave straitjacket about what 5G is going to look like. It's going to be hybrid beamforming. You're going to have partially connected arrays where it's really one beam per subarray and things like that. And so if you want to keep going down that road, then I think we can talk to Facebook about this stuff, and other people like that. They actually have pretty well integrated modules, but you're going to be straitjacketed to that architecture. If you want to talk about exploring new architectures where you do fully connected arrays and other things like that, you kind of have to get more to the principal components. And as far as that point, I think at 28 gig, I haven't done that much, but I think there might be some kind of principal component players. At 75 gig, which is where we've done all of the Hydra stuff, it's basically ADI. and that's it. And so, yeah, I mean, they've been very helpful for us, and they are actually, I think, interested in collaborating with academia. But I don't know how far they'll go as far as, trying to build up a larger scale eval board than what they already have.
So this is I mean, I'm trying to sort of, we're getting to the end of the time, et cetera, but some action items, some, distill down what we sort of went through in the last hour and a half. So I think this approach of, at least, Akbar, what you suggested about what is it that this community can do together, who the players are, sort of identifying. So this is sort of a fact-finding mission, I guess, where we need to put on paper who the players are, what expertise do they bring, and what are sort of a gap analysis of which are the pieces that are missing, engage our industrial partners, engage companies, sort of make those connections that we have from the expertise in this room, and sort of scope out what this would look like. That would sort of be one challenge, and sort of understanding where that falls into the roadmap of large-scale systems, plus what people are doing in their labs already with Hydra, with NYU Wireless, with other universities that are part of this consortia RCN, and then sort of presenting that roadmap to the community and sort of understanding, here is where we want to play, here is where we don't see either an industry player or a company doesn't really see the value because it's not part of their business model, it's not addressing a large enough community or customer need, but it's still important enough stepping stone for this community to get to the point where it gets interesting for other industry players. And I think that's sort of, I would take that as sort of the next steps to do as we spend the time. And you said you have, a year and a half, and a lot changes in that time. Breakthroughs happen. So just to be cognizant of, what will be, what's going to be feasible and possible, and sort of being very realistic of, if the suggestion is to do something in 2020, where will industry already have been leaps and bounds and, gotten how far, and where actually realistically we'll be able to build anything. Just want to put that out there. We should be cognizant of that too.
Oh no, I think I have no illusions about that, but I think industry will go in their specific directions where their vision is governed by 3 months. So academics have a possibility here to kind of think a little longer and also take on some of the hard work to build it themselves. Because we can't just wait for industry. With all due respect to industry, something we have to do ourselves too.
Akbar, can I just turn around another question for you on this kind of, if we were going to try and build something like this, what's the budget, right? Because,
right. Money is known to fall from the sky, especially in Washington, D.C. So no, listen, the point here is we don't have a budget. No, I want, what we are looking for is, hey, what is it? Are people interested? Is the community interested? Who are the teams? What is the blueprint? And what resources are needed? What would it cost? You come up with that. And we'll do our best to make it happen.
Yeah, well, I guess I just wanted to figure out how that fits into, NI does have a lot of platforms available, right?
Yeah.
And I think they are kind of expensive for us, right?
But but we cannot do everything with NIs. With all due respect to NI, there's also a LabVIEW straitjacket on it and other straitjackets. So and they don't have a networking part. So we want to be able, and we can bring in NI, people who are LabVIEW enthusiasts can go in there. We can bring, MathWorks stuff to processing to whatever we want. But I think it's an end-to-end system where we can play with it, modular at every level. Is it possible? Is it feasible? Are we interested? Is the community interested and committed to doing it? And what would it take? You create your blueprint. You create your what is needed and what resources would be needed, and then it's our job to try to make it happen in terms of providing the resources.
Yeah, actually to follow up this, right? So will we have this, what do you call that, power phase 2? So I think I don't know the status right now. I didn't follow recently. So initially decided to support 4 test beds, right? So right now there was 2, and they're going to have another call for proposals for the other 2. So
that's pretty much that. So that's round 2, which will fund again up to 2 more platforms. That will again follow that same RFP model that NSF follows, and that is anticipated to release by Q3 of this year with an award date of August 2019.
But let me just be clear that what I'm asking for is not in the purview of power.
It is not.
Power is about creating a large-scale testbed which is flexible, more infrastructure. And I think a single power platform dedicated to millimeter wave doesn't even make sense. Not right now. Maybe it might make sense, depending. Yeah. So this is a separate thing. This would be an effort where that effort will produce components which could go into any and all of the power platforms, Cosmos, Powder, wherever they have, because that is what they ought to be able to do. If there's any power platform that cannot support emerging millimeter wave technology, then we haven't done the job.
I was just going to make a closing thought that it is interesting, at least in this discussion, which it is a small group here, so it might not be representative of the rest of the community, but we did focus a lot on very low level and componentized discussions rather than applications that could be enabled by a testbed, which I think is a very interesting space and maybe is reflective of where we are in the community. But is something to I guess keep in mind as we do look at other MRIs, CRIs, and power that we might be a step before really application-based needs. That's a good point, that we may have self-selected into a group of just talking about that. So that's a very good point.
We have made tremendous advances, but again, it's not the end of. It's not just an engineering challenge left. There are a lot of things which are not solved, and millimeter wave and higher frequencies will have similar challenges. So I think these kind of test beds and thinking about them could be very interesting, and it is complementary to what power can do. I think there's a lot of misconception, not a lot, but misconception what power is about and
absolutely
what other things are.
Right. So the one thing I think, again, we can wrap up any time here, but just thinking about for the partners that you mentioned, these are what's the value proposition? What's the why would they come to the table for an initiative or a program or to set up a blueprint for? The one thing, again, just in telecom, mobile communications world, this whole notion of open API, open interfaces, openness has sort of, taken forth. So I think if we jump on that, if we piggyback on that sort of stream and frame this conversation around this openness aspect, I think we're, much more likely to get some traction. So to move it out of just the technical domain, I think we have to put our own hats on what is that partner going to bring, or what are they going to benefit out of this flexible millimeter wave platform on their end. Because at the end of the day, if they don't see any value for them, it's going to be hard to get them to the table. I just again, things to consider, not. And we felt that with power as well.
I agree. I think that, but I feel that if enough. So we are looking for people who are interested in solving the technical problems. Okay, and I think the community has enough bandwidth to collectively solve these problems.
Yep.
And we have enough resources so that we can tap them to do the things that we cannot do, like wire bonding that easily or whatever.
Yeah.
And I think we can do this even without having big players come to the trough, so to speak. That's what I feel. And I think there are examples. Hydra is one example. What we were able to do is one example, and other players too. So I think this is possible. It's really up to the community how much are they really interested in making that happen. And the value proposition is going to be the greatest for the community itself, and then, it might open the eyes of the industry too.
Yep. Okay. Yeah, no problem. Thank you again for those who participated, and obviously we'll gather on our notes, our thoughts, and present this when we do a breakout then. Thank you.
Thank you very much,
No problem.
Manu. Thank you for everyone. And yeah, we will have a readout tomorrow, and this is, it's a very important readout because the rest of the groups missed out on very important discussion.
Right. Thank you, guys. Thank you for participating.
I'm very happy to be here to talk about 5G millimeter wave, and I'd like to cover 6 points. First, I thought you might enjoy kind of a backstory of what happened and how my students and I figured out that this 5G millimeter wave would work, and some of the trials and tribulations we went through and some of the discoveries we came up with back about 4 or 5 years ago. And then I thought I'd present how those differences have kind of developed over time and how the 3GPP global standard has evolved in the area of channel modeling. And I thought I'd do some quick comparisons, because it turns out that the channel model is vital to comparing and testing. And we found some distinct differences, but because of the breakneck speed of this development for 5G new radio, probably the fastest standard development in the history of wireless, is 40-year history, to move up an order of magnitude of frequency. I thought that'd be interesting. And then I wanted to look at some real world issues and some things to consider in the area of hybrid beamforming, comp, and development in general. And then I thought I'd touch on the trials, actual update of what I've heard from industry leaders who are actually doing the trials and what the results are. And then finally, I thought I'd look at some things that we don't often talk about in academia, but is very important to the development of new technologies like the internet, like millimeter wave wireless, and that is the regulatory framework and some of the things the FCC is doing to help speed the deployment of millimeter wave in the US. And these kinds of activities will probably be echoed around the world in other countries. And then I'll conclude. So this curve, it was really interesting. Yesterday, a number of presenters talked about hype and where things are and what's real and what's not. And this is a very useful curve called the Gartner hype cycle. Gartner's an information, kind of an analyst that's very highly regarded in the technical field. And this is the Gartner hype cycle curve. They publish it every year. And on the x-axis, it's cut off on this slide, but on the bottom, you have on the left the technological trigger. When something is triggered by a fundamental discovery or a basic new issue that's come up that people haven't thought about before. And so on the left, you have this innovative trigger. And then here at the peak, this is maximum hype. And then you go in time a few more years, and then you fall into this trough of disillusionment, where all the hype seems like it was overblown, and it's actually not going to work well. And then as you go to the right, you kind of hit this slope of productivity, where people get over the disappointment and then just get to work. And then here you finally taper off to where it really becomes real and productive. And this is basically the utopia. It hits mainstream and everyone wins who stayed with it. And you can see here we are at the 2017, maximum hype was deep learning and machine learning. And all of you in electrical engineering know that your enrollments are going down in the hardcore electrical engineering because everyone wants a job in deep learning, machine learning, and all the salaries are there for all the stuff. And now pundits are saying, what is everyone going to do in 2022 when that entire market busts? So we're at maximum hype now, and if you note the color, it says, well, in 2 to 5 years, it'll actually start being productive and on the slope of productivity, but right now it's full hype. What's interesting is 2017, 5G wasn't yet quite in the maximum hype cycle. It had 5 to 10 years to go before it was real, so I suspect in 2018, 5G will be here in the peak of maximum hype, and then maybe machine learning and deep learning will fall off. And then it'll go through a trough. But what's interesting is autonomous vehicles, self-driving cars, right here near the maximum hype in 2017, and it's still a lot of hype. And then you have the terrible accident with Uber, and it starts heading down into the trough of disillusionment. But it's always interesting to look at this. And you know, it's good to see 5Gs here, and even business analysts, which don't always get it right, are saying 5 to 10 years. So they're saying 2022 to 2027 is when 5G will be building out. And I say that's probably closer to 2022 than 2027. I'd say it's probably 2020, 2021. But that's always fun to show. Now, how did we get here? How did we get to millimeter wave? We have NSF doing these workshops. We have the FCC making spectrum. We have probably tens of billions of dollars being invested around the world in various areas of 5G, even when 4G is still building out. 4G is an amazing generation of technology. It allows smartphones and applications like Uber and real-time video, and probably some people out there on the internet watching the real live stream or watching this on 4G. Well, here's how it happened, and I thought you might enjoy the backstory. I was at UT Austin and had done measurements at 38 gigahertz around the campus. In fact, let me go back 10 years earlier. At Virginia Tech in 1995 and 1996, I was looking at 38 gigahertz. I actually published a paper on what hail and rain do to fixed links, because this was before the LMDS, the CLEX, the idea of independent local exchange carriers putting up millimeter wave. Companies like Telligent went public at unheard of valuations in the late 1990s, and a few years before that, I was showing that you could do millimeter wave communication with huge bandwidth, and that weather wasn't that much of a problem. I was doing that at 38 gigahertz. But it became very apparent to me that the semiconductor industry back in 1995 just couldn't make the devices cheap enough, and we didn't really have the internet yet on cell phones. So the idea was way too early. So I kept the equipment in mothballs, always checked it out every year or two to make sure it worked. And then in 2011, as WiGig and wireless HD in the 60 gigahertz band for Wi-Fi was ramping up, I said, now's the time to go mobile. So I did measurements at UT Austin in 2011 and actually saw amazing coverage, non-line of sight coverage, which really surprised me. And when I came to NYU, they said you could get on every roof, because I said, if I'm coming to NYU, I want to make millimeter wave tests and show the world this can work. They said, okay, we'll let you get on the roof. They don't like to do that generally. But so I had rooftop access in New York, and I figured if we could make it in New York, we can make it anywhere. And so we put base stations up in 2012 and had a team of undergraduates, freshmen. They just finished their freshman year in college from the CS and ECE departments. And they worked tirelessly, and we made measurements all over Washington Square, on the business school rotunda, on the courtyards, went all around the streets of NYU. And lo and behold, indeed, it was working, and it was working really well. We made a channel sounder that used a sliding correlator method so that you could get very good dynamic range, 140, 150, 160 dB path loss, with very wide band, 800 megahertz RF bandwidth, yet you could get the advantage of time compression so that you could get the multipath, but you'd use a dilation, time dilation, use a sliding correlator, so you get these large link margins with relatively low power. So we're using 1 watt of transmit power at 28 gigahertz, 800 megahertz bandwidth, and getting very comparable base station-like ranges, in fact, much less than what commercial base stations will use. And we published these papers in 2013, and I'll tell you a little story about those later, but the bottom line is we started to collect huge amounts of data. We measured Brooklyn. We measured where you walk coming into this building and on the courtyard of Brooklyn. We had huge amounts, terabytes of data over the next few years. And one of the amazing things is we collected all this data using directional antennas. There's a channel sounder right out here running at 140 gigahertz that my students are using, very similar architecture. So we would just meticulously scan with directional antennas. And what we quickly saw is that with all this directional data, there was a lot of confusion. How do you process all these little narrow slices of received energy over azimuth and elevation in different locations and make sense out of it? How do we do an impedance match or a conversion to language that the wireless industry would understand? So here's what we realized. The entire wireless industry in 2012 viewed the world as omnidirectional at the handset. In fact, the entire wireless world viewed wireless in general as kind of omnidirectional. A base station, even if it's sectored, was kind of viewed as an omnidirectional antenna, and a mobile was viewed as an omnidirectional antenna. And so when I go around and tell people in 2011 and 2012, often I was scoffed at when I said millimeter wave would work. I realized after collecting all this data that people were misinterpreting a common law which is fundamental to wireless, which is Free's free space equation, this equation right here. And what I realized is the whole world was looking at Free's free space equation, which tells you the received power over the transmitted power is equal to the product of the gains of the transmitter receiver antenna times this lambda squared over 4 pi d squared term. What I realized is everyone was thinking that GT and GR is 1. Unity gain, omnidirectional. And so what I realized is, my gosh, what we're doing is when we use a directional antenna at the transmitter, it's not 1, but it's AE, the effective aperture. It's kind of like the physical area times 4 pi over lambda squared. And what we're doing is we're canceling out the lambda squared in the numerator here with a lambda squared in the denominator there. And so really we have the gain of the receiver antenna over d squared. So everyone says, gosh, we have this terrible higher loss at millimeter wave, because as lambda goes down, down squared is up, so the loss goes up, all right? So everyone views the loss as being greater at millimeter wave, but our data said it wasn't. And I knew from this formula it wasn't. This is the biggest misconception still to date. And this is why I want to bust this myth. Millimeter wave is better link margin, more received power than we've ever had in wireless. And here's the math. People, at best, would figure out, okay, if I use a directional antenna, I could at least get rid of one of these lambda squareds, but I still have the 1 over d squared loss. But here's what happens when you use both the gain of the antenna and the receiver. You get a lambda squared in the numerator, you get a lambda by 4, a lambda squared squared in the denominator. So you basically get a gain. You actually get a gain from the antennas that can beat the d squared loss. In fact, if you use a constant physical area on the cell phone and a constant physical area at the base station, that is A sub E stays constant, and you change the frequencies in both these terms, you get a square increase when you go higher in frequency. And this is why all the world is surprised and shocked. The trials are better than we ever thought. Well, of course, because you get a much better link when you keep the area the same but go higher in frequencies, because you're basically getting more focus. And the math shows it, but the world doesn't even still today understand it. In fact, let's look at the simple case where maybe you just put gain at the antenna and you keep the receiver shrinking as you go higher in frequency. If I keep the receiver on the order of lambda, that is A sub E is lambda squared, look at the gain of the receiver. Lambda squared over lambda squared is 1, and I get a 4 pi term. So basically, if I keep the transmit area constant as I go higher in frequency, and the receiver gets smaller and smaller, which is how the world always thought of it. They'd always say higher free space loss at higher frequency, because in their mind, they don't realize that they're shrinking the antenna as they make that proclamation. But if you keep the receiver shrinking, but the transmitter constant, the 4 pi squared cancels out, the lambda squared cancels out, and you get the same received power over all frequencies. So at worst case, if you shrink the receiver, you still get the same path loss. Now, I'm not counting weather or hail or fog or foliage or trying to get through building walls. But the bottom line is in free space, you actually get better signal-to-noise ratio. This is a fundamental result that the world is still trying to grasp, but the transmitter-receiver area, if it stays constant, if you use the same real estate on the tower and in the handset, the received power is greater at higher frequencies than lower frequencies. Now, how do we figure that out? How did we prove it? We had to do a lot of processing, and this paper in GlobeCom 2015 has kind of become the standard by how everyone processes this directional data and tries to put it in a way that we can all understand, and particularly what 3GPP understands. 3GPP had always made omnidirectional path loss models. You put the gain and the antennas on after their path loss model. That's how all the generations of cellular developed. But we figured out that it's vital to get rid of the gains in a way that's fair to what's happening. That previous slide is when you have a direct link, kind of bore site aligned transmitter and receiver. When the bore site is aligned, that's a very special case. It's not a scanning receiver, it's not scanning beams, it's when you've done all that hard work and now you have the link. But in the real world, in statistical channel modeling, when we're trying to develop systems, we don't care about knowing where the exact link is. We want to know what happens for any case. And that's what the omnidirectional model does. So we figured out how to process all this data regardless of the antenna gain so that you could rescale everything to an omni model and then change that back to any antenna pattern you wanted. And that's really tough. And 3GPP is still wrestling with that. And here's some of the fundamental things we found. While 3GPP was rushing to make a channel model so it could develop 5G new radio, they were really doing it without very many measurements in the world. They had our measurements, which we provided and published aggressively so they could see it. And we helped them build channel sounders, our industrial affiliates. We worked closely with them, gave them software, hardware, told them our vendors. So a lot of the channel sounder you see here at NYU was reproduced very rapidly by teams of engineers all over the world, the companies that build the 3GPP standard. They went out and found the same things we did. They proved it to themselves in 2014. And we launched the Brooklyn 5G Summit here as a place, a melting pot, for all these people to come together, to bring the FCC, to bring federal regulators, so they could see what was happening. We hold that every year in April. And what we found is that, remarkably, the channel model that had been used for 2G and 3G, which was this floating intercept model that was standardized in the 3rd generation and 4th generation 3GPP standards, used these parameters alpha and beta that had no physical significance. But when you get to millimeter waves, because it's very site specific, it's vital that you have a physical significance to your channel model. Otherwise, you can't make sense of what's happening with different directional antennas if you're on board side or if you're not. And so what we proved is that if you used the old 3GPP models, you could get these really bizarre slopes for path loss, which were very specific if they happened to be measuring and a building was blocking it. But if you went over 360 degrees and you used this physically based model, which used a free space path loss reference at 1 meter, that is, you standardized everything to 1 meter, free space, close in, free space, you got an N value, a path loss exponent, that had significance, it had physical meaning. It went back to the original theory where n equal 2 is free space. In this equation, n equal 2 is the path loss exponent, that's free space, and n equal 4 would be a 2-ray ground bounce model, as taught in my textbook and taught in the 50s by Bullington. So we were able to show that there's physical significance when you use this very simple 1 meter universal free space path loss reference. And it was vital once you use the 1 meter path loss reference to understand directional path loss models, because n actually goes up. You get more loss in path loss exponent if your beam is not aligned. It's when your beams are aligned, and that's what we have to do in beamforming, align the beams, align to the best bounces, find the best multipath when we're scanning. That's when n goes down. So it was really important to have both directional path loss models and universal free space path loss reference. Now this met with resistance from a lot of the industry. 3GPP didn't want to use a 1 meter free space because they had software written below 6 gigahertz. So they kept on doing the ABG model. But they did concede that this was better for millimeter wave, and so it actually made it into the standard. Shu Sun and George McCartney, 2 PhD students, were able to get the CI model into the 3GPP standard. I'd never had grad students during their PhD actually get a 3GPP contribution. So that was pretty good, and an acknowledgement that the world was seeing that this is different. Now, there are other things that 3GPP did in the development of their channel model in haste. They basically took all the stuff below 6 gigahertz that were done with pretty much Omni or Omni-like antennas, certainly not with the beam width you need at millimeter wave, 10 or 20 degrees. They used broader beam antennas. And they basically took all the parameters for number of scatterers, number of clusters, time cluster, and brought that into the 3GPP standard. It was fast, it was quick. They'd all have a standard channel model to compare their algorithms with. Problem is, it was wrong. We had all these terabytes of data and we're processing it. And while 3GPP assumed there's 12 clusters and 20 rays per clusters, we were finding there's much fewer clusters. In fact, there's only at 6 at most, usually 6 directions, not 19. And usually these are random, depending on where you are in the streets of New York or Brooklyn, and not fixed. And this is a problem, as we'll see in a minute, because if you have fixed number of clusters or paths or diversity paths, that basically means you have to build that many RF receivers to get all the energy, or have that many chains. Or conversely, it means that your channel has much more diversity than it really does. Turns out that 3GPP and the people at it are pretty wise, because they knew that wouldn't do a whole lot on capacity, and I'll show you that it doesn't. You get on the order of 2 factor of 3 dB in capacity using the different models. But where it does come into play is how to build a receiver, and I'll talk that in a minute. So here you had industry using this ABG alpha, beta, gamma model, which had 3 parameters, alpha, beta, and gamma, which are just path loss parameters that have no physical significance. And we used the close-in reference distance model, which had only 1 parameter. 1 parameter, this value of n right there, the path loss exponent. So 3 parameters versus 1 parameter with virtually the same standard deviation. In other words, the ABG path loss model was oversubscribed in terms of number of parameters. And that's why you got these really weird looking curves in the ABG model if you happen to specifically measure one particular angle at one particular building or had one group of buildings blocking your measurements. Very much measurement dependent in ABG. The CI model, close-in model, is much more accurate. And it used this free space anchor at 1 meter and 1 gigahertz. Now, why 1 meter? 1 meter is pretty much in the far field of most millimeter wave mobile devices. But here's the other reason why 1 meter. And I never really expressed this till today. 1 meter wavelength is 300 megahertz, right? All the millimeter waves way above 300 megahertz. In fact, UHF cellular started above 300 megahertz. So lambda at 1 meter is 300 megahertz, is a frequency much lower than we use in millimeter wave. If you just put a lambda of 1 here, everything cancels out, and you see the point I made earlier immediately. If lambda is 1, you can immediately see that with lambda of 1, the gains, the a sub e squareds come into the numerator. And so using a lambda of 1 meter, you very, very quickly can see the fact that your gain increases by the square of the frequency when it goes up. Another reason why is if lambda is less than 1 meter, you also see that very quickly. If you put a lambda less than 1, you get a less than 1 squared over a less than 1 to the 4th. What's a less than 1 squared over less than 1 to the 4th? Much, much greater than 1 squared. So again, you see that the gain's very quick. So this 1 meter has very nice intuition as well as being accurate. And so we also noticed in these field measurements over 28, 38, 73 gigahertz, now 140 gigahertz we're measuring, that while the industry and a lot of common models want to force the joint spatial and temporal cluster definition, we found that field measurements don't do that. See, here's what the channel model is in cost in 3GPP. They force an assumption that any multipath that happens in the channel model are both spatially and temporally joint distributed. That is, any multipath delay that arrives at a certain nanosecond delay must come from a particular angle. They force that joint distribution. That the angle of arrival, it happens to be also coming from a time delay. But we found in the streets of Manhattan that I could have a multipath at 10 nanoseconds coming from a nearby building, and at the same 10 nanoseconds, could have something coming right behind me from the other building. So in that case, you have 2 rivals at 1 time delay coming from 2 different angles. So the joint spatial temporal model used by 3GPP and in a lot of textbooks is not what you see in field data. Actually, in field data, you see time delays coming at many, many different delays from the same angle. Maybe it's a building here, 300 meters away, and another building 500 meters away that's taller. The energy will still come from the same angle, many hundreds of nanoseconds apart. We saw this. And so we defined this definition of clusters, where you have time clusters, but spatial lobes, where there are no more than 6 spatial lobes, and there's many time clusters, we have the distributions, we saw it time and again, we processed all this data, and we call this the a time cluster spatial lobe approach. Now, the energy in space always has to be equal to the energy in time. The area under this curve is the area under that curve. Space and time energy is the same, but it's different. It's a different approach, and it's a statistical approach. So we made this simulator, NYU Sim, came out in 2016. FCC was interested in it to validate some of the things they were seeing. In fact, the FCC followed our work very closely. They would call me. Michael Ha would come up to our Brooklyn 5G Summit back in the early days, before the world believed. They really wanted to see if this was happening. And indeed, they saw it was real. They used the simulator. And it basically recreates all the measurements we've made. So you can get free, open source, downloadable in MATLAB, this simulator, NYU Sim, which replicates all of this. And here's some of the interesting outputs of NYU Sim versus the 3GPP channel model. Let's look at the eigenvalues of HH Hermitian, which is basically telling you the energy or the diversity paths, the rank you have of the channel. This is the famous Raleigh channel, which is why OFDM evolved and became vital in all 3G wireless. The beauty of having narrowband channels, narrowband tones, is why OFDM is so great. And we talk about it in Chapter 2 of the millimeter wave textbook that Robert Heath and I wrote with our PhD students. This is why OFDM happened. This is why we love it. OFDM is a bunch of narrowband channels. Narrowband channels are flat fading. Flat fading in any mobile environment is Rayleigh. And this is why we use it, because you can use MIMO in OFDM. Because you have all these narrowband tones that are all fading Rayleigh. That's the Rayleigh channel. In wideband channels, though, NYU Sim and 3GPP, here's what you have when you basically demodulate and are looking over wider bandwidths. NYU Sim has fewer higher ranked eigenvalues or channels. So we have like 3 main channels. 3GPP predicts 4 or 5 channels. So you can see that the rank in 3GPP assumes there's more diversity. The largest 4 eigenvalues you can see here. NYU Sim has fewer but larger eigenvalues. 3GPP has weaker but more eigenvalues, and this is going to lead directly to hybrid beamforming results, digital beamforming results, diversity results, signal processing. Now, we just published this paper last week. The new proof just came in, and this is kind of the definitive discussion of all of this, all of the channel models. And in this paper, we look at hybrid beamforming, we look at single-user MIMO, we look at multi-user MIMO, and we look at comp for a 3-cell base station from 3 to 12 users. If you're working on beamforming or comp, this is a remarkable resource, just went online like 3 days ago, and it's basically a culmination of everything I've just talked about. The NYU Sim versus 3GPP and the result of receiver architectures and hybrid beamforming and comp. And I want to go into some of the results now of the 2 PhD students, George McCartney and Shu Sun, who helped bring a lot of these ideas to the world. So we've heard a lot about beamforming. We've heard, and I need to finish up pretty quickly here. We've heard a lot about beamforming. We've heard a lot about digital beamforming. And one of the interesting things is analog beamforming, which is right now being used in most of the trials, is very simple. You have a single RF chain. You basically have RF precoding a network that's going to do RF distribution to the antennas to basically get fixed beams. Digital beamforming is kind of the holy grail. This gives you maximum flexibility. You can put a beam wherever you want with amazing fidelity based on the resolution of your array. The problem is that you need a lot of DACs. You need an RF chain for each of the antenna elements, which right now, today, is expensive and will be expensive probably for 3 to 5 years. So why hybrid beamforming? Hybrid beamforming basically takes advantage of baseband precoding and RF precoding, RF distribution, phase shifters, to kind of find the best of both worlds. You use a large number of antennas so you can get good array fidelity, but you can use fewer RF chains, less cost, less power, and it's very, very close to the spectral efficiency in a real system simulation that you get with digital beamforming. That is, you're like within 5% of the spectral efficiency if you go to the effort of all those digital beamformers. And so you start using beamforming with various approaches of comp, where today's cellular, we use a lot of these single cell and multi-user MIMO is where a single base station will send to multiple users. But comp is something that we've looked at in 4G, a lot of complexity. And so we wanted to kind of bookend what happens for a single user MIMO case, a multi-user MIMO case in a single cell, and what happens if we ever get to comp with best beamforming. So I'll just quickly give the highlights of the work. We all know what 4G and 5G is. And so basically, we're going to look at non-comp and comp using different beamforming architectures. And they're discussed in that paper I just mentioned that came out 2 days ago. And I think these are the world's first results of comp. First, we've got measurements we made on this campus. This is the map of our campus. And George McCartney, for an entire summer of 2016, took very high resolution angle measurements, thousands of angular measurements from all these base station locations, and received them at the other locations. And we built this database, and the bottom line is, even with a high density base station cluster, there aren't that many places in a mobile system where you're going to have a lot of interference. That is, maybe you could get 16% of the time in full interference, twice the capacity using comp. But most of the time, 43% and 35%, that's like 80% of the time, you rarely get capacity gains using comp. In fact, Shu Sun looked at the simulations, which are in that paper, and found the same thing. And by the way, these bits per second per hertz are kind of hypothetical. You know, it's hard to get 10 bits per second per hertz with modulation, but it's kind of a reference, it's a benchmark. If you look at this going 3 user and 12 user per cell, the NYU Sim channel model predicts more capacity by about 25 to 80% more capacity. But the bottom line is comp's not going to give you a whole lot. This is baseline with a single cell, just forming single beams. This is the best you can get with signal leakage noise. Akbar, one of your students, helped kind of develop this idea. And you can see that at the 90% point, you maybe get a little bit more using comp, but not a whole lot more bits per second per hertz. In fact, knowing this, the industry is now building out these trials, and they're not looking at comp, and probably won't be probably won't use comp, because millimeter wave is not interference limited. It's basically link limited. You don't have a lot of interference, which is what George's work showed. So here's what's happening in trials real quick. There's a bunch of trials in Texas, largest 5G trial at the silos. Attenuation by tinted glass is major. They have launched 5G already. There's 1 gigabits per second download speeds, less than 10 milliseconds latency, reported at 15 and 20 gigahertz. This is before the 5G NR. And they're going to be using standalone pucks that take the outdoor signal from fixed wireless and distribute it indoor. Verizon's going in 11 cities. They're going better than they ever thought they would. Well over a gigabit per second, 10 milliseconds, and again prior to 5G NR, which just came out last month. So trials are working. They're really excited. Intel's got a product which they call the mobile access unit, which they put right at the window and the wall. They take the fixed wireless access signal from the base station of 5G and then redistribute it using a hockey puck. Here's what it looks like. This is the wireless remote radio head. The station comes in from 5G, the fixed wireless access. It's then redistributed. They're getting 3 gigabits per second. And then the FCC, trying to ramp this, created this rule just recently, a few months ago. They asked our opinion. We gave it to them. We said, look, you've got to make it easy for the wireless companies to deploy. You've got to make it easy for them to get on lampposts. Right now, cities and municipalities realize they can charge money and hold up the permitting process for carriers that want to deploy small cells. They see this as a revenue grab, and the wireless carriers view this as a tax on mobile broadband. You know, if you're going to call it a tax, call it a tax. Don't hold up our business. So the FCC is trying to remove unnecessary barriers and trying to make it possible for small cells to be legally deployed without onerous rights. And we asked our industrial affiliates before we talked to the commission, what do you need? What do you want to see wireless happen quickly at millimeter wave? And here's what they said. It's got to be fast. They said the small cell order is a great first step, but we really need more mid-band spectrum, and they want these auctions happening. FCC listened. Auctions are happening this November, which I predicted back at the Brooklyn 5G Summit. Even though the FCC was hedging, they said it'll be next year. I said it'll happen this year. It's happening this year. You need to give them right-of-ways. These companies are desperate to get right-of-way on poles and lamps. They want to avoid zoning. They have to be reasonable. They can't put up ugly things. But this is a big deal. And then Michael Marcus, who's here, has helped propel this 95 gigahertz and above spectrum horizons. So in conclusion, 4G LTE, which we have today, is morphing into 5G. You won't see comp used. You will see multi-user MIMO and comp. Comp only gives you about 5 bits per second per hertz greater than uncoordinated. Is it worth it? Read the paper. And carriers have to decide, because right now I don't think it's worth it, certainly in this early stage. Maybe in 6, 7 years it'll be worth it. Interference is so much less of a concern with these directional arrays. That's why comp's probably not going to happen anytime soon. The myth busting I showed you shows that there's greater signal to noise ratio, greater data rates, and greater coverage as you go higher in frequency. Sans the weather, but over a few hundred meters, rain's not an issue. I gave you some recent testimonies and stressed some key regulatory needs and the auctions that are now happening. And in conclusion, millimeter wave really is the tip of the iceberg. The FCC's gotten out in front on these issues, but countries all over the world, primarily in Asia, are working very, very rapidly on this. Finally, I want to thank the NYU Wireless Industrial Affiliates program. Qualcomm is here, Osgay. All these companies are great partners. We really work closely with them and take their inputs to the FCC. It's very harmonious and symbiotic. They hire our students. I want to thank them. And I want to thank my 3 current PhD students, Yunqiao Xing, Ojas Kanheri, and Shihao Zhu, who are exhibiting some of the stuff as they kind of follow in the footsteps of George and Shu in trying to tease out the knowledge. Thank you very much.
Well, thank you, Ted, for a very exciting and energetic. This is one of those talks where you almost need a debriefing. Because with all due respect, not everything was correct. So, students take your words correct, seriously. One question I have for you is comp. You said, hey, it's not. And we were talking to one of your colleagues, Shiv, I don't think he's here, that, blockage, if you think in terms of latency, right, the other elephant in the room, that's where comp may be useful. Interference is not the issue, but suppose it gets blocked, you may want to use another one.
I didn't mention in the talk, we considered that. We have a blockage model. We have a human blockage model. We published it a year and a half ago. It's a 4-state Markov model, and that was included in the analysis by George McCartney. George actually, and his PhD thesis is open access. He's working on a journal paper. So we considered that. We considered human blockage in the NYU campus layout. And still, even with human blockage, there was not that much outage. And remember, he has all these beams. And the human outage is very slow. You can predict when the person's starting to walk. And so if you have all these beams, you can basically look and quickly make another beam and rescue. We have all that data and showed that you could quickly get away from the blockage and point somewhere else.
Yeah, well, that's, okay. So, it's not just the physical layer, right? It's the networking layer that has to talk to it as well. Okay, well, any other questions?
Dan has a question back there.
I just wanted to follow up on that. Would you expect that statement to still be true above 95 gigahertz?
That's a great question. Will that still be true at 95 gigahertz? I believe it will be. I think you have some answers in some of your work, but yes, I believe still above 95 gigahertz, you will indeed be able to do the same thing. Look, order of magnitude of 30 gigahertz is 300 gigahertz. Channels don't change that much over an order of magnitude of frequency. In fact, if we used 7-degree beam widths 10 years ago and measured the channels for 3GPP, we would find very similar things than we're finding today. It's just now we know the technology will allow small form factors with very directional antennas. The industry wasn't thinking about that 10 years ago in a cell phone. So yes, I believe it'll follow.
I would, so directionally channels become sparse. I think that's one of the reasons why hybrid works and why interference is not there. And I think so channels do change in that regard, that you're not going to be having this diffuse, rich scattering. That was your Rayleigh curve.
Well, it's a very good observation. He's right that in general it becomes more sparse because diffraction goes away as you get to these higher frequencies. The diffraction is based on the physical world. However, I did measurements There's a paper like back in '96 with a giant horn this big at 2 gigahertz, and I found similar sparsity. I published it, no one cared.
That's narrow beams.
Yeah, exactly.
Narrow beams is the thing.
My point is when you go narrow beam at any frequency, the channel by definition
My
is
point
sparse.
is that if you go to very high frequencies, any damn antenna is narrow beam.
Yeah, well, yeah, because you have to physically make it.
You can't make it broad.
That's right.
So, okay, well, any other questions before we arm wrestle?
Well, Ted, thank you so much for a very inspiring and informative talk. I have a bit of a technical question. This is related to the clustering model that you have, and specifically to the channel coherence time in a beamforming environment. And just to give you a background, I'm trying to figure out how often one has to do tracking and kind of changing of the beam. So how long does the channel maintain its coherence time under mobility, and how would the clustering phenomenon impact
Great question. Great question. And Shihao Zhu, one of my students, is actually working on this idea of spatial consistency. We have all this data, and we're going to put that model in NYU Sim. We don't have it in yet. The bottom line with coherence time is it's roughly related to the inverse of the Doppler frequency. So basically, what's the Doppler? And when you look at the Doppler at millimeter waves, it goes up by a factor of 10 from where we are in today's cellular. So in a high-speed car today at cellular, you've got Doppler of what, about 200 hertz? So you can imagine up at millimeter waves at a high-speed car, you're going to have Doppler of 2,000 hertz, 2 kilohertz, which is going to be about half of a millisecond. So you basically have 500 microseconds while the channel is static. That's why packet durations of 50 to a couple hundred microseconds will basically be like a static channel. And by the way, that's a very short time, but you can get lots of bits through at very high data rates. So you're kind of looking on the order of fractions of a millisecond while you've got a static channel. And that's a lot of time. The overhead, I mean, we're going to take 5 milliseconds to kind of figure out where all the beams are. You can't go very far in 5 milliseconds on a track. So generally, the channels will be spatially consistent. 3GPP said spatial consistency is within a 15-meter grid. You know what? We made measurements that showed in a 5 by 10-meter grid, the average path loss really doesn't change. So that means the clustering's not changing. So if you figure in a 10-meter distance, whatever speed you're going, the channel's not going to change very much. In fact, we have a VTC paper in the workshop that Kate is heading up that talks about spatial consistency. So the bottom line is you've got 10 or 15 meters in general, unless you're going around a corner. You know, if you happen to go right around a corner in millimeter wave, you know, you're obviously going to change clustering because you're going to change serving base stations. But generally, you can think that as kind of a stationary region from what we've seen in the measurements. Does that answer your question?
I'll add to that, you know, I think a lot of people, this is another myth that things are moving too fast in millimeter wave, but we have to remember our sampling intervals are in nanoseconds.
Right.
That's large bandwidth, so it's in super slow motion. So you can track the hell out of things. So yeah, that is true. A shorter way of saying it, maybe. Oh, yes.
So besides the channel during a packet, right? You say the channel during the packet is constant, and so you can just use it as a static thing. But then when you go to the networking level, it's not just one packet. You may need to retransmit. You may need to schedule and decide when it's good to schedule transmissions. And if you know that your channel is going to be static for 1,000 packets or 1,000 slots, then your ARQ strategy, for example, would be different compared to when you know that every transmission is essentially IID. And so that knowledge, I mean, one can roughly say, oh, at these speeds and at these frequencies, don't worry, everything's going to be static for your single transmission. But what about, you know, the more complex scenario where you have multiple transmissions, you need to schedule, decide when to transmit. And so in that scenario, it becomes important to be able to say what is the correlation in time and in space for a multi-user system. And so I think we need measurements for that.
Yeah.
We need measurement for correlations, because now it becomes important. Now you've done the marginal statistics, right? The PDF of the signal transmission. Now give us the correlations, because we networking people need that.
Yeah, you hear that, Shihao? You hear that? That's That's your master's thesis. We're doing that right now, actually. He is going through all our database of measurements, looking at the track measurements we have, because we've made so many track measurements, and he's writing the correlation. Now, we've published correlations on receive fading envelope. In December of 2017, in the IEEE Antennas and Propagation Society special issue on 5G, you will see the correlation distance as a function of antenna of the received power envelope. So you have correlation right now on what's going to happen to the received signal. It's published and it's available. We have the mathematical models. The other thing is the clusters. There's not a lot known, but we're going to get that data. And we've got spatial consistency figured out to a first order, and we're going to put that in NYU Sim so that you can get that correlation over a track.
Debriefing is absolutely in order. So with all due respect, these horn antenna data is not indicative of the phased array narrower beam data that may be used. So we need some more different measurements in addition to processing the old measurements. I know you guys are getting better sounders, and they're going to be built, but
you always need more measurements.
And 20 degrees is too wide. That's not what the systems. We have to measure them at the resolution that they're going to be seeing, at the spatial resolution, which is still not being done.
More measurements are always welcome. We're using 7 to 30 degree beam with 72230, but you're right. Look, you need more measurements. So this is so new. The world doesn't yet understand this. And until you measure and see it yourself, you really can't understand it.
Absolutely. Let's thank the speaker again. Thank you very much.
Yesterday we had the 4th breakout session about signal processing and networking interface. Myself, Tanguy, and Ismail were leading the session. I started off by talking about, by recapturing the goal and motivation behind this breakout, being cross-layer open discussion with research communities in the intersection between Phi and Net. And specifically, we tried and challenged and refined the tools and methods used to conduct end-to-end millimeter wave research, focusing on the network simulator NS3 and some ray tracing thoughts. And then we tried to stimulate some discussions about other potential research topics related to this CSP net interface. So I started by talking about something that I've created in the last few months after the last workshop. As promised, I created this website, a shared website. It's a Google site where anybody interested can participate and edit and add thoughts and ideas. And as you can see, this is the structure. You have different pages, and we've, based on the 3rd workshop, NSF-RCN workshop, we've spotted some topics of interest. As you can see here, we have some MIMO channel characterization, some thoughts about error models and link to system abstraction, and simulation scalability and complexity reduction for channel simulation, millimeter wave channel simulations. We've had 3 WebEx calls offline between these workshops, focusing on these 3 topics with a bunch of people involved. We are 23 participants across industry, academia, NIST, research labs, and so on and so forth. So as you can see, the format is as indicated here. Every page has its own topic and a hyperlink to a Dropbox page where I upload recordings of the WebEx plus the slides of each presentation. So this is just so you know, and if you're interested, please participate, ask me to access. So related to yesterday discussions in general, the main topics that were also captured and discussed across the WebEx meetings in the last couple of months are as follow: channel models, ray tracing blockage, antenna partner orientation, hand rotation, phi abstraction, and simulation scalability. So we started off with a little bit of background on simulating the MIMO millimeter wave channel in NS3, both for 3GPP and R as implemented by NYU, and for IEEE 11AY as implemented by NIST. So this was an overview. Most of you are familiar with this snapshot, and this framework is the end-to-end millimeter wave module developed at NYU in collaboration with the University of Padua that got recently published in COMST in 2018. Where you can find all the details. Then we briefly talked about the channel generation procedures as indicated in 3GPP, which are step-by-step the ways we have in NS3 the channel initialization, the MIMO millimeter wave channel initializations with channel metrics, spatial signatures, complex values, and a lot of complexity indeed. We've also shown that we validated some of the optional features proposed by 3GPP in 38.900, like self-blockage, spatial consistency, and this is just to show the audience that this is what we have, and we would like, to get feedbacks and people, if interested, to tweak this or just use this because it's an open source tool. And then we've also talked about the synchronization that we've recently integrated, really following line by line the 3GPP guidelines in release 15 with SS burst periodicities and a very detailed OFDM symbol tracking based on that, and also showing that what we can do is not only 3GPP procedures, but also plugging our own measurements, the sounding, and basically get some TCP and higher layer performance evaluations. So this was my first part of the presentation about NS3 millimeter wave channels. Then NIST talked about their very impressive tool developed in MATLAB for the 11AY simulation in NS3 also. I want to stress this because we believe it's the right tool to do a lot of joint works. So they talked about this quasi-deterministic channel model implemented in MATLAB, which will also be released as part of the WLAN toolbox in September this year. And that's being used in conjunction with NS3 to provide this physical layer for simulating end-to-end 11AY, basically. And then Ismail jumped on stage and talked about some of their preliminary measurements with propagation statistics, beamforming, the effect of beam shape on angular spread through their ray tracing tool, and some modeling of blockage and multipath energy in the angular domain in vehicular networks. The second part of the presentation was about abstraction, physical abstraction, and this is where we've got the best insights, and I think there's a lot of space for improvements, joint improvements. As I mentioned earlier, it's key to simplify as much as we can the simulator, the channel part of the simulator, and try and minimize the complexity of the MIMO channel specifically. So I briefly talked about mutual information-based link-to-system abstraction, which is the globally accepted solution to do this sort of abstractions. So I got the audience to better understand what we have there. And specifically, the most important part is this. These are link-level AWGN curves used in LTE for the OFDM evaluation methodology. And what I've openly asked for is help or advice about implementing the new link level defined in NR release 15 to basically rerun these performance curves and refine our error model, because as of today it's based on LTE OFDM at 20 megahertz, and this is even it's just an AWGN channel. But I will recap in the end. So the other part was Nis talking about their error model for 11AY, which is indeed different, and they're working on this, also based on a MATLAB implementation that's part of the 11AD WLAN system toolbox. The last topic we've discussed, so basically just to recap, we've talked about channel, MIMO channel, millimeter wave, both 11AY and 3GPP NR. We've talked about PHY abstraction, and then as I stressed earlier, the importance of scalability. We've shown some preliminary results where with one single link, the bottleneck of the complexity is on the higher layers. The TCP and IP takes most of the runtime computation with one link. UDP traffic indeed is easier because you don't have congestion control algorithms. And then what we've shown indeed is if you start and grow the number of base stations and users, the bottleneck becomes the millimeter wave module. Channel metrics, interference computation. So what we've proposed and implemented already is some decoupling for the channel metrics to make it more runtime, but it's still very complex and it takes a long time to simulate multiple users and multiple base stations. So we're working on another technique where in collaboration with Nokia, we're discussing with Nokia because they're having very similar ideas. So we might end up doing the same together. They're very open to open sourcing this. It's down selecting some clusters to minimize the computational burden. So this was the third part, and let me now wrap up with this slide where I want you to see what are the next joint steps and a little bit of a call to actions. So link level millimeter wave simulation to improve and refine the PHY abstraction for millimeter wave end-to-end and R. Working together if you have ideas about this channel complexity reduction. I think it's an interesting also research topic. We could use technique, maybe machine learning, but it might be, we've tried and we don't think it's the right way, but if anybody has ideas, we're happy to sit together. Integrating and testing new channel blockage and rotation models, because it's such a modular tool, we can easily plug and play different models and compare. And this was assist to Ted's keynote where he talked about NYU SIM and comp, so maybe we can integrate all that and show the performance, the end-to-end performance differences when you plug these different models. And please reach out to me or to Ismail. I forgot to put their email, sorry, but it's enough to reach out to me for joining in future WebEx sessions that we will have offline between workshops. Just sit in, give ideas, get inspired, do whatever you want. There's a hyperlink here. You'll get the slides so you can click and get to the website. And please know that we would be happy to have you join the NS3 millimeter wave community, either 11AY or 3GPP NR. There's a lot of documentations and tutorials. The learning curve is not that steep, and we would be happy to help. Open source is key to acceleration. Thank you.
Thank you. So that's a great summary, Marco, great readout. A couple of questions. So one, and this is going to be really, and I want you to sit in front because you're going to be part of the panel discussion here. So the error rate performance was to actually maybe put it at abstraction of the PHY layer at that level into your NS3 simulations rather than implementing, that's what the goal of this link error model. Okay, and then PHY layer right now, is it still single beam in your implementation?
Oh, not at all.
Oh, you don't have? Because
No, it's multiple beams.
You can do multiple beams and multiple channels. Okay, well.
You can easily plug that in. Right now we're doing, you can easily do multi-user MIMO with the way it's implemented today.
Excellent. Yeah, one question I had asked you last Asilomar, I think, or some 2017, I don't know. Can you estimate latency?
Of course. Yeah.
So what's the shortest latency in reasonable scenarios that you've been able to get?
Oh, so we've shown, it depends on where the server is sitting, right? So when we do edge simulation, where the server is sitting pretty close to the user, we're able to show that thanks to the frame structure and our frame structure and the retransmission procedures, you can easily hit the 1 millisecond.
But that means that, everything is on the edge, all the information.
What's that?
All the information is on the edge.
Yeah.
So which the physical distance is maybe hundreds of meters.
Yeah.
So yeah, okay. So
yeah, so it's pretty easy.
offline.
And also through handover, because we've implemented this dual connectivity framework where you have sub-6 and millimeter wave. As soon as you lose the millimeter wave link, you can very quickly maintaining the millisecond latency thanks to these lean handover procedures enabled by this framework.
And then you also have the NR standard components in there, it seems like.
Yeah,
Okay.
highly customizable. Yeah.
Very good.
First, I'll say that I wasn't expecting to do this. Harish was supposed to be here. So we had three of us sort of leading the discussion. And I don't have the slides from the three. It was Pete Musburger from Ball. So he's in charge of developing their phased array, the 28 gigahertz new commercial sort of prototype that people can use to investigate development of 5G systems. And so he discussed the advantages, and this isn't on the notes here, this is just sort of the preview. Pete discussed the advantages and disadvantages of various phased array implementations, fully digital, hybrid, and more traditional sorts of phased array. And he really made the point that the business case needs to drive the decisions on what technologies to use. So and then that the decision on which type of phased array implementation to use may change as technology advances. So for example, people are using hybrid arrays right now. That makes the most sense from a business case point of view, but there may be a time in the future where the fully digital implementation of the phased array starts to make more sense. Harish, he's professor at Columbia, and then he also has a startup called Mixcom, where they're doing RFIC design. He touched on several different open challenges regarding which technology to use for 5G implementations, silicon or 3.5 based or hybrid types of technologies are all candidates right now. He also talked about which architectures to use to improve system efficiency. So the fact that the amplifiers are, need to be operated in very linear operating states right now means the efficiency is very low. That will also probably change in the future, but there are certainly technology or architectures that can improve system efficiency, technologies that can improve system efficiency. And so the choices that are made now are sort of the most safe to get systems up and out the door, but things are likely to improve over the course of the next few years, and we discussed that yesterday here also in the panel. And then, being from NIST, I discussed the role of measurement in improving models and reducing the need for digital signal processing, things like digital pre-distortion. So I gave a couple of examples on the use of measurement uncertainty to improve the nonlinear models that are being developed for transistor design. Showing that if we extract model parameters from large signal measurements, that by doing sensitivity analysis of the various extracted parameters can lead a designer to understand what the weak points are in the transistor model development. So for example, if you run something near compression or high current, you can see very clearly from the uncertainty or error bars that there are weaknesses in certain parts of the waveform as you're nearing compression. I also gave some examples on the use of channel measurements for directional array design. Based on our NIST channel sounder, we can synthesize an omnidirectional radiation pattern. We have a switched array that samples very quickly in the azimuthal plane. From that, we can synthesize an omnidirectional array, and then we can actually take the measured data and start synthesizing narrower and narrower beam widths, so that you could, a designer, an antenna designer, could see the effect of various beam widths, based on measurements in a specific environment. And then also talked about over-the-air measurements and how those can be used to verify the performance of devices and then to improve the performance of devices. So that's a big issue right now in the 3GPP, is the OTA test of the millimeter wave devices, because they need to be verified. The performance needs to be verified in sort of these 3D spatial channel models. And so I showed an example of a hybrid chamber that NIST has developed to create specific 3D spatial channel models, essentially in physical space, based on a reverberation chamber that's very heavily loaded with RF absorber on the wall, so essentially like an anechoic chamber, but then certain patches are left reflective to create the angular clusters of multipath that are specified in various channel models. And then the sort of key value added that NIST brings to this is the verification of these environments with the synthetic aperture techniques. So that was sort of the introductory comments that the three of us made. And then we had a very nice discussion, focused a lot on the beamforming arrays, which is not really my expertise, but was certainly the expertise of a lot of folks in the audience. And so the first question that we tackled: will fully digital arrays ever become a reality at millimeter wave frequencies? And as I mentioned, well, there's a lot of advantages to fully digital, so people are trying to head that way. The hybrid array is not as efficient in shaping the beam, but the hybrid array, I think this is the big advantage right now, only uses a few ADCs, and then of course one RF or fewer RF chains as well. So eventually, I guess right now, and Ted touched on this also, if the millimeter wave use case is primarily line of sight and maybe has 3 or 4 clusters, does it really make sense to use a fully digital array, or are we fine with just a hybrid array having 4 or 8 various beams that it can create? So that's sort of a fundamental question. Fully digital is quicker when it's used for the initial access, the discovery of the channel. So, ultimately there are probably advantages to using that. It may be, this is something Pete brought up, a fully digital system would likely be more difficult and complex to maintain in the long run, just because you have more of these moving parts, the active parts, the antennas, or sorry, the RF chains and the ADCs. Let's see, and then there was a discussion on this concept of open loop beamforming, where you don't monitor channel conditions in real time. You just assume that the coupling between the elements is constant and that you have adequately tuned your array for, to minimize blind spots. Closed loop beamforming, you can compensate for non-idealities like coupling and unexpected scattering in real time, but at the expense of power. So power is a big issue for the millimeter wave systems and the system complexity in terms of the long-term, maintenance and usability of the system. So it was argued that open loop is generally satisfactory, and if a few elements are operating in a nonlinear state, like because of coupling, signal conditions, or something like this, it won't be all of them, and so and that tracking and blind spots don't change that rapidly in practice, so that gets to this idea of the coherence time of the channel, and that we're really mainly tracking 3 or 4 clusters at a time. So let's see, for now the cost of a fully digital array might be high and the reliability might be low, but that's today. So the potential is very high for using fully digital arrays if lower cost ADCs could be produced as technology advances. And so there was a lot of confidence in the room, I would say, that fully digital will be a reality at some point. I mean, everyone pointed out that right now in the sub-6 region. We have fully digital arrays, and 10 years ago, you never would have thought that could be possible. So one of the questions that Harish brought up is, is 5G a large enough business or commercial entity to drive the development of these low-cost ADCs? And so perhaps other applications might drive the development. For example, if Internet of Things really takes off, and in the industrial environment, or these other very high reliability use cases like automotive applications, perhaps the millions and millions of nodes that would be a more likely driver for the development of fully digital arrays. Let's see. If the applications are primarily line of sight, why use beamforming at all? These are questions that came from the audience. Why not use mechanical systems? And the answer there is that right now, it's performance versus cost. So operators do not want this first generation of 5G to fail. Phased arrays are proven. We know that they can work in this hybrid technology. They're cost effective. So that's what is going to be used right now. Let's see. Acquiring channel state information. Is there a high overhead for training fully digital arrays? In mobile multi-user applications, fully digital is more powerful, and I think Sandeep had a paper to demonstrate that. To make digital arrays more cost-effective, you could reduce ADC resolution. Okay. All right, on to question 2, augmented virtual reality. And this was just interesting. It was estimated that each user would need 3 gigabits per second of data with a latency of 10 milliseconds or less. So can 5G do this? Well, the panel sort of said, well, maybe 6G. That really is beyond the capabilities of even current, in the near future projected technology. Question 3 on PAs, power amplifiers, and digital pre-distortion. For example, if you had 256 power amplifiers in your array, and not all of them compress at the same time, how would you apply digital pre-distortion? Can you use an average over the entire array? Well, you could actually apply digital pre-distortion on each data stream. So again, if you had a hybrid array, you would be applying the pre-distortion on each of those subarrays individually. So that's maybe not a showstopper. There was also some interesting comments on third-order intermodulation products. If each power amplifier in an array creates its own intermodulation distortion, and the IM3 has a different phase from that of the main beam, it essentially creates its own distortion beam in some undesired, maybe not random, but undesired direction. So various research groups, and I thought this was really interesting, are using shaping techniques to direct the distortion products, so the beams that are caused by the third-order intermodulation distortion, away from the desired directions. You could also direct, and then Harish brought up the point that, well, maybe using these techniques, you could actually direct IM3 away from a receiver in the presence of a blocker to overcome some interference issues. So these are just ideas that came out of the group. And then the final question was, the new radio bands are very reconfigurable. LTE always had a fixed, you designed your system to operate at a fixed 20 megahertz bandwidth, whether you use the whole 20 megahertz or not. That was the system that you designed. So what are some of the issues in hardware circuit design for systems that are very reconfigurable? And this answer is very abbreviated, but the bottom line here is that reconfiguring hardware, so components like filters, and then the ADCs with the sampling rates, it's difficult, but that there is quite a bit of research in the area. So that's what we had.
Well, one thing I was wondering, so in terms of the interface signal processing, it seems like pre-distortion techniques, clearly signal processing has a role to play in terms of the subarrays. And then in the filters, some of this, why do we have to have hardware reconfigurable filters? you could do it in software too, that you're only using sending signals on a partial stream. It won't be as, the leakage won't be as controlled. So I don't know if it's necessary or not.
I think that the trade-offs are the the power consumption and the complexity that's required to implement things in signal processing or DSP versus hardware itself. And we actually talked about some groups are trying to get away from the use of digital predistortion and go back to sort of the old techniques of using analog circuit design to compensate for distortion. This idea of coming up with better designs, maybe using lookup tables more as opposed to real-time analysis. Any little tricks that companies can use to minimize power consumption, they're really trying to do that right now. And so I think hardware implementations are actually are less power hungry typically.
Power hungry, yes. Yeah, I think that's a good point. Okay, that's one of the reasons why hybrid beamforming is being used as well.
So this was a session, and if you wouldn't mind just raising your hand. So the participants were Greg from BWRC, and Hang from Catholic University, and Kira out there in the back from National Instruments, and myself, I'm Manu Gosain from Northeastern University, and the hat I wear here is as a member of the Power Project Office. So essentially the motivation here was to answer some questions. Again, thanks for the introduction. So we didn't really do presentations. We actually really wanted this to be hands-on and address some fundamental questions, since at least in my, this is my first RCN, but having looked at previous agendas from the previous workshops, this is the first time I think a community testbed session was addressed. So we sort of wanted to level set first with the members, with the panelists, as well as the attendees, what exactly the state of millimeter wave research testbeds is, at least in the US academic community. And essentially the first testbed of its sort that has been funded by the National Science Foundation under the umbrella of the PAWR Platforms for Advanced Wireless Research program is the Cosmos platform. And yours truly, NYU Wireless, is a member of the team. So is Columbia University, so is Rutgers University, and so is the City of New York. And the goal is to basically deploy a citywide large-scale wireless testbed, an end-to-end system. So as you can see, millimeter wave is just the RF enabling technology. And not only that, it basically, given the cost trade-off, will effectively be only available on about 25% of the deployed sites around the Columbia University campus. So we are actually looking at field deployable millimeter wave systems at 28 and 60 gigahertz. And essentially, one of the first comments that came from the group is that's what 5G is doing today. We really want to push the envelope and look at spectrum horizons above 100 gigahertz. So what can you do for us? And the answer was nothing much at this point, at least in the power context. So that was a good input to take in for the testbed community to develop something that does not exist today, or maybe exists in small pockets and only for a very few subset of people. So that was sort of the power story. That's essentially the only NSF-related academic large-scale community, the emphasis being on community, meaning it's going to be available to all the researchers here in the room, as well as the broader research community. After that, Greg briefly talked about Hydra, which is being built or has been built at the Berkeley Wireless Research Center. And essentially, I don't want to butcher the details, but it's a massive MIMO 75 gigahertz, 128 element millimeter wave system. Currently works only in the uplink side, so they have about 60 clients and the base station, and they have a working implementation on the uplink side, with emphasis being working on getting the downlink going, because that's how you discuss or research on higher layers, network and MAC, etc. So then we sort of, tried to answer or tried to discuss some of the fundamental questions of how does a testbed benefit this community? And that's when we started to narrow in and focus mostly on meeting the needs of this community, really digging deep into the physical layer specifications, layer 2, layer 3, and not as much worrying about applications and transport at this point, because we need the base infrastructure here, and we need some consensus in the community on what's important and what needs to be done. Again, for the U.S. academics in the room, there are some instruments available in the National Science Foundation funding cycles, specifically CRI and MRI, which are used to award infrastructure grants. So the goal here was where do we stand in addressing the fundamental research challenges in millimeter waves, and at what scale should we be imagining or envisioning specifically building millimeter wave systems and testbeds? Are we at a point where a community scale or a community size, large scale, shared testbed resource, are we at that point, or are we still at the point where we need instruments which you basically can get funded through small MRI grants and basically represent or develop channel models? Obviously, we heard from the keynote that more measurements are always welcome, but have we sort of gathered enough data and come to some consensus that we want to take the next step and actually develop something as a community that's going to be useful to everybody? Question 3 was something we did not get to, but again, just to put it out here in front of the audience, the goal here was to actually understand who the actors or what the terminology used for this testbed would be. So to reflect this back at the group, essentially looking for volunteers in this community who would want to be either a experimenter, meaning a user of the testbed, a testbed provider, so a person or an institution that's going to host this testbed or the system, or actually develop it. And then the third, and quote-unquote the most boring part, which is actually keeping the millimeter wave testbed system up and running. So these are sort of the candidate roles, and again, we're looking for members in this community who sort of raised their hand, and we did get some volunteers for a couple of those options there. Fourth was sort of to level set, I think something that was said on yesterday during the industry panel, which is essentially from companies and industry to stay away from the modem and the silica. So as the closer you are to the device end, the barriers to entry are very high. And essentially that's something that us as a community trying to get access to millimeter wave systems will have a very hard time. So we need some partnerships. And there were some creative solutions that came up, and I'll get into those. And I think that's sort of one of our most concrete steps that came out of our discussion. The cost performance trade-off models. So essentially, I think this again is to justify the cost and the investment needed to build these community size or individual campus size testbeds. As you can imagine, currently the state-of-the-art or commercially available solutions sort of are quite pricey, and again, you need to be part of either a very prominent research group or a research center to even get access to some of these instruments. And the goal here is to sort of somehow democratize that access by developing these millimeter wave testbeds. The other one, so the next point was essentially an action item of sorts, was to conduct sort of a gap analysis, paint a picture of what's actually currently available in terms of systems, both commercial, open source, some academic efforts such as Hydra and the Power Cosmos platform, and basically try to understand where the gaps are and where actually this community can develop, and where we actually will need to partner with some industry members, and how do we entice them, or how do we put a value proposition to actually attract industry to contribute to the testbed. A couple other things just brought up more for information's sake was looking at other open source communities, specifically in the telecom space, the Telecom Infra project. There is a Telegraph 60 gigahertz point-to-point radio developed by Facebook, which they now have opened up in what they're calling a sounder-in-a-box program where, as an academic, you can actually go and apply to obtain one of these radios and actually use them for channel sounding in 60 gigahertz if needed. So that was more informational here. I did share a slide deck with Akbar, and please feel free to post that to the website. Then we got into, what sort of experiments could a testbed support? I think this sort of was relayed back from the comment again made in the industry session where in the standards bodies, there was people who work on radio and people who work on network aren't really talking to each other. So that was another motivator to build an end-to-end system, a millimeter wave system, where actually these different silos are forced to talk to each other and come up with standardized or common APIs or common interfaces between layer 1, layer 2, layer 2, layer 3, which currently, at least in our understanding, do not exist today. So that would be another work item that can be taken up here. Last but not the least, a big thing was if these systems are being built, they need to be highly calibrated, they need to be really well managed, and the data needs to be very clean, well managed, well documented, lots of metadata, so that any of the data, either IQ samples, channel state information, whatever is captured, is useful to the users of this eventual testbed. I'll pause here if any of the panelists want to jump in, if I forgot to cover any item. If not, I'll move on to sort of what the, do you want to add anything, Hang? Or, no, okay. So basically what came out. So some of the action items that came out, I think the biggest one that came out, and I think garnered a lot of excitement, at least after the session, where some other volunteers from other breakout rooms came in and sort of jumped in, were to actually build a reference design in this community by building together or piecing together all the different research done at the system level, some at University of Wisconsin-Madison, some at Berkeley, and some at Washington State University. The idea being to have a very modular approach to pick out all the discrete components and actually do a layout, an RF board layout, and essentially spit out something that can be developed or something that can be shared with the broader community, where the community can raise their hands and say, yeah, if you build this, I'm going to use it. And essentially what this gives us is the collective bargaining power to go out to a manufacturer or an RF assembly shop like QuickPack, et cetera, to actually build these things, and also gives confidence to the federal agencies such as NSF to see that there's community interest in a project or in a system that's actually been built from the ground up, completely open source, at a price point or at a cost that can be afforded and can be distributed at a wide enough scale. And that was sort of, I think, the big one. Again, I'll pause here, wait, if Greg or any of you want to add anything or fill in the gaps here. Any questions from the audience about that approach going forward? Because one of our goals, at least on the session, was to think about the next couple of RCNs, that there is a year and a half left. So the goal would be to output something, before the next RCN, at least gather things maybe similar to what Marco has done in a shared Google site and start contributing some of these discrete components if you have them available, or point the broader group to who you've been working with on your supplier side if you've been building these systems, and sort of come to a consensus so we can present back to the community the next time we meet as a group, with a broader goal being in a year and a half coming up with a concrete proposal that can be built or written into a grant proposal that can go and be received by the NSF under the purview of any of the programs that were mentioned earlier. In addition to that, the idea here is also about the other large-scale efforts that have been developed. So I mentioned the PAWR program. The timeline for that project is to deploy their millimeter wave system. So I apologize, I think I skimmed over the details, but essentially the phased array system that the Cosmos platform's using, and again, Sandeep and Harish are part of that team, is an IBM Ericsson 64 antenna element, 28 gigahertz phased array, which has 4 ICs. So it might not be it might not be useful for some of the really tackling the fundamental research questions about, so there were points asked about, will you get per antenna channel state information? Maybe, maybe not. I don't know, Sandeep, if you have that information. Yeah, if you oh, there's a mic there. If you want to add. So that was a question asked about per antenna CSI from the IBM phased array.
Right now, it's a phased array, so you can only get that to the extent that you can sweep over with multiple phases. I don't know if that was your question. So it's an analog phased array. So there's 8 anyway. I can give more of the details, but it's not digital on each one.
I think you're raising many interesting and good questions, but I'm still seeking some answers in terms of, for this community, to take advantage of power, and specifically Cosmos power. I know this is just has started. Those of us who are not directly as part of the 2 teams, how are we, what's the mechanism for getting involved? And maybe relatedly, and this is more like to NSF and the power, I know there's an upcoming phase supposedly intended for the research efforts to make use of the testbed. What's the timeline on that part?
So that one I'm going to beautifully just deflect, and that's my karate move right there. Goes to NSF. I unfortunately don't have the either authority or anything to talk about access per se. What we have done is talk about federation with European testbeds and platforms similar to the 5G efforts that are coming up. So 5G in Fire, 5G Tonic, all the testbeds that are coming up. We've started discussions. I think there is an open call in the EU ICT 21 that's going to fund CSA, a coordinating entity that will essentially interface or liaison with the PAWR program. So I think that's going to be a venue where that question actually gets addressed on what the mechanics are for access, what the federation, identity management, all those thorny issues that need to be sorted out. So as I said, I'll deflect that piece, but for sure that's on our radar. With respect to when is it going to be ready for the current community? For the Cosmos platform, again, Sandeep can jump in any time, but in fall of 2000, so when the Cosmos team submitted their proposal, they submitted a large number of sample representative experiments. Some of them were based on millimeter wave. The early ones are going to be done by the NYU and Columbia team, as well as they've solicited some lead users, extreme users, quote unquote, to actually provide feedback on what these systems are capable of doing. So questions like, CSI per antenna on millimeter wave systems. Okay, if you can't give us, what can you give us? Is it useful enough for us? So there are a series of workshops starting in fall 2018, which will sort of recruit users in each of the domains that Cosmos is building. So there is a millimeter wave component on the RF side. There's a fully optical, reconfigurable optical backbone overlay, which will basically address that community. There's a networking SDN edge cloud component. So these components will run multiple different workshops to gather user requirements input, as well as develop sample representative experiments that will be available to the broader community. In terms of the go live date for the platforms, when it will be available, in terms of what the development roadmap or timeline has, that has it for late November 2019. So that's a year and 3 months, and 3 months from now is when it's open to everybody. Because it's effectively, if you think about it, it's not just, it's an infrastructure project. It's essentially a building a city-scale network. So we're sort of some of the issues that, Ted laid out at the end about right-of-ways, access to streetlight furniture. We are going through all of that. All right, I mean, the team is too.
So yeah, I think I would like to make a few comments about that too.
Sure.
That, so we are getting, and I'm sure that this is, hello, that this is a confusion. People are getting power. So this just one of the discussions. There are two different things going on. We don't want to make this a power session. They just started. I'm sure NYU and Rutgers and Columbia would be, doing their thing. That's going to be happening. But the testbed, a lot of people have this misconception. What is power doing, and what the community testbeds that we were trying to get an input on, that the first bullet item that Manu had. So I want to just clarify a couple of things. All of these power test beds are going to be more infrastructure, and all of them should be able to support millimeter wave experiments. Cosmos is one where that is one of the components of it specifically. The later ones may have bigger components on that. But what we are looking at, one of the things that in this panel discussion, and I want to just make some brief comments, is maybe towards the second half, we will discuss it more explicitly, is what is the need? So some people may be satisfied with, working with power platform, whatever they provide them. But there are other people, I would say my group at Wisconsin, we were building, and I have to be careful, we are building a test bed, and that's going to be, we have a different, less expensive way of doing beamforming. We're also trying to create an end-to-end solution where we built all the RF hardware ourselves, antennas. We have FPGAs too. We are developing the code. Berkeley is doing that with Hydra. And so, some places are trying to get that end-to-end system, but different people have different expertise. There are other members of the community who are not here today who are taking 60 gigahertz thing, velocity or something, and they're more focused on network layer experiments and end-to-end. So the goal here is there an interest in the community to develop something in parallel to power, or almost independent of power in some ways, which will enable smaller scale experimentation within their institutions. So one of the ideas which Greg came up, so first thing would be, okay, who are the RF people who build antennas, who are interested in building antennas for the such test beds, or RF front end, for example? Who are the people who would be interested in ADCs, DACs, and looking at those boards and combining that with FPGA backends, because you'll need FPGAs for any kind of real-time implementation? And then who would be interested in developing the FPGA code so that you can even do or interface with an end-to-end networking interface? These are different expertise, but I know that in this community, all of those folks exist, expertise exists. And then, so first thing is identifying who wants to work on these modules, create community-wide specifications for, what are the needs that we need, modular, and what it can do, and then fill in some of the other expertise outside ones where, for example, these RF boards will be integrated, so, we have to outsource it to some companies. We don't have to work with big companies, and we are not, this is not a commercialization pathway, so we're not intruding on any big companies or anything. So is there an interest? Who are the players who would want to actually do the work? And then who are the researchers who would be interested in getting access to that platform? And at what cost, so that we have a complete idea of, okay, this is what we need, the community agrees to that, and these are the people who would build it, but at the end, once it's ready, perhaps there'll be 50 institutions who would be saying, oh yeah, we'd be interested in replicating that system at our institution. And so we need the community to kind of develop that roadmap if there is an interest, and we'll come back to that, and we'll send emails about that too, and then create a roadmap, plan, proposal, blueprint for what to be done, and then what resources are needed, and see and then, present it to us, and we'll see if we can make it happen. And now this will be complementary to power and any other platform. It could be, I can see it being in Utah. I mean, it's a beautiful place for doing experiments. And New York City, absolutely. So it could be put in any and all power platforms. And yes, international collaboration, I think there are many multiple dimensions to it, and but I think I'm not fully prepared to answer that question right now. But it's, yeah.
Will NSA be paying for this?
For what? The second thing?
Infrastructures, no. For these experimental platforms.
The second part I'm talking about?
Expect the groups.
Yes. So what I'm saying is that right now, the CRI, MRIs, people can build components. So we can leverage those, or there could be new programs too. It's a question of, NSF wants to listen to the community. What are their needs? That's our power program came around, right? So what are the needs? If really there is a need the community feels, and I've heard that, but are there people who are really interested in actually doing the work and working together to do it, then create a plan which is compelling, which you believe in, and then let us do the rest of the job. We will try our best. So anything is possible.
So we only have two panelists today, but so hopefully the rest of you will just pitch in and we'll make just a free floating discussion. My own contributions here are just to stimulate this a little bit. So I just wanted to, let's just to start off the discussion, talking about moonshots is really talking about requirements, and this famous graph, which has been reproduced in different ways, was from the IMT 2020 vision, I guess was set now maybe about 10 years ago. And I just want to start up, and it sort of put three types of requirements, either in terms of throughput, latency, and connectivity in terms of number of devices, the latter one being related to energy requirements. My view from looking at this right now is that all these dimensions are pretty much technically feasible. The prototypes that are being done are pretty much meeting them right now, but it's a question, I think, of getting it down to cost and getting the coverage out. And maybe just to start either with our panelist or anyone else, where are we in terms of that, and also maybe what would be reasonable targets for what's next in terms of these phases parts?
Yeah, I think in the last couple of years, we really just focused on one aspect of this, just the EMBB. And that's just the industry's been focused on that, especially on the millimeter wave side. And I mean, specifically on millimeter wave, EMBB was the clear target. And it's hard to imagine what kind of a role it would have in ultra low, high reliability, low latency part is fine, but the reliability part, there seems to be a place for it in industrial IoT. If we can get the cost down, but really it has just been EMBB. And on the EMBB front, if we had this conversation maybe 2 years ago, it probably didn't seem like it was that cost effective. It wasn't that clear, but now it's shown to be cost effective. Once the industry puts all the resources to it, it becomes cost effective. So I think So
you think it's just once it scales to the right volumes, you don't foresee there being a cost issue with building these devices?
Yeah,
at least on a smartphone cell.
I foresee it. Yeah.
Michele, do you want to just quickly talk about on the networking, on the low latency part? Where are we now?
Yeah, well, I guess I wanted to make a comment that I think we've seen a lot of focus on the high rates, the millimeter wave, closing the link at these frequencies, showing that this is good and this works. I actually think we don't have a good understanding of how the network will work. I don't think there is enough work done. And, in a way, I'm a little uncomfortable with this focus on test beds, because I think we also need fundamentals. We need fundamental understanding. Being an academic, I'm all for that part, mostly. And I think the fundamental trade-offs that are there, I don't think they have been explored sufficiently. I wouldn't even be able to say if those trade-offs are just the same as we know from other networks, just with different parameters, or there is something fundamentally different. Coming from the networking side, just an example, the need for directionality. Ted made the point that directionality will solve the issue of the path loss, right? Because the antenna gain will compensate for the path loss. But then, when you look at it from a networking perspective, there is a delay issue, which is there. There is a mismatch between coverage in the data plane and the control plane, which will make these networks harder to manage. And so all these trade-offs, people are looking at the extreme broadband, the ultra-low latency, the energy issue, the coverage issue, but are we looking at these together as a multidimensional space where we need to find the good operating point or the good trade-off, so the boundaries where we can or cannot go? All of this, I think, hasn't been done in this community. There are some people working on networks, and there are some contributions there, but I think much more is needed. And so, we're happy with all this physical layer work and link budget and measurements, but really we need to go to the next level and show that these networks can work, can be managed. It's hard because experimentally you can't do much. Simulation-wise, you can do more, but we discussed yesterday in the Breakout group, simulation has its own limitations, and so that's another modeling issue that needs to be solved. So, if I look at it from a network perspective, nothing has been completely solved yet. And so I don't think it's a moonshot because, we're talking about the system we've been looking at for many years. But really, I don't think the progress in the networking area has been as significant as it should have been. And so I see that as a wide open area where we should really invest a lot of brain power. And also looking at fundamentals, analytical tools, maybe some simplified models that get insights to be complemented by these measurement and experimental platforms, certainly. But as a mostly academic community, I think we should try to provide what we're best in, right? Which is insight and understanding.
It's interesting. Maybe one way to think of Moonshot is, what would be the ultimate theorem that, like, if you think of, okay, like MIMO had the capacity formula, there's a single, expression that encapsulates the whole MIMO theory that was really revolutionary. And there are similar results in queuing theory and in network and TCP, but there's been really, maybe I'm wrong, but I don't think there's been a single or really significant theoretical result of that nature.
Some information theory approach where you include explicitly this flakiness of the channel, these extreme dynamics, or this inherent diversity you need to have, multi-connectivity and all that. Does that change fundamentally some of the theorems we know? Some of the, the Shannon type? Maybe, but we don't really know. We haven't thought enough about that.
Okay.
And if I may add, let me see, on the...
Testbeds are, so I'm going to, you're saying, right, that, hey, we need to do fundamentals, so I agree with you. And what I'm getting at is that, we don't necessarily know, as you said, what is different here. So I think there's something very different here in terms of the characteristics that achieving this latency, low latency, is going to be challenging. And there's a lot of things in the air, and testbeds, the hope is that, or the goal is that we actually build these testbeds so that we can answer those questions in parallel, so that, you can have a theorem which may be irrelevant, right? Because it makes assumptions and you have a beautiful theorem, but it's useless. On the other hand, you could have a testbed which is useless too, because it doesn't allow you to answer meaningful questions. So it's somewhere in the middle. We want to join forces. Can't be this or the other. And industry, with all due respect to industry is going to go where they are going, right, where they can make the most money. And so they'll give one straitjacket after the other, which is not going to let us answer the fundamental questions necessarily, because they'll have a specific way of doing things which are cost effective at that time. So that's the goal here.
Okay. So on that note, one way to think about, I put this up because, is it too early to be talking about, how would we want to change? So that, for example, there's this 100 megabit per second number on the EMBB, or the less than 1 millisecond latency. And I guess in different parts we've reached or not reached these. Is it too early to be thinking about what would be the numbers as a moonshot to go increase these? Or is this even the right way to be thinking about what is a moonshot, or the next step, at least, for the field?
Well, is it all about numbers?
I don't know. That's my question.
If this is about improving those numbers by an order of magnitude, we can agree that's a legitimate goal, or maybe it's not a legitimate goal. Maybe there's something different. I can certainly see increasing the data rate as something we may think of. Now, decreasing latency, I think you're going to hit some physics. Yeah. Because there's only so much distance you can cover with a small latency, and so at some point you're going to hit that. And so you either decide everything's going to be heavily decentralized, or you're just giving up because that's not going to happen, right?
All right. The other. Oh, go ahead.
Yeah, I think that, so the data rate part, we can always increase it by just, right now we're talking 5 gigabit per second for a UE, but then you can always add more layer if you densify enough, and you can go up to 256 QAM or further, or do channel bonding across 28, 39. You can always increase it, but I think the fundamental issues will really just be trying to make this more robust and more stable. And because when you come to data rate, even 5 gigabit per second, everyone loves it for a PR, and everyone will put in the headline. But when you talk to any operator, they don't know what it's going to be used for. Right. They'll admit that there's no need for it until someone comes up with an application that requires it. So then they just throw VR there, because VR is the only application that is in the gigabit per second. But then, is there really a business case for VR in a public environment? Where are people going to walk around with a VR headset? I doubt that. So right now, I think the main focus really should be the stability and the lowering the power and making this more cost-effective before we start increasing data rates.
So what is, also put up here, so we've seen that, in a lab situation with kind of infinite resources, you can create these high data rates. And we mentioned, you're saying that the economies of scale will drive down the subscriber cost. But if we look at the network side, what's the cost barrier to delivering, even in the order of, say, 1,000 megabits per second throughput universally? Is that affordable right now from the operator side to put in the network equipment? And what would it take in terms of research to get it, or development to get it those cost factors down?
Yeah, I think the small cells themselves have a cost issue, and it's really on the RF side. So there's really no cost-effective phased array right now for macro small cell stations, and that's where I think the leveraging the UE side will help out quite a bit. So any development on the UE side where you're deploying millions of these devices, and if you can leverage that on the base station side, and that's going to be key. Then there's also the deployment part of course, of trying to bring backhaul to all these small cells, because you really have to densify enough so that you do have a robust deployment. And if you densify, then you have to run fiber or a wireless backhaul. But then there really is no appealing technology right now that, unless you go for the proprietary technology that allows you to get the wireless backhaul. So that's why I think the integrated access backhaul work is quite important to really have a cost-effective deployment.
Yeah. Another thing I was thinking is from network side, this protocol overhead, right? So, this 4G or 3G or 5G protocol stack, if you take a look, is very complex, especially this control signaling or PDCP, all these things. And also some of them inherited from this legacy phone network. So it's from network side, I don't know, for the 3GPP point of view, is that their roadmap, to all this GDP tunneling, all these things. So is there a way to simplify it, and make it, I guess they are trying to get more flat network, but so is there something to reduce this overhead, because this is related to the latency and also the cost, right? So from capacity point of view, you can always, and improve the physical layer, increase the capacity, and even you have some control overhead, probably you can compensate that. But from latency point of view, probably is more important, and to take a look at the stack, to see where we can simplify it to speed up the process.
Yeah, there are actually several dimensions to this. One is the device complexity, right? if you need to run a complex protocol, then you may need more resources. And on a cheap IoT node, you may want to relieve that complexity. So that's one thing. The latency, and I would add energy as well, dimension when you have these complex protocol stacks. This has been addressed. Clearly, it's a known problem for IoT, right? Because you send only a small piece of data, you have to exchange 20 times more messages in order to do that. So that's a problem which is being addressed. I'm directly aware of some work coming from Aalborg University on simplifying LTE for this machine-to-machine type, where they try to compress these handshakes, this exchange, back and forth of signaling messages by maybe combining functionality into the same message. So this is being addressed. And so, but that's clearly one way where we should go, especially in this machine-to-machine or IoT type of scenario. Now, another issue related to this, I would say, is about the network architecture, right? So not just the protocol, but the network architecture. So what is the network architecture going to be? And we face a lot of complexity in terms of heterogeneous nodes and traffic. We face a lot of issues about, at least in millimeter wave, for multi-connectivity, and so this comp type or maybe quick handover or multiple connection active at the same time type of issue. And even though 5G suggests an evolution of a cellular systems to a new cellular system, so does this have to be cellular? I mean, people are talking about no cells. Would that actually a question? If you do away with cells, right, whatever that means, is that simplifying the network architecture, or would that complicate the network management? Right.
So
yeah, here's
Parmesh Ramanathan from University of Wisconsin-Madison. So I'm not quite answering the thing, but yeah, part of it is if you're thinking of the Moonshot, I think some of those things have to be on the table, right? Including whether we want to get rid of IP. I mean, I know various times over the years I've been in this thing for 30 years, and we have predicted the death knell of TCP or IP and those kinds of things, but we have never ever got there. But maybe this is the time for us to think through and make some fundamental changes to the networking stack, because it may not be feasible to get those low latencies, however lightweight we go. I mean, we have been working on those kinds of things for a long time, how to make it lightweight. And it's just not feasible. I mean, or we have not had any good breakthroughs on that thing, and that's why we are stuck with TCP and IP, right? So maybe we need a completely different network protocol stack completely.
Maybe just on the complexity issue. So the 3GPP, of course, has, in one sense, simplified it because they have the data plane separate from the component. That was already the case in 4G, and they partitioned it even more in 5G. And in terms of the network architecture, they've made it extremely configurable. So you can have the kind of standard, more centralized packet gateway structure, but also distributed gateway structures. And then with the network slicing and network functional virtualization in 5G, it's extremely configurable. But I guess there's two issues. We don't really know how this is all going to be used. It's almost like it's even worse than the Airlink, which has a million different options. In the network, there'll be even more. And the other part there's another type of complexity, which is just this, if you try to, and we're going to probably hit this when we talk about the testbed development, if you actually there's a huge barrier to entry to implementing these protocols, even if theoretically when they're implemented, they're extremely fast. I mean, there's just thousands of pages of specs and aspects of these protocols, and that's another type of software complexity, which it's another whole issue. Maybe we can come back to these, or at least in the context of some use cases that might drive what we think about moonshots. So if you look at of course, there's a standard for everything in 3GPP. So if you look at 38.913, when they were envisioning for 5G, they list a number of use cases. So, you know, hotspots, connected cars, highways, all sorts of things. So I just want to go through a couple of these and wonder, you know, how close we are to these and whether any of these might define how we're going to direct research. So let's start off one that's come up in a lot of discussions about connected cars. So connected cars is, of course, connected to autonomous driving. Where are we now in this? And you know, how is this driving 5G and how will this drive requirements? And maybe instead of going to the panelists, I'm going to flip this over to Tomi because I know he gave a talk about this at IEEE 5G forum, and maybe he can. I'm sorry to put you on the spot there, but you're sort of knowledgeable in the area.
Yes.
And you just introduce yourself.
Okay, Tom Svensson, Chalmers. So the question was, where are we today in connected cars?
Yeah, that's right. And you know, how is this going to drive the use cases for 5G and what we should be doing in terms of wireless research in the next, you know, 5-10 years?
Yes, from I think that there are different perspectives, different parts of the world, and academia and telecom industry and automotive industry, and inside the automotive industry there are also different views. But I see a moving trend towards connectivity of vehicles in the automotive players, away from ITS, DRSRC kind of connectivity towards network assisted. They start to see the value of it. So I personally, I think that there will be steps. They will start with DSRC kind of connectivity, to create, implement the basic ITS services, and then every vehicle will need cloud connectivity, and that will be more and more data. And sooner, and when you have these models, they will start to see the added value to harvest what I normally talk about, improved information horizons, because that's what the mobile network can add to the control systems for active safety assisted vehicles and towards fully autonomous. So we have a EU project called 5G Car in Europe.
What's it called?
5G Car.
5G Car, okay.
So just Google on 5G Car and you will find the website. It's a 2-year project and we run 1 year now. And there are a lot of use cases there. And I would say the most advanced will be remote driving, remote parking. So it's not. It should be enabler for autonomous vehicles in massive scale. But personally, and the European industry seems to think that it's a little bit further away. Yeah, it's what is the unplanned statement now. I have a 40-minute presentation in my pocket.
Oh, okay. Well, sorry, put you on the spot there to give a quick summary.
But I think also, I was also in a panel at the UCNC a couple of weeks ago, the European conference for all the EU projects, and my view there was that maybe you should have split focus in the public space, regular cars driving in cities, with a mix of manual cars and pets and kids and bicycles and pedestrians that are blocked with headphones. It's quite complicated use case.
Yeah.
So why not? So there maybe we should have. Maybe that's TED shows the hype curve. I think that is a hype curve problem. It will take 10, 20 years before we have it fully autonomous in a massive scale. But there are a lot of other use cases in professional contexts. Harbors, mining areas, building construction areas, factories for store warehouses, sure. automatic robot cars in high-build warehouse storage. They can be fully autonomous. And there we really could play with controlled network assistance and learn what we can use 5G and beyond 5G for. And then we are ready to go massive scale in network assisted autonomous vehicles. That's my view.
Okay.
Can I add
millimeter wave will play a role. Just as a comment. In street canyons, I think millimeter wave have a good fit.
Yeah, you need to distinguish between connected cars and self-driving cars.
There are two very different things, right? And you know, was another IEEE event a few months ago, and someone from Berkeley made it very clear. You know, self-driving cars, you mean totally autonomous, you know, able to drive wherever and in any condition. That's going to be very far into the future. Now, connected cars are useful, but they're not by any means self-driving or anything like that. Now, the second aspect is that applications for connected cars, because cars can talk to each other or to a network, may be very different in terms of importance, in terms of requirements. Clearly, safety-related applications, you know, typically short messages, you know, low latency, high reliability, versus entertainment for your kids, so they don't bother you. You know, that's a different thing. So where is 5G millimeter wave playing a role? Well, high data rates can help, you know, in both the entertainment, but also in some safety-related, like LiDAR images are very heavy, and so there is a role here for millimeter waves, I think. Although, you know, how to make it work in a highly mobile and highly dynamic scenario is, of course, a challenge, right? So we're actually doing some work in this area and trying to find, you know, what are the fundamental limits.
Yeah, I think the current EMBB for millimeter wave definitely solves the infotainment needs and the HD map needs, and it makes a lot of sense for a car. And then I agree that there's high mobility, but if you look at some ways like highway, New Jersey Turnpike, or some places where they've already cut down all the trees, and it's a clear line of sight, and everything's very predictive. You can predict that the car is coming from there, and then next step it will be, you can track the cars fairly easily. It's a very predictive environment. But the problem really with the connected car in that use case is really that the car industry moves very slowly. And by the time they adopt something like that, it's almost unless there's some kind of a mandate, it's very hard for those things to happen immediately, right? Because the operators will not deploy base stations for that use case because the car manufacturers will move slowly. They'll focus more on the EV handsets, and it'll take a while before those two things converge, and that connected cars, there is infrastructure for connected cars on highways, unless there's a mandate by a government mandate, and then they, all the industries, join together.
What's the state of DSRC now? I mean, in terms of deployment. What's the state of DSRC in terms of deployment? I mean, even that standard's been out for a number of years.
Some car manufacturers announced they will deploy DSRC in all their cars, maybe from some level up soon. And so that's happening. I don't know if it's mandated, but it is happening.
Akbar, you want to go first?
This panel is putting me to sleep. And so, so what, so for everything there's, so I've heard, that, hey, we need to do some more fundamental research. And then, for latency, yes, there'll be a physical problem, but let's classify where. So are there use cases? So I'm just trying to put some structure here. So latency, is it, Palmer said, well, we've been trying to make things lightweight for a long time, but TCP/IP, is it's embedded everywhere. Yeah, we're not going to replace that anytime soon unless we make a very darn important case. So what are the applications where latency is going to be an issue? And then we have to address the question, okay, physically, what are the limits? We can put radius in terms of, speed of light, and that'll give us the first thing, and then what kind of networks can be within it. So can we put some structure on the kind of research problems that we can address? And do we have enough information? And how does industry, industry, it seems like, there's just anti-robustness. So what is there something to collaborate, or is it a lost cause? Seems like it's a lost cause. This is the fourth meeting on RCN, and NYU, you guys have a lot of the affiliates, but I don't know how much, your comment was yesterday, yeah, we listened to you guys initially, and then we went and did our own thing. So, what are we, can we, what is the role for collaboration here? And what, are there some problems that we can identify where we can, whether it's theoretical or whether it's, if it's end-to-end simulation tools that you're developing, what is keeping them from being predictive so that we can actually help address those fundamental questions, or maybe explore some from scratch protocols to move things forward. I mean, it seems like we are just, passing the buck to some other domain where, putting the blame somewhere else. So what are we willing to do to push this forward?
In terms of application domains, I mentioned two good candidates. One is automotive, right, where low latency is needed. Because
what you earlier said, there'll be some physical limits, right? So why is low latency limit needed, and what kind of information? And
well, if you look at safety-related applications in the automotive domain, where you mostly talk to your neighboring cars, which are very close, and so the physics limit goes down, then that may still be feasible. The second application scenario where I think this is going to be important, and the scenario itself is going to be important, is industrial IoT. Right? In everything that where you have a control or automate the process and tightly control things from a safety perspective, but also from an efficiency perspective, the time scales in those environments go down significantly. And so that's another area where low latency will be important. And again, it's a local environment, and so probably the latencies will be because of how you design your communication system, not because you have to travel 100 kilometers. Right?
Yeah. So what about those different dimensions? I don't know which company has that 5G different latency rate. What are maybe some of the pain points? Maybe we need to look at some extreme cases and use case and kind of look at where those applications would come in. This kind of thing, but there's another, I don't know, maybe Nokia had that where there's like different dimensions like latency, complexity, and things like that. Maybe that's what we focus on, or some use case.
Yeah. So one thing that maybe we need to investigate is, I mean, clearly in the back end, replacing TCP and IP is going to be much more challenging. But we may be able to now, because of the way it is, have the gateway in between that has a different network layer protocol for the last mile or the last hop, and a different one on the air network. I mean, IPv4, we kind of, it's death knell because of address space, we kind of solve by putting the NAT boxes all over the place, right? I mean, same way, I mean, now maybe it is a time to think of these other boxes that will do the gateway between two network protocols. Because for the AR, VR stuff, maybe it is just like local thing, and we could achieve the latency that is there, and only for these end-to-end applications that we need to go to IP and TCP, and maybe a network gateway that translates to these two protocols, maybe a solution that we have to go for to achieve both latency while retaining the legacy of TCP and IP in the back end. And then we need to investigate what would be a suitable network and transport protocol just at these UEs and just at the last hop of the millimeter wave, or just basically more generally these high data rate wireless networks in general.
So can I intervene? So my comment here is we've done exactly what you're talking about in the millimeter wave specifically. So reconsider the proxy server solutions to maintain the TCP/IP semantics while designing something more cross-layer in the last hop. And we have some really good results. It's based on the simulations, right? So we need better models, but we're taking that direction. And my question is, how can we make an impact? Because we're clearly working on that. We're trying to, capture the most realistic scenarios, but we would like to have a better impact, and we don't see a way to engage. What should we do? Go to IETF? Should we? Because otherwise it's this constant, academics publishing papers that just remains in the academic domain and have zero impact. I would really like to find a way to have a stronger impact.
Into the 3GPP standards or into the industry like the automotive industry, both of which are kind of very difficult.
Yeah, I know. Exactly. I mean, in any sort of, how can academics developing and having these open communities, research thoughts and brainstorming, how can we have a bigger impact? And
does not remains, in our papers. And one more comment, always related to this TCP stuff, is recently the head of system architecture at 3GPP had some interactions with IETF to reconsider the TCP/IP stack. And considering new protocols, like, for example, Google Quick protocol, but those are the Google people. How can we, have our say and show our results? I would like that. That's something that we would like to. But we need better models. We need better test beds. We need we need to refine all these tools that are giving us some insights about performance. So yeah, these are my thoughts about that.
Do companies care about this? Do companies care?
No, so this is no. They don't care until it hits their bottom line. So I was having a discussion with Shiv yesterday too, right? That okay. So the first thing is you have to think about, okay, what is your message that you want to convey? So I again go back to latency, right? I mean, that's nobody discusses. Industry people also, you also said, hey, there's a different part of Qualcomm that works on that. And so maybe we haven't hit that use case, right? And so what you need to think about is, okay, what are the, with our existing standards, with the 3GP work, what are the scenarios where that latency is that was my question to you a year ago. What are the situations where a millisecond latency is going to be critical, or where the current protocols will just not work, and it would hit industry in their bottom line?
Cooperative flight? Cooperative flight?
What's that?
Cooperative flight?
Cooperative flight? Well, where is it happening? Maybe. Whatever it is. I think we have a couple of
Yeah, so I had kind of more industry-related questions. So you guys have kind of got the operators to buy in 5G now. It seems like it's going to happen. So if 10 years from now you need to sell them 6G, what are the things that you have to show to them to convince them that they need to actually buy into a new environment? Is it just improving capacity by another 10 to 100x? Is it getting rid of small cells and actually making macro cells that are capable of these high capacities? Like, what kind of features do you think justify the next steps?
Actually, a big part of the deployment, if you ask operators right now, many of them don't really have a capacity issue at this point, but they think that they will have a capacity issue. So it seems that 5G will solve that. It also brings in more revenue for operators because there's all the new services that it can bring in. But a big part of it is just large operators that push forward. They want to be the first in 5G and they want to deploy it, and they know that revenue will come in. They know the demand will grow, and then at that point, the others, it's almost peer pressure, right? You can't have one operator doing 5G and then no one else is interested, and then now other regions start coming in. Europe doesn't want to be left behind, and everyone jumps on the bandwagon, right? If you looked at the early schedules of 5G release, it was further out. It wasn't meant to be end of this year or next year, because that's really when people thought that the capacity needs would be there, and that they probably have to think about deploying 5G systems. But because of some operators pushing it earlier, now the whole world is behind, and they all want to deploy early on. So I imagine, it's hard to predict what things will be in 6G, because even it's not clear what the need is for all these in 5G. But in 6G, maybe there will be more capacity, but likely that we will need more capacity. And again, there'll be another push by operators to deploy 6G and try to get more revenue streams and think of more use cases. But it's hard to predict that at this point.
Mickey, did you want to say something? I forgot. Yes. Okay, I didn't see if you were raising your hand or not.
Yes, thank you. So it was related to your earlier question about does industry care about some of the simulation?
Mickey, by the way, is from InterDigital. Sorry.
And I think from our standpoint, for instance, we play in the field between academia and commercial deployments. We're smack in the middle, developing technologies. with our focus on 3GPP, for instance, we would have been extremely interested in having the NS3 network level simulator available and ready to use for instance, the NRU study item on release 16. But obviously it's not there yet. It's going to be very interesting in the future, but it could have been available for this good of mankind kind of contributions that would help develop the NRU standard in release 16. So yes, in that respect, we really care. And you know that we work with UPadua, for instance, on related topics. So that's an area where we could quite well.
So why wasn't it ready? I think so. This is exactly the thing.
It's not ready for readily available for NRU, right? So NS3 has a lot of LTE functionality and capability, but because it's being developed while the 3GPP release 15 was being specified, it is hard to have it available at the same time.
So is it impossible or is it a resource problem? Because if it's a resource problem, this is a perfect place where industry and academia could, and you should put your money where your mouth is and say, hey, Marco, you want to expand your team so that you have this NSC simulator ready for prime time?
Sorry, we've been, Marco can talk about this, but I mean, it is a bit of a resource issue, and we've been trying with Sumit to address exactly that.
But this is exactly the case, right, where it would be where industry, there are things in industry which they don't have the time, and that'll be a place where it could be useful, and I think it's true across the board, but people are just too busy to even think a little bit, yeah.
So, do you want to talk just quickly about discuss with Sumit and tell us
about what? Which one?
NS3 and trying to get it.
Yeah, and even more in general terms of Sumit is the maintainer NS3.
The maintainer NS3.
Yeah, which were basically.
Sumit's right.
Yeah, so we would like. I think there's a call for you guys at NSF. Basically, we're trying to find a way to get funded for growing these.
Industry should fund.
Thanks for putting me on the spot.
No, or Qualcomm. I mean, who are you? You are smack in the middle, right? You said we are smack in the middle. So you say, hey, this would be useful. You convince your industry players that, hey, this would be useful. Let's provide the money. I mean, come on, when we say government should subsidize industry, that's ludicrous. I mean, let your CEOs and CDOs take a few 10% cuts before that.
I have a maybe it's not even about you guys invest, but why? I'm pretty sure that I know for a fact that there's a system level simulator at Qualcomm. There's a system level simulator, I guess, at InterDigital. Why can you share the baseline? The baseline. We don't want the technologies. We don't want IPs, but just the baseline, the L1 baseline for link level simulations, or the Mac. What's that?
That's exactly where you guys come with the NS3, so you accelerate the simulation so it gets far with us, and then we can submit it directly to 3GPP. Okay, because obviously, there's a lot of work that was put in both the NS3 simulation, network level simulation, as well as in InterDigital's system level simulation, right? So I think the collaboration would be extremely beneficial if somehow more resources would be thrown into the NS3 to bring it to the level that we are at. We obviously cannot disclose a lot of our internal stuff.
Yeah, no, exactly. But the baseline, there's so much baseline.
So can this be an action item for follow-up? I think this seems like this is similar to the testbed stuff where community. There is a this working group has been moving things along. you have put yourself in the middle right now as well. And so, yeah, you place, InterDigital isn't smack in the middle, so this should be an action item to kind of say, okay, and you have some good questions, what can industry share, and what are your needs? How can academics help who are interested in that, and what is going to be needed to fill in those gaps that you're seeing? We need to improve models, channel models, measurements, whatever it is. This could be another action item for a plan, a community plan for a subgroup, and this could, I see it as connecting to testbed too, because measurements could go in there obviously, and other aspects too. So I think this could be something that we could follow up on. So even though you said no to the panel, you're on now.
Actually, I'm going to, because we have about maybe 10 more minutes. So I had walked through a couple of different use cases, but I wanted to bring to this one just because maybe on Akbar's point about trying to get actionable action items out of this. So one of the use cases, of course, is on edge computing, and this is particularly relevant today with all the talk about AI. Maybe AI is in the peak of the crash and will crash. But one thing I noticed when doing a research for this panel was there's actually presentations you can look on Amazon AWS services, for example, and they have talks about 5G, what 5G will be for edge computing, but I have never seen any of them show up, not just at RCN, but pretty much any of the wireless conferences that we're going to. How do we engage with this group? Because presumably, either maybe there is no relation between 5G and edge computing and AI, or there is, but the companies that are in that space are just not talking to us. And how do we get this? Actually, this was stolen from, I forget, one of the, another cloud provider. It's not the Amazon's, but the Amazon has whole presentations which they go out and give to other AI companies on their, on the AWS services and MXNet and so on. So maybe has anybody had experience relating with Google or Facebook or AWS, and can we ever get them at an RCN? Should we get them at RCN?
I think that's actually an excellent point. I'm glad you brought it up, because I think there's a lot of so machine learning is everywhere, right? So on the NSF side, we see machine learning on all the proposals, AI and whatnot, and nobody knows how it's working. And one of the places where I think from a basic science perspective, it's very useful is to understand how AI works in engineered systems. And this is a perfect example where I think, networks are going to be running a lot of data analytics on their own. It's like self-referential AI. And I think it'll be great to bring them along, and maybe, maybe InterDigital or Osge has.
Actually, I do know that Qualcomm has I met them actually at NIPS, the machine learning conference. Jeff Gelhar, who we used to work with, I met at NIPS, the machine learning conference. So there is, I know, on the terminal side, looking at AI, but not in terms of necessarily in the connectivity part. I don't know.
Yeah, that's great. I mean, we do have a group that looks on the terminal side, because at least on the terminal side, for years things moved to the cloud, but now there's so much compute power on the phones, and that there are applications of AR and VR and machine learning that it has to happen with very low latency on, and can use the phone. Those groups, I can engage with those groups and see they likely do work with Google and Facebook, and
edge computing is going to be key to low latency as well.
Right. Yeah, that will be a real driver.
Yeah. So I think we need to bring that. Yes.
Manu?
Yeah. So again, the community that you're talking about and access to them. So we've had a lot of interest from our power industry consortium members, namely Intel, as well as some members in the telecom infra project. So there is a working group within that community looking specifically at AI and machine learning at the edge as it applies to telecom networks. What they're looking for is data. I think the struggle there has been access to operators and willing operators that will actually run AI and machine learning and actually provide that data. So they've come to Power Testbeds to actually see if some of that operational data can be shared so they can run their training data sets on the back end. But again, would be happy to make that connection, and they'd be very willing to come out here and speak with us.
Yeah, there's definitely interest that, from the data side, like people want to do data analytics on the network itself, but also, you look at the presentations that AWS is talking about are providing cloud computing offloading for AI. And, I just don't, and they, like I said, they see 5G in their presentations, but I've never even ever seen any of these people at any of the conferences we're at.
No, I think that's an action item too for next. For your own, have you had them at the Brooklyn one?
No, I've never seen them.
No, I think that's a good action item to get them engaged because I think that to me, the latency is one part that gets shrugged under the rug, and this is a key enabler and AI related. So I think that would be a very good thing to bring in.
Yeah, just one comment. First of all, as Manu said, a lot of discussions, even a few days ago in San Francisco in the IEEE World Forum, talking about this and opening, because we need data to make machine learning. And the second thing I want to bring up, and it's basically an open invitation to Samsung. I was talking with some people at Samsung, and they want to do AI in NS3, basically. So there's also another unbiased comment that I make about NS3, and we'll try to bring them in specifically for this, and then we got also, expand a little more on the core network and stuff.
I mean, another thing maybe for the next RCN meeting, I mean, Akbar has been asking what are the applications, and we didn't get too much response. And I think even the testbed thing, Manu's thing was, we were talking about the applications. So NSF had that on the wired side for the gigabit kind of thing, after Google Fiber and so on, NSF had the US Ignite initiative to fund applications for gigabit applications, basically for the end-to-end, but more distributed across the country, right? I mean, they're focused on how to be, and some smart cities and those kind of things. But maybe we do need to engage either the US Ignite community or have specific calls from NSF to think about applications that will drive last half gigabit, multi-gigabit wireless backbones, right?
True.
I mean, applications. And maybe we can have sessions in RCN trying to target those kinds of things in here.
I just want to, so basically the next two power platforms are actually envisioned to address that. So it's again a shameless plug for the upcoming RFP for the next two platforms. So if you are interested in building a platform that's more application industry vertical focused, because that's the feedback we are getting from industry, is to focus on applications use cases to drive the technical requirements. And that's something that we are addressing in terms of funding the other power platform. One initiative I just want to mention, it's not a US-based one, but it's in Canada. It's called ENCOR, ENCQOR. It's a $400 million initiative between 5 telecom operator and infrastructure companies and Quebec and Ontario provinces, where they're actually doing exactly that, funding SME startups, companies to come to the table, developing a 5G network and actually having them develop applications to sort of stress test and see feasibility. So again, it's happening worldwide, and I think we want NSF to hear that too.
Well, I think that seems like another place where industry academic collaboration could be brought to the fore, because I think this is one of the goals of our program and also RCN to have a better collaboration with industry and academia. And personally, I think we haven't really, in RCN, we get a C for that right now. We haven't really made any progress on that. So maybe some of these things would lead to that, where industry and academics can collaborate, especially for things which are aimed at particular use cases which are of interest to industry. Okay.
All right, I think we're kind of running out of, maybe we'll just wrap it up.
We have time. I just wanted to, and we can still discuss, I wanted to, if you want to have some closing for this one, but I wanted to loop back briefly to the test bed.
Yeah, so I think maybe we'll leave time for that. So why don't we just wrap this up there? And I think so there were a couple of other things I wanted to talk about in this panel, but I think it might be better to talk about them in the context of the test bed anyway. So we could just go straight to that discussion. The one part I just wanted to, on the Moonshot part, I guess wondering how do we think about connectivity, and we can think about this maybe offline. Right now we maybe just use our phone for either text or calling, but you know, what would it take for us to have this meeting virtually and not have to travel here? And part of that's a connectivity issue. And are we, you know, can that be a moonshot view of this? Anyway, I'll leave it this because I think I'd rather leave time to go back into the nitty-gritty of the test bed.
Any other slides that you wanted?
No, it's fine. Yeah, you want
of interest to NSF too, because we do virtual panels. And so we use this Blue Jeans software, and it's actually pretty effective for the most part. But I think that could be a moonshot, that how good an experience you have with a virtual augmented reality. Yeah, I understand. Okay, so we have about a half an hour discussion wrap up for the community testbed development aspects. And so I know that, so just again to refresh your minds, you know, there are, in RCN, the interesting problems have been at the interfaces. So there have been working groups, especially in networking and signal processing side. Marco and some other folks, Ismail, and even some of the UW folks, Seattle, Tom Henderson, have been really looking at that, and they've been doing end-to-end simulation, a lot of work, interesting work going on there. And then there's been more recently hardware signal processing that has taken traction. And so yesterday the idea came that, okay, there's a different groups out within the country, in the U.S. are developing these test beds. Berkeley, Wisconsin, and I know that Jananth at CMU, he's developing some, and I'm sure there are other folks. And some are building the whole thing, others are taking eval boards from, you know, Velocity, Qualcomm, wherever, and you're just playing with networking protocols. And the idea here is there an interest to have an end-to-end simulation, or not simulation, a testbed platform, which could be, you know, I don't know how it would look like at the end. You know, it could be in one place and it's accessible like a mini version of PAR or whatever, or ideally at a cost point that can be replicated in a modular fashion at different institutions. And so the first thing is, you know, what we want to gauge is interest, and two, who are the people, you know, who are working on, you know, RF, and then ADC, FPGAs, because you'll need that, and then the networking protocols. And who would be the people who would be interested in actually involved in being a part of a team that actually creates the specs for it and builds that test bed, and then who would be interested in using it at the end, and then eventually it could also go into, you know, provide technology for power platforms. So, so first whoever I want to hear from folks here, you know, how many people, are there any people involved in building it, and who would be interested in using it, and so on. So I know that there's you.
Hi, so I'm from India Networks Institute in Spain.
Okay.
So we have like two different tracks right now. So on the one side, we are working with off-the-shelf devices. So using 1180 devices with the Qualcomm chipset. So with these ones, we are just doing we have the whole protocol stack. So we are trying to do some reverse engineering in order to be able to obtain data and also modify beam patterns and these kind of things. But of course, it's very limited. We cannot do whatever we want. And on the other hand, we are building right now, we bought a large FPGA and also an antenna array front end of 60 gigahertz. And we want to do a platform with that. And we are trying to do this as an open project to be able to collaborate among different institutions.
Very good. So you bought an FPGA and an antenna array for 60 gigahertz.
Yeah.
Where's your antenna array from?
So we bought the one from Sivers IMA.
Okay, it's some European.
I think they are from Sweden.
Okay, so it's a single beam phase array, 60 gigahertz.
Yeah.
Okay, and then you're developing FPGA solution. All right, very good. So you would be interested. You would be interested in being part of some development like that. And so, do you think your expertise is more? It seems like more on the FPGA and algorithms part, or?
Yeah. Yeah, not on the other side,
okay.
for sure.
Okay, very good.
More like a networking group.
Networking group. So you can. And do you think you're interested in developing real-time implementation protocols?
Yeah.
Very good. Excellent. Excellent. So we need to get your name, absolutely, and contact. Who else? Aditya, are you interested in building something real?
Yes, so what? Blow, well played.
A real emulator?
No, so the project that we are running right now is to build a 28 gigahertz array, a fully digital array. So we are basically building these boards that have 4 channels each, and they are extremely small, like they're going to be 2 cm by about 5. So you can tile them to create arbitrarily sized, rectangular arrays. And so we are working on fabricating this board, everything using commercial off-the-shelf ICs from Analog Devices and a bunch of other different players. And so we are still very early, but we hope that by the end of the year, we'll have a proof of concept, fully digital array at 28 gigahertz working.
28 gigahertz fully digital, how many elements?
So the thing is that every daughter board has 4 channels, but you can tile multiple of these daughter boards arbitrarily in both directions to create hopefully arbitrarily sized.
Okay, so it's like so you have a basic module which is 2 by 2, 4 elements, full ADCs, DACs, and everything, and power amplifiers and everything in there.
So the board that we're designing right now is actually, it goes, say on the transmitter side, it's 4 channels IF in, and then some reference LOs, and then you multiply the LOs up, and then you mix, and then you filter, amplify, and then you connect it to antenna ports. And then on the other side, the antenna is going to, so the daughter board has IF in and antenna ports on the outside, like these really tiny XMPS connectors. And then the antenna board on the other side is going to be like this, is going to have either patches or Vivaldis or whatever, with connectors at the bottom. So you can just like click the antenna on top of the daughter board.
Okay, very good. So you'll have, so this will be a modular, you could scale it up. So that's fantastic.
So if you want to scale it up, if you want to have a different number of channels, you'll only have to redesign the motherboard, because the motherboard has slots for each of the daughter cards that goes in. So you have to redesign the motherboard. So the motherboard is going to take in baseband IQs in, convert to IF, and then feed the IFs into all the daughter cards. And the reverse process.
And so this is basically just RF, and you'll have IF interface, and then we can put it to the back end ADC. Very good.
That's it.
So,
I mean, we have nothing working, I must say.
Oh, that's okay. We know that. I mean, we'll make it work.
And so, and I'm the engineer, so the probability of failure is
high. All right. No.
quite significant.
No, that's very good. No, that's great. So you're in. So that's great. You'll be another RF player. Potentially, so that hopefully,
But we're new to the RF game, so take
No, I think this would be there's a lot of collective expertise on that.
I wanted to maybe talk about 2 initiatives that I've heard about, but I don't know fully the status of them. On the network layer stack, there's out of Raymond's group, the OAI from France, the organized for open air interface. So they've already built a full new radio stack, but below 6 gigahertz. And my understanding is that there's some effort already to try to use that above 6 gigahertz, which the protocols don't change that much. You just have to speed it up. So hopefully that can cover the upper layer stack, to say Mac and above. And then I've seen this. So does anybody have much experience with the MathWorks side? Because MathWorks did provide an LTE.
MathWorks?
But the way that you could put the whole blocks on the LTE part and then simulate and then actually synthesize from that FPGA code, right?
Beautiful. Yeah, I think this is something I'm going to loop back with them, because
I know they have a 5G effort too, and I know Mickey, you would talk to a little, have a little experience with that.
MathWorks, we will loop back with them, because you can create HDL code from MATLAB.
Basically, we are evaluating the 5G toolbox from MathWorks to using exactly that, the HDL, to go from Simulink to HDL directly.
Beautiful, yes. So we, Yes, so I think I wanted to get MathWorks folks here, but I just didn't get to do it in time. So we'll loop back with them. So how has your experience been so far?
It's in beta, so basically we're working on it.
Okay, good. So we'll keep you in the loop too, because I think that could be useful. Because I think I can share, in our group, we were working with Xilinx boards, and we use Simulink as well, and their system generator as well. And in the end, in some cases, you have to just code it up yourself, or system generator works quite well too. And Simulink is good, but when you come to tricky timing stuff, it can run into trouble. So, but I think MathWorks may be interested in putting some resource in it too. So we'll loop back on that. Cool. Okay, hang. So who's Ismail? You're taking. Okay, so yeah, very good. So all the players, let's keep noting. So, okay.
So we are more focused on network stacks. So we have a project with Army right now. So it's not related to millimeter wave right now, but what they want to do is to use 3GPP stack, but use their own radio. So basically what we are doing is we use OAI stack, all these LTE stack, and PDCP, all these things, but combine it with EMU. So this EMU is this Army research simulation or emulation platform. It can run on the multiple virtual machines then connected by the Ethernet. But underlying radio, so could be any radio. And right now, we use a wireless LAN radio, but on the top is 3GPP stack.
Okay, so, and this is also for real-time implementation.
So they don't have real time right now. So requirement right now is, but you can run on multiple machines to set up this simulation platform.
Okay, so I think this could be. I wonder if that is more tied into something like NS3, or would it go into some testbed where we would want to. So testbed, it's another thing I want to emphasize, and this was one of the, and I don't know if Kate is still here or not, but there's also this channel measurement, right? So once you have your testbed, you have a channel sounder too, whether you like it or not. Channel estimation, and you can do all sorts of channel measurements. So there's a non-real-time operation used too, where you just get traces and you can process. So everything. So you could be, so you'll be a good player for the networking protocols.
Yeah, I think this is one step further than NS3. NS3 is a more event-driven simulator.
Yeah.
Right? But this thing, the EMU is also a simulator, but somehow you can set up on multiple machines. The underlying, you can use Ethernet to simulate, put something to simulate the channel, and also you can plug in different radio. So right now we just use wireless LAN, because that's already built in.
So is that EMU? Is that an army thing?
Yeah, I think the EMU is one of the simulator came out from Army research or Navy research.
And it's open. They are willing to share.
That's also open source.
Okay, very good.
Right now they have a very simple built-in ad hoc wireless LAN-based thing. On top of that, so we are trying to integrate OAI stack, the LTE stack.
Is that the same one that Sandeep was mentioning, OAI open air integration?
Yeah, right, yeah. But OAI is right now is running on USRP platform, So we are trying to do is to take out the radio part, but put any kind of other waveform generator in. So they, because they call the simulator. So the simulator, you can build some adaptation, things. So.
All right, very good. So I think we will, you'll be on the networking side. All right. Who else? Yes.
Okay, Ahmed Suleiman, Embry-Riddle Aeronautical University, Arizona. A few years ago, we were working on spatial modulation scheme, and there were a lot of theoretical, input on the scheme, but no one had, presented a result from Testbed. So what I did was to bought some off-the-shelf warp board developed by Rice University, and we were able to put this work in 2x2 MIMO. We extended it to 4x4, and we were able to collect some real-time data from this to show that this system actually works. So this was an example of MIMO-based or spatial modulation-based testbed. I developed it. It works at 2.4 gigahertz, and we could also go at higher frequencies, just about changing the antenna.
Well, I think so. This is actually a good point, but warp boards will not work in this. So this is like building a warp board, version of warp board for millimeter wave. So warp sampling rates are not going to be fast enough. So that's why you'll need a dedicated FPGA development. And this may also be true for some of the networking protocols. It's non-trivial because your data rates are very high. So we'll have to think about, conceptualize, what that architecture looks like. But, yes, so this will be developing a new warp board.
Okay. So on the RF side, like I was telling you, channel sounder is all about just, one can build them oneself by putting local oscillator, signal generator,
well, that's exactly what.
Receiver, and you can choose the frequency as much as you want.
Yes.
Now, developing that into MIMO is also possible. Right now, we're using one transmitter and one receiving antenna.
Okay, so you could potentially contribute to the RF part too, because one of the things is that we have discrete solution and we could, and there's different front-end architectures that could be integrated into an integrated RF board, which could be used. So, for example, Wisconsin could provide lens arrays for beamforming, and, Berkeley could have phase arrays, or Aditya could have a phase array on steroids. Fully digital beamforming phase arrays. Okay, who else? Ismail, yes.
So I think we have a couple of platforms that can be of relevance. One of them is, maybe I can speak also for my collaborators. We have a project from NASA with David Matolak and Hanimer Puyan from Boise State. So we are developing channel sounders, which will turn out to be also some test beds at 3 different frequency bands. What we have at NC State is PXI-based platform, which we already started doing indoor measurements. We have a lot of, we are collecting data. These are for now based on horn antennas and physical steering. We are looking into now moving outdoors. We have our FCC license at 28 gigahertz for a year. And Hani already is doing measurements at 60 gigahertz. He has a Keysight platform at Boise State, and David is doing 90 gigahertz from Rode Schwartz. So we will have 3 different platforms. The main idea is we will go to airports together, and we will do experiments in the same exact environment to see how the propagation they change in these 3 different frequencies. We are interested to do air-to-ground scenarios, but that's not easy, obviously. But I would like to echo what you said before. Once you have these test beds, you can use them as channel sounders. If you have a channel sounder, you can use them as test beds. We are also looking into using our platform for drone detection. I don't know what will be the range and how feasible it will be. But we also had some tests for example, indoor mapping. We were trying to map the size of a room in an indoor environment. We sent a white paper to DoD, but it didn't go through. So that's one platform we have. We have the 2nd year funding coming, so we are looking into what phase there is we can integrate to this platform. We are trying to get a quote from MMWAVE, but we have been not successful.
Good luck.
So if there's any of you have expertise on or suggestions on phase array platforms for integrating to NI, that would be very helpful for us. We also have a USRP-based platform at 60 gigahertz with the Pasternak Rubik. We also have some measurements. It was the main motivation for developing that was carrying the mid drones. So there was a poster yesterday from NYU. We have to, for one of the projects, we have to do air-to-ground measurements. And recently we started looking into doing an FPGA-based, I mean, I don't know if you want to talk more about that, but with a master student, whether we can do with FPGA, I'm not sure where it will go, but that's another thing we are doing. And the last thing is we had evaluation boards from TensorCom based on 11AD, but what I understand is they are shutting down or going out of business. So one of them stopped working. I think they were very reasonable for doing air-to-ground measurements. The range was up to 500 meters, but we couldn't do air. I mean, they stopped. We have a paper, a simple paper in VTC coming up based on the measurements with those, but so those are some platforms we have.
Okay, so that's great, and I think that actually brings up another point that people who have already invested in. So one point I want to clarify: if you have a test bed, it's also a sounder. If you have a sounder, that's not necessarily a test bed, because sounders you cannot test all the protocols. So it doesn't necessarily go the other way. So for example, people who have already invested in NI equipment, right? They cannot do networking protocols where you say, hey, you can put it whatever you want. So with your PXI, if someone built a FPGA-based networking interface, you could use that, for example. So I think, and then the front-end RF could be useful for you too, just like you said, phase array or lens array that you could use. So I think that's the modular part that could be really useful here. But where would you think your main contribution would be? In processing or developing networking protocols and FPGAs, or where could you contribute? Or maybe you'd be the user.
I mean, it can be user, but when you say testbed, this is a communication testbed all the way going to networking layer, or can you consider, for example, you're also interested in sensing localization type of applications in indoors, so testbed can be many different things, like it's not necessarily networking testbed.
So that's a good point, and I think what I'm initially thinking is end-to-end communication with real-time implementation of protocols, where you could play with it, and it could also be, for example, I can just, our plan for Wisconsin has been to create these access points with beamforming capability and then put them in different buildings and create a virtual network of 3 or 4 access points, and then put you mobile devices or mobile stations accessing and creating networking protocols. So I think that's what I'm thinking, which potentially could be replicated. But this will be fleshed out as we go along.
So it's also, one other thing we are thinking is we have right now, it's obviously channel sounder unidirectional, but if you have 2 more pairs, one more pair of millimeter wave radio heads, we were thinking of extending it to bidirectional, then it becomes you can do uplink and downlink communication. So that's also.
Yeah. Okay. Shin.
So far, we mainly work on the implementation or just simulation on the MATLAB platform. We implement all the channel models and also 11 AD and 11, AY kind of protocol stack. I think we can extend to the testbed. The reason is testbed has too many platforms. We don't know which one we can apply, which one will survive. That's a major problem. I think it's no problem. We can extend to FPGA kind of things, but really we have to choose something will work, because you can see the different things. I don't know which one will work. But the protocol itself, a lot of cases doesn't really depend on those platform. To some extend the simulation part actually challenging. You have to build something, and for channel, for example, you can measure, but in order to do the simulation, you actually have to understand channel model to actually build it.
Yes. So I think you could, So that could be also the end-to-end simulation that Marco is doing. But I think that brings up another interesting point where a lot of us will have simulation software in MATLAB, and I think if math works, especially if if we develop it in Simulink, or maybe their HDL coder is even more advanced, so I'm going to loop with them. Maybe next time that's an action item for the organizers to have them here for sure, to see how much of that could be transported onto the FPGAs to create an HDL code. But some of it would be non-real-time, some of it would be real-time. Okay, so we are, Marco, yes.
This is something, I met these guys, ITRI, I don't remember where, from an Asian. Yeah, right? Taiwan, right? What's that? That's from Taiwan, right? Yeah, exactly. And they have a platform, a fully MATLAB-based integrated. It's very interesting. I think, they should.
Yeah, actually, I know the team working on. They have a platform supporting millimeter wave communication. Everything is implemented in C and MATLAB. And now I think I spoke to them because I work on the OAI implementation. We're trying to create an interface to integrate OAI on top of their millimeter wave platform.
Yeah.
And last time when I met them in June, OAI workshop, I invited them to join the workshop this time, but they are busy for MWC. But they definitely told me that they are interested in join this community.
It's funny because I invited them too, and they told me that somebody else invited them. That was
I think that's me.
Okay.
Yeah.
And there's a very nice presentation that they public domain that I found that's from the OAI meeting. It's very nice.
Yes.
Yeah. So I think we should take a look. I will share.
Yeah, this is below 6 gigahertz right now with 56 megahertz bandwidth, but they could be a partner in helping us build some of the components. Very good.
It is because, in Taiwan, the license band is not in 60. So they choose lower
frequency. Very good. So we'll loop with you too. Who actually, before I forget, that's also an interesting point that a lot of companies are also now putting out eval boards, including analog devices. And so we need to be, there's a lot of things that's available out there, and some of you will have information on that. Anybody else who wants to share who is working on test beds or would be interested in this effort? So if we had this available, how many would be interested in using it? A lot more. Okay. So I think what we're going to do is we'll definitely follow up on this because and with a little more structured information so that we get information from you, get a kind of a mailing list for it, for a group setup, so that we can develop a framework, what this looks like and what the specs would be and build on it. And our goal is to, maybe have definitely next steps for the next meeting, which is 6 months, and maybe in the 6 months or a year at most. We have 2 meetings left, so at least at the latest, at the end of that, if the community wants to do it, then there should be a plan and the players identified. So, okay. Any other comments by anyone? Do you want to say anything, Greg?
Yeah, I think this sounds like a good plan. I think kind of coming back together and making sure that whatever comes out is modular and has well-defined interfaces will kind of be the biggest key to success. So, if everything is kind of undocumented or just kind of ad hoc interfaces, one person might get something cool to work, but it will be extremely hard for everybody to adopt. So we just need to be very kind of cognizant of that.
Absolutely. That's a very good point, and I think that's an excellent point. Yes, I know exactly what you mean. And I think, but the most important, the most beautiful thing about an RCN like this, and this is my experience first time with something like this, is that the collective expertise in the entire room. It's like for every interesting or important challenge, there's somebody who is interested and has the skills to do it. So I think that's what makes it successful. So it'll be a team effort. So thank you very much. And I want to thank the local hosts again, Sandeep, and I don't know where Pat is. Pat Donahue has done an amazing job. She's the one who's the chief organizer, and then William, who was the AV guy. I know today we have another person. Thank you. And also, where is Adam? Yes, thank you, Adam. So let's give him a hand of applause.